a very, very warm welcome to this event which is called the Quantum Leap. And we are celebrating the contributions of Professor Apoorva Patel, who is going to superannuate at the end of this month. And this is a day-long symposium which has a series of technical talks from the who's who of quantum computing and quantum technologies in India, interleaved with several personal anecdotes of old friends, colleagues, students of Professor Patel. And it's been a great honor to host all of you here, and I especially want to welcome and thank all those people who traveled from far and wide across the country to come participate in this event. It's a gesture of their affection and respect for Professor Patel. So without further ado, let's get started with the proceedings. So to begin, we have a friend and colleague of Professor Patel, Dr. Rajan Gupta, who is at the Los Alamos National Laboratory. He's an LANL fellow from the theoretical division. Dr. Gupta did his MS in physics from University of Delhi. He then went on to do his PhD in theoretical physics from Caltech. He was a Robert Oppenheimer fellow, Los Alamos National Laboratory, and a postdoctoral fellow at Northeastern University, and honorary postdoctoral fellow at Harvard University. He was a guest professor at University of Wuppertal. He was also visiting lecturer at Caltech. He was the group leader of elementary particles and field theory at Los Alamos National Laboratory, and he is currently the program manager for high energy physics there. His research interests are standard model physics, lattice QCD, high performance computing, energy and climate security, smart green grids, and global development. So with that introduction, let me hand over to Dr. Gupta for his message.
Thank you very much. It's something that I was confused. I thought the group was confused. But here I am. I have no idea what this is. I've come to my office, but here it comes. And here is the question saying, oh, in 15 minutes there is this meeting. So the reason this is funny is the first time I met Apoorva, I think it was 1981, early 1981. He had started, or he was in his second year as a graduate student at Caltech. And we met in the hall. And I forget, somebody introduced us and said, oh, there is the mic at the speaker. So, and there was a Apoorva. So I said, okay, what are you interested in? Are you interested in sound? What? Sound.
Just again. He's coming. Again. This is too.
Because in those days, there was a lot of
Yeah. I, you know, I
Start. How long were you
1 month. Months.
here? This guy who start from maybe he can tell now how bothered he was. He wasn't as concerned. So I had a good relationship with people at Kolkata. Uh, I told them, like, hey, why don't a favor this guy really good? Can you come as a post? Type was met. Do you remember?
Just a phone call.
Yes. And they both came to me. Rajan, are you sure? This guy doesn't seem like people are. Then are you sure? So when we tried to talk to him, answers were I have no idea. And to cut the story short, he offered, start.
In terms of research.
Completely not. Completely not. So taking all these things now where we case for him. Use it. Bring notes and books. That was a long working with him and enjoying all of it. And then another thing, the actual classmates, what was the working?
Now it's fine. Yes, sir. Now you can speak.
So the last story is in one of those times when the four of us were again together at Los Alamos. So one evening we decided to go to a disco. So we asked Apoorva, do you want to come? He looks at us, says, okay. So we go to a disco. So here are the three of us dancing, drinking, and there is Apoorva standing there with a smile on his face. So after about 2 or 3 hours, ready to go home, so we asked Apoorva, oh, did you have a good time? And in the characteristic manner, he sort of waved his head the way we remember him, said, yeah, it was interesting. So that was another wonderful memory of Apoorva that I cherish. And let me end with the statement that at one time I asked him. So the thing is that Apoorva came in fall of 1980 to Caltech. We met in 81, and then we worked together. I left in 82, but I was coming back very often, and many times I was sleeping in the same sort of one of the houses in Caltech, and which was one of these shared places with 5 or 6 people staying there, and I remember cooking rajma along with Apoorva, and we would eat that. So anyway, he graduated in 84, and I forget, at some point I asked him that, Apoorva, I think you're almost like I was your PhD advisor and thesis advisor. Because at Caltech, we really didn't have a supervisor. Nobody else did lattice QCD except for 3 or 4 graduate students. He looked at me and he says, yeah, I think you can say that. So with that, I'll stop. It was an amazing time spending with Apoorva, an amazing collaboration, an amazing sort of just us living this wonderful life of just doing science, having fun, and 2 totally opposite personalities having a wonderful 10 years of fun, collaboration, and just fond memories. So thank you very much, Apoorva.
Thank you, Rajan.
Oh, you can say a few more words, Ziv.
That's enough.
And the funny part is none of your colleagues are laughing. They just don't even have a reaction. I mean, what do? You don't laugh when there's a personality who's 4 sigma off the chart. Anyway, Apoorva, you got to say a few words about those years. Come on.
What about you?
No, those days and times. You don't have to tell anything about me. Or maybe you want to tell. You can say what an idiot I was, You can say anything you like.
Yeah, I enjoyed all my experiences, whatever it is. There were lots of turns this way, that way, etc. But that's part of life. And they are all memories one can recollect and ponder on once in a while. Life goes on.
I guess it is still characteristic of Apoorva. I shouldn't expect anything more. Anyway, let's move on and continue the celebration. I don't think I'm going to get anything more out of Apoorva than what he just said.
Hello.
That's all I have to say.
Thank you, Dr. Gupta. That was a very beautiful account of the lighter side of your, shared memories with Apoorva. Move on. Speaker. We have who was he's going for quantum he associate laboratory in assigned then on under
the
in my of
and then to do like tomography or like to sort of figure out what the state is, you measure it, you sort of rotate it using a bunch of different unitaries, then measure it, and finally you observe the measurement. But the point is that like there are sources of error in all of these steps. There could be step when you prepare the state, there could be error when you prepare the state, there could be error when you apply the matrices, when you apply the unitary transformations, like it would be imperfect. The state itself could decohere over time in the computer, and finally there could be errors in the detector that you. So all these are like very difficult problems to solve, but just for the sake of simplification, I will assume that the decoherence and the imperfection of the gates are not there. So the sort of the middle two steps in this picture sort of, or at least, yeah, the state is not like sort of decaying in time, and at least the use you apply to are not noisy. But I will assume that there is like error in the state preparation, and there is error in the detector, right? And this is what, so in the title there is a word spam, S-P-A-M, and the spam actually stands for state preparation and. So this, so spam, the tomography in the context of spam noise means that you want to do tomography, which is like the estimation of the quantum state in the presence of state preparation and measurement. Right? And we want to do this in the most general setting. Sort of that's the aim of this work. Now, we basically assume that there is like some unknown state coming to you. That's the state preparation error, essentially. And to sort of model noise, we will model it using in the most general way possible, using a completely unknown stochastic. Right? So we assume that all the other sources of error can be taken care of, and the state can be transformed before measurement using some unitary but you always know it. And so the observations sort of have this form. The state is unknown, but there is a known unitary, and then the diagonal happens because you are like measuring it and sort of polarizing the state. But there is an unknown A, which is an unknown stochastic matrix acting on sort of the measurement outcomes. Right? So the usual game in tomography is like, okay, the state is still unknown, but there is no A is identity usually. And so the game is sort of to design a set of unitary operations that will give you enough information about the state row. So it should be A and rho. But now there is an additional noise on top. So the sort of the sort of the algorithmic task remains the same. You want to design a set of unitaries that will like reconstruct you both the unknown stochastic matrix A, which is the noise in the detector, and the sort of the unknown state row, which we assume to be unknown because we assume there was some error in the state preparation. Now this is a very well studied setting in literature. But usually what people do is they'll assume something about either rho or A. And for example, like it is very popular to sort of assume that the unknown state can be anything, but the noise has a certain structure. And the problem becomes sort of tractable if you assume that this A is like an invertible matrix, but it's a noise matrix. It need not be invertible. Or you can assume that the noise is acting independently on different parts. And you can sort of assume that it has a certain correlation structure. So all these makes the problem sort of somewhat tractable, and people have studied it in those settings. And another way, or the other way of solving this problem is you can sort of assume something about the state itself, right? So there have been works where people assume that the state is known. So you have a probe state that you know, and you know what that state is. So now the task is only to reconstruct the stochastic matrix. Then also this problem becomes kind of easy to do. Or you assume that you don't want to recover this you don't care about recovering the noise. You only care about the state. So all these simplifications are possible. All these assumptions simplify the problem, and you can solve it to varying degree of success. But the question we want to ask is, what is the limit of sort of this problem? Like, if you assume nothing about the state and nothing about the noise, what can you do? Is this problem even solvable? Like, can you, from the measurement outcomes, can you get the noise and the state simultaneously? So we call this problem the simultaneous tomography. And the first result that we show is that actually it's not possible. It's not possible to recover the state and the noise uniquely just from this measurement setup that I showed you. And I can give you a very simple example, and you will understand why this is the case. Just take a single qubit, and suppose you see that whatever rotation you do on that state, and you measure it, you always get 0 and 1 with equal probability. So the noise, the output probability distribution you observe, independent of any operation you do on the system, is always 1. And in that case, what is the state and what is the noise? So either the state could be completely mixed, and that there is no noise in the measurement, and you could be just observing a perfect system, but just happens that the row you started with is a maximally mixed state. That could be one reason. The second reason is the row you started with could be a nice and pure state, but your detector is so bad, so noisy that it only outputs uniform randomly. It only outputs a uniform randomly. So the point is that there is stochasticity at the output, and it's very hard for you to say whether it came from sort of the quantum nature of the measurement or whether it came from the detector being bad. So it's very hard to separate these two things. And this is a general phenomenon in this problem. And what you can see from the sort of the equation is that given a certain rho n a, you can find another rho prime a prime that will give you the same measurement statistics curve. But this sort of rho and a and rho prime and a prime are actually cleared by a simple sort of one-dimensional transformation. So that's what I have written down here. So a prime is just some linear combination of a with a certain other matrix, and rho prime is just a linear combination of rho with the maximum state. So, and there is a single parameter that controls this sort of transformation. Now people have called this gauge invariance of the problem, which is a lot of physicists work on it, so they like to call it gauge invariance. But it's quite a simple feature of the problem. Now there is the main result we show. So there is always a question. Okay, there is this one gauge invariance in the problem, this one parameter issue in the problem. But are there other But what is the dimension of this sort of invariance? Is it just one dimensional, or are there more things that are are there more dimensions that are sort of unknown? But in our work, what we show is that this is the only ambiguity. So there is an ambiguity, and the problem is not solvable in general, but it's only a one-dimensional. So, and you can show this, and we show this by exploiting some linear independent structure of the interleaved. But this, although the outlook is pessimistic, because you see that there is the problem is fundamentally unsolvable, it kind of tells you that okay, it's unsolvable, but only up to one unknown. And maybe the sort of the hope is that you can do everything up to this one unknown parameter, and this one unknown parameter you can maybe fix using some other information that is not coming from this measurement, some other prior information. So this is the first result, and in the second sort of after establishing this, we sort of go into, can we actually do this tomography problem? Can we recover the state and the noise matrix up to this one unknown? And we'll worry about fixing this parameter later. And we give an algorithm to do this. I will not get too much into the details of the algorithm because it's quite involved, but we can always look at the paper. But the algorithm itself is quite simple, and I will sort of explain the high-level idea. The point is that the things you can do, the valid operations that you are allowed to do on this sort of system are only unitary transformations. And unitary transformations will mix everything. It will mix the sort of the state with the noise matrix, and different components will get all mixed up. And you will sort of not be able to extract the information. Now, what we have seen is that if you take sort of the, it all happens in the super operator framework, but I will not sort of get into that part of it. But the point that we see is that, but although you're only allowed these unitary matrices, you can combine unitary matrices in different ways to get sort of these canonical matrices, to get a kind of this canonical matrix that I've written down, EIJs. And it is basically, and this EIJ matrices, you can think of as they are like the basis vectors in the space of operators. So there is a 1 at one position in the matrix and 0 everywhere else. So the point is that if you could apply this kind of an operation, which you cannot do physically, but if you could apply this E operator to a quantum system, then it will actually isolate a single component of the state and the noise that you want. Something like a single component of the state multiplying a single element of the noise. So it will isolate the thing that you want. And then you can take that thing and do a simple post-processing to like separate rho and A up to this one case variable that I told you about. But the problem is that this E is not. But you can always write this E as a linear combination of a bunch of unitaries. So the nice thing that we find in our analysis is that, okay, you have to take a combination of unitaries, which is not something you can do natively on the system. But the coefficients of this linear combination are actually all positive and they sum to 1. So this gives you a way of sort of applying this transformation, but as but not on the computer, but on the classical set of things. The way you would do it is basically you would actually apply U1 to UL on the quantum computer. You will collect the statistics of that, but the linear combination itself you will do outside the quantum, and that will sort of effectively apply this operator on the system, right? Or we can get the statistic of this application. But quickly, when you sort of have this idea, you will run into a problem, which is that actually this number, capital L, the number of unitaries you have to apply is like exponentially large. It's a very large number. So it's sort of infeasible to like apply everything. But the nice thing is that all these coefficients are actually positive and they sum to 1. So it's a valid probability distribution, these E coefficients. So instead of trying to like apply every operator and then comparing it, you can actually sample from the distribution according to probability Ci, and then you can so you will sample I with probability Ci, and then you will apply that unitary Ui to the system. And so you can sort of do instead of like computing this, sort of applying this Eij exactly, you can sort of do a Monte Carlo, right? And this you can show converges quite fast. And an additional thing the nice thing that we find is that actually the set of unitaries you have to sample from are also like quite tractable. Like they are just a subset of what are called preferred circuits. So like, and they are like very easy to implement on a computer. So it's like it's not super hard. Once you sample from the distribution, it's not super hard to apply to the system you want. And yeah, and I as I said, I don't want to get too much into how the algorithm works, but basically, once you apply these EIs, it's quite trivial to get the data, so that you just isolate the component that you want, but only up to this unknown. Now, the question comes, how do you fix this unknown? For this, you need some additional information on the state. And in the paper, we give a lot of different examples for this. For example, if you know that your state is a pure state, you can fix it. if you know that the state is sort of, if you know that the A is sort of tensored across different parts, again you can fix this. And a probe state is sort of something that was previously considered in literature. So you do this first with a known state, then you fix the alpha, the sort of the unknown parameter, and then you go back and do it for the state you want to do tomography on. And you can also do it if the noise matrix is a binary symmetric channel, which is like a common type of thing that you study in information theory. And you can also do it if there's an independent answer. So if you know that everything else is noisy, but there is like one qubit that is like clean, which is not noisy, then also you can. So these are like all the sort of ways you can fix this prior information, but like you need to have this information sort of before you do all this measurement business. And I'll not get into like exactly how to do all of these, but I'll give you the intuition for how to do it for pure states. And for pure states, as you know, trace of rho square is 1. That's a property of the pure state. So again, in geometrical terms, what that means is that the set of pure states, so if you just plot what trace of rho square equal to 1 means, it's just a sphere. It's just such a higher dimensional sphere. So all pure states lie on the surface of a very high dimensional sphere. But what I have told you with this gauge fixing business is that I know my answer up to one unknown parameter. So there is like a one-dimensional manifold or a one-dimensional line actually that is going through the higher dimension. And it's sort of piercing this sphere at exactly 2 points. Enters the sphere at 1 point and leaves it at 1. But the point is that the sphere is just trace of rho square equal to 1. That doesn't imply that your state is a valid density. For example, trace of rho square could be 1, but rho might not be a positive semi-definite. Right? And you can show that basically there are these 2 points where the sphere is pierced, and those are the 2 candidate sort of solutions. But only one of them is positive. One of them is a physical state. And in this way, you can sort of identify, okay, this is the actual state. And you can then use that to also identify the actual noise matrix. And so you can remove this one-dimensional gauge ambiguity if you know before that the state is pure. But similar ideas also apply to the other cases. Now, finally, let me just give you the complexity of this, which we have worked out in the paper. But basically, the unitaries you have to sample from are just can be implemented in a linear complexity. These Clifford circuits. The coefficients you have that I showed you are also easy to sample from. It's just a flat distribution of some sort. You can easily sample from it and do everything in this Monte Carlo fashion. And the total number of measurements you need to do everything is some 8 to the power n divided by beta square by d square. And beta and d are 2 features of the problem that sort of tell you how bad it is, sort of how hard to solve the problem is. Beta sort of measures how close you are to the sort of the mixed state, and d is it's a certain property of the state, and d is a measure of how close the stochastic matrix is to the worst possible stochastic. It's the stochastic matrix that always outputs the uniform distribution. So this is something we want to avoid. But this dA is the measure of how far A is from this pathological case. And the A to the power n is sort of is unavoidable because it's tomography, it's always going to be exponential. But we do believe that this is A to the power n is sort of optimal, because even in the case of no noise, when A is just identity, if you are only allowed to do independent measurements, the complexity scales as A to the power n. So we don't expect to improve in the case where there is no. So the n dependence is likely optimal, but probably there are more things you can do with the beta and d dependence. And we also know that given some of these prior information, you can actually reduce this complexity, but but in general it will be like some exponential. And with that, I'll stop the technical part, and if you have any questions, I'll be happy to answer it. Thank you.
Thank you, Abhijith. If you have any questions here, we can take them. Can you hear me?
Hello, yeah, I can hear you.
If you have one is
Oh,
unknown,
it's
rho
not,
2 is
it's not very
unknown.
clear actually. Can you?
Hello.
Yeah, it's not very clear. Can you?
If you have
move closer to
two, if you have two states, rho 1 and rho 2, and common noise packets, can
Yeah.
you then recover all of them simultaneously?
And if you have common noise, what was the next part?
And two states, rho 1 and rho 2,
Huh?
can you do simultaneous tomography?
Oh, I see. So if it's like, yeah, I mean the same framework should work, but yeah, I mean unless there is like some weird interaction happening between the, yeah, I see. So like, so yeah, I mean if you can always think of it as a single system with like a state of rho 1 tensor rho 2, right? It may not be so bad because you know that there is a tensor structure, right? And this tensor structure can even be exploited to fix the unknown keys. So actually having two states that are sort of independent is beneficial to this procedure. Difficulty will happen if the state is like entangled. If these two states are sort of, two systems are like entangled, then it becomes like a very general case. But yeah, but if there is like two independent states, it should be like easy. The same sort of principle applies there.
Any other questions? We have time for maybe one more question. Okay, Harsh.
I have two questions. How do you design the unitaries? Are they dependent on the state, the unknown state?
No. So the unitaries are like a subset of the Clifford group. So actually, they only depend on the size of the system. They are independent of the. They are independent of the state. So.
If no further questions, let's thank Abhijith for his talk. So that concludes the technical part of this talk. Over to you.
Yeah. So. Yeah, thank you for the questions, but let me quickly share the experiences that I had with Apoorva, but I will not take a lot of your time. So, I met Apoorva actually in 2014 when I joined as an MTech student in SCRC, and Apoorva was an affiliated faculty at SCRC at the time. And I was like super interested in working in quantum information, and I just went and talked to him randomly. I mean, I passed into his office one day, I guess. And my background was actually in mechanical engineering. So I had no physics background, no computer science background. And despite all this, when I sort of conveyed my interest in working with him, Apoorva was very encouraging. He never said that. He never said. He basically told me, "Oh, you should." The two things he told me was you should read Nielsen and Chuang, which is the sort of the fundamental text in quantum information. And he told me to take Deepti Mohan's quantum monomer course. So these were the two things that I got from this first meeting. And I would meet him regularly, and I remember the first year I was just doing exercises from Nielsen and Chuang and just taking it to him, and he was just telling me, "Oh, you did this wrong, you did that wrong." So he was just helping me sort of understand because I had basically no background. So he really helped me the first year just to understand the basic stuff. And then we started working on my MTech project, and I joined for PhD, and we worked on a bunch of algorithm stuff. And we would meet regularly from 2015 to 2020, almost every week. And Rajan mentioned that Apoorva doesn't talk a lot. I would add a caveat to this. Apoorva does talk a lot if you ask very like pointed questions, like technical questions. And I can confidently say, like, during these 5 years, I met him, like, almost 70% of the meetings, like, he was just educating me on various aspects of quantum theory and physics in general. And yeah, it was always fun talking science with him. And like one thing I actually learned from him is always like connecting like physical intuition to algorithm. which he does very well. At least I think some of it has rubbed off on me. So I'm always thankful for that. And I think I can confidently say that meeting Apoorva has like changed my life for sure. He's a very interesting person, and yeah, it's very hard for me to express this. Yeah, but anyway, but I come from a family of teachers, and like, my mother would always like. She always likes this one Sanskrit poem that called Guru Vandanam. But I'm not gonna say it in like Sanskrit and butcher it, but the final part of it essentially says that a guru is someone who leads you from the blindness of ignorance to like the light of knowledge. And I think that sort of encapsulates what my experience has been with Apoorva. I have surely been enlightened. So
Thank you for that.
So fantastic. So, Abhijith,
yeah,
there is no contradiction. The thing you have to remember is my relationship to Apoorva was very different from yours. In the sense, we were two graduate students trying to figure things out. And the thing I found great with Apoorva was you didn't need to say very much. We seemed to read each other's minds on the physics and stuff almost intuitively. So in that sense, there was very little, I mean, it was just different. And I lost him as a teacher occurred later, so I'm absolutely thrilled that he has excelled in it, and not that I'm surprised. So fantastic work, and even more to enjoy him in years to come.
yeah, I had a great experience. That's all I have to say.
Thank you, Abhijit. Next up, we have actually invited an old friend and colleague of Patel, Dr. Grover, to give a video message, but unfortunately, due to his health condition, he could not do that. So he sent us a written note, which I have the pleasure of sharing with all of you. And Dr. Grover doesn't require an introduction to anybody who is familiar with quantum computation. So he is the inventor of the famous Grover's algorithm. And but just a brief profile of Dr. Grover for the audience who are not familiar with him. Dr. Grover received his bachelor's degree from the Indian Institute of Technology, Delhi in 1981, and then he went on to do a PhD in electrical engineering in Stanford in 1985. And then he started working in Bell Laboratories. And he also worked as a visiting professor at Cornell University. He retired in 2008, but continues to be an independent researcher. So I'll now read out the note from Dr. Grover. Hello everyone, it's such an honor to be addressing this gathering. Thank you for the privilege. I and Apoorva go back a long way, more than 3 decades. He has so many good qualities that I admire, and I'll share a couple of them with you today. We joined together at Caltech as graduate students. Apoorva was in physics and I was in electrical engineering. We were all very nervous to be in a new country with new faces all around us. We all, being young students, did not dare approach our seniors, but Apoorva confidently went straight to Feynman, not just to a senior but to a Nobel laureate. He made friends with him so easily and got a picture click with him. Even today on Apoorva's website, one can see their picture together. Over a period of time, their friendship grew so much that Apoorva and Feynman wrote a paper together. After I finished my PhD and started working in Bell Labs, one summer Apoorva visited me. We got talking and he suggested some books on advanced quantum mechanics that we should both read. At Bell Labs, I was entitled to buy as many books as I wanted. So I went ahead and ordered one copy of each book for both of us. For me, it was just a click of a button, but Apoorva was very upset with me. He was really mad. It took a lot of persuasion to get him to accept the books. His honesty was commendable. He is one thorough gentleman. He has so many virtues, and I really respect him for that. I can go on and on about him, but I'll not keep you waiting to go on with the party. Wishing you a very, very happy retirement and lots of success in your future endeavors, Apoorva. Thank you all once again. This is the message from Dr. Grover, and we can all relate to those qualities in Apoorva that he has just listed. So with that, we move on to the. We then move on to the first live talk from an invited speaker here. So we have first up Dr. Parveen Kumar, who is an assistant professor at the IIT Jammu, and he was a PhD student working under Professor Apoorva Patel and graduated in 2018 from IISc. And the title of his talk is Quantum State Engineering Using Weak Measurements.
Okay.
Yeah.
Hi, good morning, everybody. Let me start by thanking Dr. Bala and his team for arranging this wonderful event for Apoorva. And today I will speak about quantum state engineering using weak measurements. I chose this topic because weak measurement was more or less the first technical topic that I learned with Apoorva. Okay. How do I change this? Okay. So when we start learning quantum mechanics, we start from its postulate, and one of the postulates does talk about quantum measurement. It says that when you measure something, the system will collapse onto one of the eigenstate of the measured observable. So for example, if we have a two-level system, which is in some superposition of up and down are just the notations. You can think of 0 and 1 or true and false or whatever you need. So after the measurement, the state will collapse to either up state or to the down state. And this is what we call the measurement back action. And typically we don't want this back action because our aim is just to extract the information out of the system state. But today I will try to convince you that this back action is not such a bad thing. One can use it for some good purpose. And today I will try to convince you that this back action can be used to engineer non-trivial quantum states. So what is a quantum state? What I mean by quantum state engineering is that suppose you have some state of the system which you don't know, it's an unknown state, and you want to do a bunch of operations, and at the end of the day you want to steer your system to the desired target state. And the desired target state could be a pure state, which we will represent by the wave function, or it can be a mixed state, which is represented by the density matrix. And this whole game is known as a quantum steering because here you are trying to steer the system from some state to the another state. There are some standard protocols that are being used for the purpose of quantum state engineering. One of the protocol is using the projective measurements, like you have some state, you do the projective measurement, it will collapse to one of the eigenstate. And if your target state is that eigenstate, you have achieved your target state. So in that case, your success is not guaranteed because the projective measurement is a probabilistic measurement. Most of the time you will not collapse to your target state. In that case, you can use a feedback. You can just apply a unitary rotation and go to your target state, but this feedback has to be very fine-tuned. If you apply slightly more or slightly less, your fidelity will decrease. Other thing is there are issues with the larger system. If you have a larger system, this means there are larger set of possible eigenstate where your system can collapse. So the success probability goes even down. And the final thing is the robustness. In experimental lab, we always have some noise. And if you have noise, this kind of procedure might break down. The other standard thing that people use to prepare non-trivial quantum state is thermalization. So suppose you want to cool down your system to some ground state of the Hamiltonian, what you do is you just couple your system with a thermal bath. It will suck out the whole energy and your system will relax to the ground state. But the problem here is when you have a larger system, then if you want to protect the ground state from the thermal excitations, your bath has to be really, really cold, which is very hard to achieve. So alternatively, we want a protocol that overcomes all these challenges. The protocol should have a guaranteed success no matter what you do, but if you come at the end of the day, your state should be in that target state. And we should not require any fine tuning, which is one of the things. And the third thing is we should be able to target any state, be it a pure state, be it a mixed state, be it an entangled state, anything. And our protocol should carry a reasonable amount of robustness against the external perturbation. I will propose a protocol that will use the weak measurement, and the whole idea is to use the measurement back action to manipulate your system state from the unknown initial state to the desired target state. What do I mean by weak measurement? Weak measurement simply refers to extracting partial or small or noisy information out of the system state. And because we extract partial information, we do not disturb the system by much. For example, here is John von Neumann, who is kind of an inventor of these things. He got a knock on the door and then he looked through the peephole, but the peephole is very blurry. What he sees that there is a person standing outside the door, but he could not recognize whether the person is a male or female, or the person is facing towards the door or facing away from the door. So there is some information, but not the complete information. And the good part here is that the person don't know that he or she is getting measured. So we don't disturb the system by much. We only induce a minimal back action. We use von Neumann measurement model, which essentially contains 3 stages. In the first stage, you couple your system with a detector, and typically we initialize the detector in a trivial state. So here we initialize the detector in the up state, and this coupling will create the entanglement. And then in the second step, we measure the detector only. So the rule of the entanglement says that if you measure one of the party, you get some information about the other party. And since we have a 2-level object as a detector here, the measurement can give the 2 results. Either the detector state will change or it will remain the same. If it remains the same, we call as a no-click measurement. These are just the names. You can call with other names also. And then in the third step, we reset the detector and we repeat the whole game again. So this is how the measurement works. Mathematically, just assume 2 parties. One party is system, another is the detector. The detector state is phi, the system state is psi, and then we apply a joint evolution in the joint Hilbert space. And this curly H is the Hamiltonian that acts on the joint Hilbert space. And in the second step, we measure the detector. So as I mentioned, the detector measurement can yield 2 outcomes. And based on which outcome we get, our system will get a different back action. And this back action can be represented using the Krauss operators. The M are the Krauss operators here. And when we average over all the measurement outcomes, we get an ensemble, and then we have to talk about density matrix. And so when we average over all outcomes, we call this as blind measurement. This means we are not looking at the measurement result. And the density matrix gets updated by this equation. But if we take the weak measurement limit or the continuous time limit, from this equation we can go to the Lindblad-Master equation. So the choice or the structure of this Lindblad jump operator L will depend on what Hamiltonian we use in the joint Hilbert space. So if your Hamiltonian, this curly H, has some local term that acts only on the system, that can be absorbed into the system Hamiltonian, that will factor out as a system Hamiltonian. And the joint term that acts on the system and the detector together will give rise to this jump operator L. So this equation, which we get purely with the measurement and the system Hamiltonian, this is a dissipative equation, and every dissipative equation will have some steady state. So we can find out the steady state, and which steady state will it have? It depends on the choice of L, the jump operators, and the choice of system Hamiltonian. And if I take a step back, the choice of L and the choice of system Hamiltonian will depend on the curly H, which is the original Hamiltonian that acts on the joint Hilbert space. So the whole idea is what steady state you want or what target state you want. For a specific desired target state, you have to choose this Hamiltonian carefully. So for example, if you choose the Hamiltonian in such a way that the system Hamiltonian is this generalized single qubit Hamiltonian, and the coupling Hamiltonian of the system and the detector is sigma x on the system, sigma x on the detector, plus sigma y on the system and sigma y on the detector. Sigma x and sigma y are the Pauli matrices. Then the steady state of the protocol will lie on this ellipsoid, on this blue ellipsoid. So it means that you choose a specific set of values in this Hamiltonian. So here I have 4 parameters. The coupling of the system Hamiltonian, theta and phi are the polar angles, and alpha controls the measurement strength. So each specific choice of these four parameters will take your system to a unique point on this ellipsoid. So which point you want to go, accordingly you have to choose these parameters. But now you can say that there are other states in the Bloch sphere which your ellipsoid does not cover. So how would you steer your system to those states? And the answer is very simple. You remember we initialized our detector into the up state, but in principle we can initialize the detector in an arbitrary state. So if you initialize your detector along the x-axis, your ellipsoid will point towards the x-axis. If you initialize your detector in the y-axis, your ellipsoid will point in the y-axis. So this way you can cover the whole surface as well as the interior of the Bloch sphere. And the other beautiful part here is I mentioned that each choice of the parameter in this set will take you to the unique point on the ellipsoid, but the vice versa is not true. A single point on the ellipsoid can be reached via multiple set of parameters. This means a single point on this ellipsoid can be reached with different protocols. So now question comes, which protocol should I use? And I should use the protocol which takes me to that target state as fast as possible. So this means there is a question of optimization. So I can optimize my protocol here. So I do the optimization. I have not mentioned here how do I do it, but I can tell you if someone is interested. So what do I get here is, this is my optimal convergence rate as a function of purity. So different states with the same purity will have same convergence rate, because different states with the same purity are connected by the unitary transformation. And by doing the unitary transformation, we don't change the convergence rate. But here we see some interesting behavior. We see that for the low purity state, the optimal or the fastest convergence rate increases as a function of purity. Then it gets saturated for some mid purity regime, and then it drops back. And the transition from medium to high purity regime happens at an exceptional point. So exceptional point is a very well-known feature in non-Hermitian physics. Some interesting thing happens, a lot of interesting thing happens at the exceptional point. And the other thing is in the low purity regime and in the medium purity regime, your system dynamics is oscillatory, like your system reaches to the target state in an oscillatory manner, while in the high purity regime, your system reaches to the target state in a relaxational manner. And this transition happens at an exceptional point. And similar connections about the optimality of the system with the exceptional point has been observed in other settings, for example, in thermal machines, thermal motors. So this connection is not unique. It has been observed across different branches of physics. And then our experimental friends at Weizmann has observed this steady state ellipsoid in their setup. They worked with the trapped ion system. So here you can see a single slice of the ellipsoid, and they could reach to their target state with a fidelity of more than 99%. To the most of the state, the fidelity is even 99.9%. So the key key takeaways from my presentation is like measurement induced backaction is not always a nuisance. It can be used for better things. If you don't care about the measurement readout, here we don't care about the measurement readout, we only care about the measurement induced backaction. And the optimal state engineering is connected with the exceptional point, which is kind of an interesting feature. And one can extend these things to higher dimensional systems. We have worked with single qubit, we have worked with 2-qubit system where we generate the entangled state. But in principle, you can go to even higher systems. And if you can go to higher systems, you can talk about phase transitions, which is kind of a hot topic these days, dissipative phase transitions. One can also talk about this measurement backaction induced quantum gates that we are thinking these days. And the final thing is this measurement induced state engineering is just not a hypothetical things. One can observe these things in experiments. I did this work, we published a couple of papers recently, and I did this works with Yuval and Edward at Weizmann, Kirillo is at Grenoble, Bern and Eger is from Germany, and the experimental group is at Weizmann, Roy Ozeri and Yoram Spira. So if anyone has any question, I can take them now. Yeah.
Thanks for the nice talk. So, in other kinds of measurement-based steering experiments, the fidelity of the measurement or the quantum efficiency of the measurement also typically plays a role.
Yeah.
And the higher it is, the more, I guess, higher fidelity you can get in the steering. It seems like it's not really applicable in this technique.
Yeah.
Can you try to explain that?
Yeah. Here we don't care about measurement inefficiency because we don't care about measurement result. Ultimately, we average over all the measurement outcomes. But the other factors like dephasing and relaxational noise, that will matter here, and they will do affect the fidelity. But we have provided the analytical results in one of our paper, but it seems that they don't affect that badly compared to if you simply do the projective measurement and apply a feedback.
You also talk about this exceptional point. So does that restrict to only certain kinds of systems or state preparations?
No. By the way, this optimization curve does hold in presence of inefficiency as well. So what inefficiency will do is, like I showed you the ellipsoid. If you have a dephasing, this ellipsoid will shrink towards the z-axis. And if you have a relaxational noise, it will just shrink towards the center. And the measurement inefficiency don't matter because I average over all the measurement outcomes. But this exceptional point is, it's somehow, so here during the optimization, what I'm doing is I'm playing with the eigenvalues of the evolution operator. And at some point of time, the eigenvalues becomes real and they become equal at some moment in time. And when they become equal, we get an exceptional point. But I think this eigenvalue will show the same behavior in the presence of inefficiencies as well. Yeah.
If no further questions, let's thank the speaker.
Yeah. And now my experience with Apoorva. Okay, that's the difficult part. But anyway, I joined the department in 2012, and I was very clear that I don't want to work in string theory, and I don't want to work in high energy physics. Then Apoorva typically comes to the department in the afternoon. So I came in the morning, and there are only two people who don't do string theory and high energy physics. One is Diptiman, one is Apoorva. So in the morning, I went to Diptiman's office, and Diptiman told me, no, I'm not taking any student this year. I'm too busy. Okay, then comes only one person. So in the evening, I went to Apoorva, and Apoorva told me, okay, if you want to work with me, work. I don't have any problem. So if it was not Apoorva, I would not have done my PhD from IISc. I would have gone somewhere else. So thank you for accepting me as your PhD student. I enjoyed working with Apoorva a lot. apart from physics, I learned a lot from his simplicity. He's a very simple person. You can go to his office anytime. He would never say no. He's easy to talk. You can talk anything. I have talked like very bullshit things about physics in front of him. He never got angry. So I learned a lot from his simplicity, his honesty, and his lifestyle. I have seen him teaching the class of one student with full dedication. So this is how he is enthusiastic and he is dedicated. I want to congratulate him for his retirement and for completing 65 years. And I wish him good health and best wishes for his second year. Thank you. Thank you.
Token of appreciation, we have a memento. So the next talk, and after this we break for tea. So we have Professor Umakant Rapol from IISER Pune, who will be speaking to us about atoms and ions as a platform for quantum computation, sensing, and other applications. So Professor Umakant received his PhD from IISc Bangalore, and then went on to do a postdoctoral research fellowship at École Normale Supérieure Paris, and then at University of Innsbruck in Austria. He worked for a while at GE Global Research before joining IISER Pune as a faculty, where he works in the areas of ultra cold atoms and ions for precision optical metrology, quantum information processing, and quantum optics. So I invite Professor Umakant Rapol for the
Yeah, thank you, Bala, for inviting me for such a great occasion. I would like to wish you very good health and also congratulations for beginning the second innings of your life. I wish you all the best. Yeah, so I have interacted with Professor Apoorva only in the last maybe 7 or 8 years, although I have known him since 1996, since I was a student here. Some of my batchmates and friends actually worked with him during their PhD. That time I didn't get much opportunity to interact with him, but in 2017, sometime in June, July, I got an email from him, which actually was the beginning of all the programs on quantum technologies in India. So the government was trying to, the Department of Science and Technology wanted to kick off, probably start something in quantum technologies. And Professor Apoorva Patel was the person who actually organized a meeting. And since he had invited a lot of people from the country who were involved in anything related to quantum technologies, I think that was the first time we actually started professionally interacting. And over the past several years of my interaction with him, I find him, of course, he has been a critique of the entire quantum technologies program in the sense, a positive critique in the sense that he kind of made some of us actually realize the practicalities and what is possible and what is not possible. And he's been an advocate of actually pursuing programs which can actually lead to something very tangible at the end of the execution of that. So I thank you very much for guiding us throughout this entire thing. And actually all this led to the culmination of the government starting such a big program now, the National Quantum Mission. Yeah, so I'll start with the technical part of my talk now. Yeah, so I'll give a brief overview about how atoms and ions can be used for doing quantum computing, as well as using them as platform for doing sensing, which beat the standard classical limits. So the first part of my talk is going to be on a few examples on how atoms and ions can be used for quantum computing. Now here are some pictures of some of the systems that have been successful in demonstrating their usefulness for doing practical quantum computation. The first one on top of here is yeah. So these the top three are ion traps, where you actually trap ions in time-varying electric fields, and you create a string of these ions. For example, this picture is a string of about 8 ions, fluorescence from 8 ions, which are trapped inside the center of what is called as a linear Paul trap. And these are different variants. I mean, the ion Q trap is again a variant of this 3-dimensional linear ion trap, where you trap ions on the surface of a chip, where you have a configuration of electrodes which generate time averaged electric potential for trapping these ions by applying radio frequency across certain electrodes. And in the bottom here is a picture of fluorescence from many atoms which are trapped in an array of optical tweezers, and one can perform single qubit rotations and 2-qubit controlled knot operations or controlled operations using what is called as Rydberg blockade, which I will come to in the next few slides. So, talking about atomic systems, here is a level diagram of one such example system of an ion, a calcium 40 isotope ion, where electronic states inside an ion are used as your quantum, the states of a quantum bit. For instance, here the transition from S half to D 5 half, which is an electric quadrupole transition, which is used for doing the qubit. I mean, the two states are used as your qubit states. And by shining light at 729 nanometer narrow line laser, you can actually do coherent operations on coherent drive on this S half to P half at D 5 halves. And the lifetime of this particular state, D 5 half state, is about a second or so. So you have plenty of time to do coherent manipulations and coherent operations. And then there are multiple other levels which are used for preparing the qubit itself, because you need to trap this ion inside. So you need to cool the ion. Even though it is trapped, it is still not occupying the ground state of the harmonic oscillator, in which the trap is a harmonic oscillator, in which you need to trap it in the lowest ground state. Now the other, so that's an optical qubit, where you use light. Your drive is light at some about 10 to the power 14 to 15 hertz. You can also have a possibility of using a microwave transition as a qubit. For instance, if you take the odd isotope, this is not the only ion which is used for quantum computing. There are beryllium ions, there is strontium ions, many other ions, but just I'm taking this example because I had worked with such a system. So you can also use the splitting in the ground hyperfine structure, ground hyperfine state, also as your qubit transition. For instance, in case of this 43 isotope of calcium, you have about 3.2 gigahertz separation between the two ground states, which can also be used as a microwave transition, qubit, in addition to the 729 nanometer, which is an optical qubit. The way these trapped ions are used for doing coherent manipulation and all these quantum operations are that, say, if you take an ion which is trapped in the ground state of the harmonic oscillator, then you have a tensor product of your internal states, which is S and D, which is your ground and excited state of, say, the optical transition, with the harmonic oscillator energy level. So you get a ladder of these energy levels, where you can excite on the carrier, which is only the internal state. This is like a molecule, okay? When there is an internal state excitation, electronic excitation, and there is a molecular vibrational excitations, right? Similar to that, these ions, when they are trapped inside this trap, if you have more than one ion, it's basically acting like a molecule. There is Coulomb repulsion, which keeps the ions away, and then if you can excite vibrations in this chain of ions. So that leads to these harmonic oscillator levels, and you can actually do a transition. There are 3 types of transitions you can do. You can just do the internal excitation of the electron, or you can excite on the side bands, where you excite the internal state combined together with an excitation of one phonon mode, or extraction of one phonon mode of this oscillation in the trap. Thereby you can basically do either on the carrier or on the blue sidebands this coherent Rabi oscillations. Of course, before doing that, one needs to prepare the ion in its lowest ground state, where you use principles of Doppler cooling and sideband cooling for bringing these ions in the lowest possible ground state of this harmonic oscillator. And if you look at, actually, if you take an optical spectrum of such a ion trapped inside in the trap, you get a spectrum which actually reflects all the different kinds of modes, the axial modes and the radial modes within the trap, because you have a linear chain. Along the axis you have certain trapping frequencies, and along the radial directions you have certain trapping frequencies, and then you can actually do a proper you can resolve all these sidebands, because the transition excitation in the transition line width is much smaller than the separation of this harmonic oscillator energy level. So you can tune your laser to any of these modes and excite the sidebands. Now, using these principles, there have been some successful demonstrations as well as commercial companies which have come on board. One of the examples is a spin-off from Honeywell, who developed more than 20 qubits of ytterbium ion based, I think it's ytterbium ion based quantum computer. There is not much information about what kind of ion that is, but it's probably ytterbium ion, and they have demonstrated more than 20 qubits with different metrics of what kind of connectivity they have, and all kinds of error rates, single qubit error fidelities, 2 qubit fidelities, and the kind of spam errors that are needed at the level of part in 1,000 or so. Then there is another company which got spun off from Maryland University, Chris Monroe's group, and that's this IonQ. They also have demonstrated now more than 20 qubits, and these are all in the form of a chip trap. So this is where you can either use the three-dimensional ion trap or a surface trap, where you can trap these ions on a surface. The other company, which is again a spin-off of the University of Innsbruck, where I had worked, they have also demonstrated, they have the best demonstration so far about, they have shown 24 qubit entanglement with these ions in this three-dimensional ion trap. Now, that's about the ion trap based quantum computing. Since the time is limited, I'm just giving an overview. I'm not getting into the details, but if you need to know some details, please ask me later. The other platform is neutral atoms. Now, in case of ions, there is a strong interaction between the neighboring ions, the Coulomb interaction, which keeps them away. And that is also responsible for creating the phonon modes in the system. 2 qubit gates, like the C0 gate, where you need a coupling between the neighboring qubits for executing the controlled NOT operations. Whereas in case of neutral atoms, if you just take neutral atoms, there is only magnetic dipole-dipole interaction and maybe a little bit of van der Waals interaction, which is very, very tiny at the level of 1 hertz or so, which prohibits you from, although you can do single qubit rotations, you cannot do controlled, 2 qubit gates without strong interaction between the atoms. But this problem can be solved by using what is called as Rydberg interaction between the atoms, meaning you first excite the electron of these atoms into very high n levels, like 50 to 100 or so. Then what happens is that the radius of the orbit of the electron increases so much, because that scales as n square, and then the electric dipole moment of the atom increases by many, many orders of magnitude. Thereby, you can create very strong interaction between the neighboring atoms. For instance, if you look at this graph here as a function of distance, for neutral atoms, the magnetic dipole-dipole interaction, which falls as 1 over r cube, is at 0.1 hertz level, and the van der Waals interaction is at the level of 10 to the power minus 5 hertz. But if you excite electrons to these large Rydberg orbits, then this interaction increases by about 12 orders of magnitude. This allows one to actually execute 2 qubit gates. For instance, if you look at this energy diagram of 2 atoms, where both atoms are in the ground state, as a function of distance, there is hardly any energy change between the atoms if they are in the ground state. But if you have one of the 2 atoms excited to the Rydberg state, then there is some energy E, which will be of order, which will be, not 12 orders of magnitude, because there is only one atom whose electron is excited in the Rydberg state. But if you excite both atoms into the Rydberg state, then there is a very strong interaction as the distance reduces, and this distance is within, like for example, several tens of micrometers. You start experiencing this interaction, and then that prohibits you from exciting both atoms to the Rydberg state. This is called a Rydberg blockade. Now you use this effect to actually execute a controlled NOT operation or controlled operation between the two qubits, a controlled Z gate, controlled phase gate. So there are two atoms. The ground 0 and 1 are the hyperfine levels of the ground state, and R is the Rydberg state. So if the control bit is in 0 and you do you give a pi pulse of excitation, and if your target bit is so when you try to give a pi pulse on this, there is no Rydberg in by the second atom. So if you give a 2 pi pulse Rydberg, take it to the Rydberg state and give a 2 pi pulse, basically take it up and bring it down, you pick up a phase of pi. Now, if you try to do the same thing when the control bit is in 1, like on the right side here, because of the Rydberg interaction, the energy level of the second atom shifts up. Thereby, when you do a 2 pi rotation on the second atom, there is no phase that is picked up. So this is a controlled phase gate. So this kind of phase gates you use to build a 2 qubit controlled operation. Now, even in this platform has been very, very successful. There are two companies which are in the forefront now, although there are a couple more companies which are coming. One of them is a French company, Pascal, which is actually founded by one of the Nobel laureates, Alain Aspect. And now they have actually reached about 1,000 qubits. There is a press release only in June that they can create an array of about more than 1,000 atoms in single shot. So this is their state of the art now. And parallelly, there has been tremendous progress in the US by this company called QERA, which was founded by Mikhail Lukin and Vladan Vuletic. So they have demonstrated about 48 logical qubits with more than 280 physical qubits, where the architecture is based upon basically you store atoms in a storage zone like this. You bring them into a zone where you basically pick these atoms with optical tweezers and bring them into an interaction zone where you create these gates, which entangling gates using the Rydberg excitations. And then you move them out into a zone where you read them out through with an EMCCD camera. And there are all kinds of protocols to do real-time Rabi flops and characterizing basically calibrating the system and executing a full digital digital gate circuit, etc. In addition to this digital computing, which is based upon executing a quantum circuit or consisting of a set of gates, you can also do an analog computation where you start a system with some initial state, and then by creating the right interactions through this, by pointing your Rydberg laser to certain atoms, you can basically create bonds or not create bonds between certain pairs of atoms. You can also and let the initial Hamiltonian evolve to a ground state. So the analog computation, that also can be done by using the optical qubit in this case. So this is about the neutral atoms based quantum computing. In addition to just using these atoms for quantum computing, as Professor Apoorva keeps saying, that quantum computers may not come so soon, they might take a long time, but what is very useful about this technology is that the first thing that would be most useful that comes out will be quantum sensors. And atoms form very good candidates for sensing applications. And when we say quantum sensing, not only for sensing but also for metrology applications, when we say quantum sensing, we are talking about utilizing the principles of quantum superpositions, entanglements, wave-particle duality, tunneling, etc. of fundamental particles, and in a way engineering them in a manner that they can be used for example sensing application or for building extremely precise clocks, for instance, for timekeeping applications. Now, some of these things are not possible with classical sensors. For example, one of the things that one can use also is like squeezing. If you use standard light for detection, you will immediately hit the short noise limit. And if you have to go beyond the short noise limit, I mean, if you can get rid of all the technical noises, but you will be limited by, say, short noise. Now, this you cannot easily go beyond that unless you do something called as squeezing, which is again an application of quantum technology. But I'm not going to get into that. I'll just give you a few examples of where these atomic systems can be used as sensors. So first is using the wave particle duality of atomic systems. You can actually build interferometers where you don't use light, but you use matter waves. And once you use matter waves, these matter waves based interferometers theoretically are about 10 to the power 11 times more sensitive. They are theoretically 10 to the power 11 times more sensitive because of the rest mass of the atoms being so much higher than rest mass of the photons. From there, the sensitivity actually gets enhanced. Now, that can be used for building Sagnac interferometers, which are very sensitive to rotations. So, one can build rotation sensors, inertial sensors. One can build acceleration sensors. One can, and since you can build acceleration sensors, you can also measure gravitational acceleration and build precise gravimeters and gravity gradiometers, which have huge applications for technological, in technology. Then you can build very precise magnetic field sensors, very sensitive magnetic field sensors, which are sensitive up to the level of femtoteslas per square root hertz kind of levels, which people have already built, and they are being tested for, say, measuring tiny magnetic fields created by the currents that are flowing in the neurons to create a magnetoencephalography image. Yeah. One can also use it for detecting very tiny electric fields, for example, microwaves, to make a very sensitive antenna for microwaves, and of course to keep time. So these are the different applications of these atoms-based quantum sensors. And here are some numbers. Sorry, I didn't put the source here. I picked up from my students' presentation. I forgot to quote the source here. Excuse me for that. So these are the different markets that each of these particular sensors are actually have a potential for. Say, for example, these gravity gradients and magnetic field sensors, they have a potential market exceeding 1 billion pounds. And here are some examples of devices which people have already brought into the field for testing. For instance, the quantum gravimeter, the gradiometer, gravity gradiometer, accelerometers, and the clocks which people have already built. So I'll give an example of what we have been doing in our group is basically building a gravitational acceleration sensor by using a sample of ultra cold atoms which are dropped under gravity, and then you build a Mach-Zehnder interferometer in the vertical direction. So you apply pulses of light, split the wave packets in the vertical direction, and do I have a picture of that? Yeah, so what you do is that you basically, with a wave packet, you build a Mach-Zehnder interferometer like that. So in case of matter waves, you use light as your beam splitting and beam combining elements. So you apply light grating pulses for the wave packet and split it into different momentum states. Like your grating splits light right into different momentum states, you apply light pulses and split them, and then again combine with the pulse like what you combine on a beam splitter, and then you look at what are the amplitudes that is either transmitted or reflected across the beam splitter. Now, if there is any change in the phase along these two directions of the wave packets, then you get a change in the population here. So, since atoms can be made sensitive to, they have mass, they have magnetic moments, they have electric quadrupole moments, etc. You can make them by proper choice of atoms. you can actually make an interferometer that is sensitive to a particular physical parameter. Now, in case of a gravity gradiometer, what you do is that you drop the atoms in the vertical direction across the you just drop them under gravity, and while they are falling, you split the wave packets with light pulses along the vertical direction, and then these wave packets travel different trajectories, and they pick up differential phases, which you actually measure and measure the local gravitational acceleration. Now you get a fringe pattern like that when you basically change the phase of the final pulse, and then you can actually sit at a position where you compensate for the gravity and you measure the gravitational acceleration. Now, we just did a technology demonstration in the lab, and we are at this particular decimal place in the value of G. As you can see here, every decimal place is sensitive to a certain reason, because if you change the latitude, the gravitational acceleration changes. If the moon goes around you, the local gravitational acceleration changes. And if the water table under the ground changes, then the local gravitational acceleration also changes. It also depends upon the density of rocks and whatnot. So people are using this gravitational acceleration sensor. Actually, you measure the gradient in the value of G by measuring the G at two different heights, and that is more sensitive to the mass distribution under the ground. So people are using that to build these gravity sensors. Now we have started, since we have done the technology demonstration, we have started designing and building a transportable version which has a sensitive up to the 8th or 9th decimal place in measuring the gravitational acceleration, which our plan is to do a gravity mapping and take it forward. Yeah, so this is the picture of the trajectory of the atoms when they fall under gravity, where as they fall under gravity, you apply these 3 pulses to build this Mach-Zehnder interferometer. And these pulses are basically coming from a standing wave of light, it's not a standing wave, it's actually a moving standing wave which keeps track of the changing Doppler shift of the atoms as they are falling under gravity. So you compensate for the changing phase that changes due to gravity by changing the phase of the optical lattice, and then you match after you compensate, you measure what is the phase change that's happening. Next one is the magnetic field sensors. Now, when we talk about magnetic field sensors, there are variety of things. So you get these sensors of the size of a cryostat to the size of a nanoparticle. Now, there are these magnetic field sensors, the size varies over a large, over many orders of magnitude. Now, when you look at, so this is basically a plot of what kind of sensitivities are offered by what kind of size sensors. So if you look at it, there are many different types of sensors. So there are squid-based sensors. As you know, once you use a superconducting device, it comes along with it all the additional paraphernalia of cryogenics, which makes the sensor head very big, although it's the most sensitive detector. Now, there are atomic vapor cell based detectors, which are the SERF detector and the atomic vapor cell, which is called here. These are a class of sensors which are basically built with atomic vapor in a glass cell. Then you have the nitrogen vacancy sensors, and then many other the classical sensors. Now, in this also, atomic systems actually excel. So when you talk about atomic systems, if you look at the size as well as the sensitivity put together, atomic systems excel in that also. Basically, what you do is that you do a spin polarization of the atomic vapor with lasers under a constant magnetic field, and then you see when an external field is applied, you see how the spin is going to precess along the external magnetic field. So that is what you measure, or you measure a change in the polarization. But the way you measure it is by measuring the change in the polarization of the light that goes through the vapor cell. Basically measure the dichroism. Okay, this is the NV center based sensor, which is not related to this topic, but These are also competing sensors because their sizes can be very small, although their sensitivity is not that great as the atomic sensors. Now, the electric field sensors, where the atomic systems can be used. Again, here one uses the most sensitive detector is based upon Rydberg atoms. So the way it is done is it's basically a electromagnetically induced transparency based sensor where you first what you do is that from the ground state you excite to very high Rydberg level, Rydberg state. For instance, this D5 half, 53 D5 half is one of the Rydberg states. And then what you do is that you do a pump probe kind of a spectroscopy by applying a very weak magnetic microwave field, which connects that upper Rydberg state to another neighboring Rydberg state, which is separated by few tens of gigahertz. For this example, it is about 14 gigahertz, where the N level is 54 and 53. Now, between these three lasers, now this, if you look at the transmission of this probe is a 780 nanometer light. And while you have this coupling laser on, if you come with a microwave radiation, it can be very weak because these atoms possess, the atomic dipole moment of these atoms is very large. They become very sensitive to this external electric fields. And then once you come with a very weak microwave field on this, which connects this neighboring transition, you see a dip in the transmission of this coupling laser. Or you can also monitor the probe laser coupling. And by looking at this dip, you can actually estimate what is how much of the microwave field is incident on this particular, in the vapor cell, which is used for sensing this electromagnetic fields, external electromagnetic field. You can also make a DC sensor. So if once you excite the Rydberg, once you excite this atom to the Rydberg state, these states are easily ionizable by applying very weak external electric field. So wherever you do the experiments with Rydberg atoms, you have to be very careful to nullify all background electric fields, etc. Otherwise, these atoms immediately get ionized, and that's it. Okay. So now about timing devices or clocks. So there are two types of clocks which people usually need for many applications. One is a set of clocks which actually sit on your devices in your systems where you need a reference clock. And one type of clock is a clock which sits in a laboratory and which is used as a master clock, which steers all the small clocks, maybe sitting on satellites, or which are clocks or oscillators that are sitting in communication systems like in your networking systems, etc. There are clocks also. Most of the times these clocks are crystal oscillator, either oven stabilized crystal oscillators or something. But when you are on a satellite, you need better than a crystal oscillator. So there you have clocks which are in the range of, whose fractional instability is in the range of 10 to the power minus 13 over many days. So these atomic beam clocks and vapor cell clocks are used. And the ground-based clocks, which are currently based upon the cesium fountain clock, which oscillates at 9.2 gigahertz approximately, that has a fractional instability. The best one so far is at about 10 to the power minus 16. People are trying to push this using optical frequency standards. Now this is what is good. These clocks, a network of these clocks across many countries is used to steer the clocks on satellites and keep them in synchronization with each other. Now the modern clock, this fountain clock is again based upon interrogating the ground's hyperfine splitting in cesium atom, which is at 9.2 gigahertz, using a Ramsey separated oscillatory fields technique. Now I can tell you the details of that if you are interested. Essentially what you do is that you create a sample of cold atoms here within a magneto-optic trap, and you prepare these atoms in one of the ground state with a microwave excitation, and then you launch these atoms in the vertical direction where you have a interrogating cavity here, which does a transition from the lower ground state to the upper ground state of the upper hyperfine ground state, basically a pi by 2 pulse. The atoms go up, they again come back, and there is a second pi by 2 pulse. So it's a spin echo kind of a setup. And if your microwave cavity is exactly on resonance with the hyperfine transition, then there is a complete population transfer. That is detected with a probe laser here. So this is the basic principle of working of this. Now, if you can, as you see, this is only 9.2 gigahertz and the line width is maybe below 1 hertz or so. Now, the kind of quality factor that you get is limited to 10 to the power 10 to 11 of this particular oscillation, of this transition. Now, imagine instead if you had used an optical transition, if you choose an atom where the excited state optical transition has a line width in the range of few seconds to many seconds, and there exist such atoms like cesium atom, ytterbium ion. There are certain transitions in these which have extremely long lifetimes, which can be used as an optical clock. Now, if you look at the frequency of optical transition, it's in the range of 10 to the power 15 hertz. And if the line width is, say, less than a hertz, even if it's 1 hertz, then the quality factor of the transition is 10 to the power 15 to 16. So you get extremely narrow. Your clock becomes extremely, the short-term stability becomes extremely large. And then by getting rid of a lot of systematic effects which actually make this clock transition drift, you can actually make a very precise clock. And the way it is done, the way the entire clock system works is that you have a laser, and this is the technology which is quite advanced, where your line width of the laser is reduced below 1 hertz, which is in itself is a big engineering challenge. And that you use to interrogate a transition which is of the same order, whose line width is of the same order, 1 hertz or so. And then what you do is that you stabilize the laser frequency to the atomic transition. And once you stabilize it, now you need a way to measure the frequency of this light, okay, which is in 10 to the power 15 hertz, which cannot be done with electronics, but it can be done by what are called as optical frequency combs. Using that, people measure the frequency of this laser and then down convert it into radio frequency range and use it as a clock. Now, this is the fractional instability of the evolution of all the clocks that we have so far. So the atomic era began somewhere here, and now the best ones are the strontium one and the ytterbium one, which are at the strontium one is at about 2 times 10 to the power minus 18 level, and the ytterbium ion transition is at about 10 to the power minus 18 level. And these are long-term stabilities. Short-term stability, people have even achieved at the level of 10 to the power minus 21. Using this, they even measured gravitational redshift of photons by using this atoms, separating the atoms by only a few millimeters. So they could measure the gravitational redshift just over a few millimeters height difference. So that has been done. So in summary, atoms and ions are very pure systems which can be controlled very precisely using the current technologies. You can get levels which have very large coherence times, and if you are wanting to use them for quantum computing, they are very promising for scalability. People are already scaling it up to several thousand qubits, and atomic systems / ionic systems are very versatile. They can be used to build many different things for practical applications. Thank you.
Thank you. Really fascinating. Any questions from the audience?
Thanks for the nice survey. In your work about the gravimeter, you have shown all these decimal places and said here. So, and the target is several more.
We meaning us when we demonstrated,
Yeah, you guys, yeah. So what is it going to take, like in terms of going to the several more places?
No, so it's only engineering, because the system on which we demonstrated this is not designed for doing very precise Raman excitations, because you need to have extremely well phase stabilized lasers, etc., which was not the case in our system. So even
predominantly better quality hardware.
Yeah, better quality hardware. So that is what we are building now, because it needs new hardware which we need to procure and all that. So That is under progress now. This is what with whatever we had, or with a system which is not designed for this application. Yeah.
But those high-end lasers can also eventually be portable.
Yeah, they are all fiber lasers which sit in racks. Unlike the lasers, our lasers are big lasers which sit on optical tables. Those are fiber lasers sitting in racks, and they are much more stable. Yeah.
Any other questions? I have a question. So, in superconducting qubits, we see that over the last 2 decades, we have seen significant, several orders of magnitude improvement in the coherences. What's the scope of such engineering to scale? Is there any effort going on to, or is that not a limitation right now?
That is not a limitation right now, because hyperfine qubits, the coherence time is as much as you want. I mean, that in terms of how many operations you can do within that time.
So the limitation, what limits the coherence is just the coupling to the.
Yeah, coupling the as you increase the number of qubits, the number of operations that you do, that kind of, as it increases, and as the scale of the system increases, the imperfections in environmental factors that affects. So that kind of kills the coherence of a multiple. If you entangle many qubits, that will kill it. But if you use clever architectures like shuttling the ions to zones where you only make them interact, ions or atoms to zones where you only make them interact with the particular atom of your interest, then that also kind of does not limit. Yeah.
Not, let's thank the speaker again.
Thank you.
With that, we now break for tea. So it's at 11:30. So we are running about 20-25 minutes late. We'll resume at 11:45. Continue with me. Thank you.
Okay. Thank you.
At some point मैं ही कैसे आ गया कोई तो आना चाहिए Yeah, sir. Okay. नहीं, वो transfer.
we now have Professor P.S. Mahesh from IISER Pune, who will be talking to us about NMR and NV center qubits and their applications. So, Professor Mahesh received his PhD from the Department of Physics here in ISC Bangalore, and he then went on to do a postdoctoral fellowship at Massachusetts, MIT, and University of Dortmund, Germany. His research interests are in magnetic resonance and quantum information processing. He was awarded with the MIT Cambridge Fellowship in 2003, Humboldt Fellowship in 2005, and the DST Swarna Jayanti Fellowship in 2014. So I invite Professor Mahesh to deliver his talk.
Okay. All right. Good morning, everyone, and thank you very much, Baladitya, and thank you very much, Professor Apoorva Patel. I'll say a little bit more at the end. So my talk is so where is the pointer? Okay, let me use. Yeah. Okay. So my talk is more about some status and prospects. It's not really about our research. I'll just take a overlook on spin qubits, about NMR qubits and NV center qubits. So these are the various groups I'll mention at the end again. So for students here, those who are not very much aware of these qubits, that just a one slide summary. So what we do is we take diamagnetic samples. Okay, so that means there are no electronic magnetic moments, and we place them in very strong magnetic field. So this orange sample, that's the sample, and that's in very strong magnetic field. How strong? It's about 10 to 20 Tesla. So that's a really strong magnetic field. And then so we have molecules in the sample, and inside the molecules we have atoms, and inside the atoms we have nuclei. And so consider this nucleus. So nucleus is magnetic. Okay, so it can have magnetic moment, and that magnetic moment of the nucleus interacts with the magnetic field, and that's how we have different levels depending on the state of the magnetic moment inside the magnetic field. So so we have depending on the spin number, we have various levels. So we have spin quantum numbers. According to the spin quantum numbers, we have various levels. If you take spin half particle like hydrogen nucleus is proton is spin half. So if you take spin half nucleus, just water or chloroform in this picture, so that's proton, that's hydrogen nucleus. And inside the magnetic field, so we have two levels, so corresponding to plus half and minus half states. So these are the magnetic quantum numbers of proton. And there is an energy gap, and that is the Zeeman energy gap. And this interaction between the magnetic moment and the magnetic field is the Zeeman interaction. And now this energy gap happens to be in the range of radio waves. Okay, the energy gap matches with the radio waves. So that's why if we irradiate the sample with radio waves, then there is a resonant absorption, and that resonant dynamics can be very precisely controlled. Okay, so we can create all kinds of superposition very precisely. Now we can label this ground state as 0 and excited state as 1. So that's our bit. Okay, so that's the qubit. So it is the nuclear spin qubit. Okay, inside the magnetic field, and that is precisely controlled by radio wave. So we can implement all kinds of quantum gates, and that can be treated as a qubit. And there are some advantages because the control is very good, so we can get fidelities of the order of 0.9999. So that's the fidelity which has been experimentally demonstrated. And the coherence times can be long, it can be seconds, sometimes minutes, and even longer. So those are the advantages, and there are some disadvantages. I'll point out that later. So that's the summary of the nuclear spin qubit. And now, so it all started in about 1997 when David Corey came up with this idea of using nuclear magnetic resonance. Simultaneously, there was another group by Nielsen and Chong. So they almost simultaneously proposed this as a quantum memory. Now, since then, there was a tremendous progress. So there was increased larger and larger registers and so on. For example, in about 6 years ago, then there were 12 qubits. These were universally controllable 12 qubits. And but then we can give up that universal control because that becomes harder and harder as you increase the register size. So then you can say that okay, we can do certain tasks, not all tasks. So if you don't have universal control, then we can go further. So we can go to 18 qubits, 38 qubits, and so currently we are working on 50 plus qubits and so on. Okay, so that is the register size, but that is one aspect. Here we are using one type of systems. I'll show you another type now. Before that, there is simultaneously work going on to increase the coherence time. So that is longer and longer memories. So there are special type of states called long-lived states, and we can also use so they're kind of decoherence-free subspaces. So we can use them to keep the qubit memory for longer time. Now, so last few years there is attention to another type of systems. So in the earlier cases, I was showing molecules, smaller molecules, 18 qubits and so on. Those were liquids. Sample was in liquid state. But now what if we take a crystal, single crystal? Now if we take a single crystal, so you can have Avogadro number of spins. Okay. Now the problem is controllability. So you can't control individually, okay, these spins, but there is a global control. So they are globally addressable qubits. Now can you do something about with such kind of qubits? So there were many works. For example, in this work, they showed that decoherence in large quantum registers, it scales only sub-quadratically. It is actually the power coefficient is about 0.4 with respect to number of correlated spins, and you can see that they have correlated up to about 5,000 spins. Okay, so quantum correlated 5,000 spins in single crystal in NMR. So that is possible. It is kind of D-wave approach. So you put lot of qubits and see what you can do. Okay, you don't have individual control. You can do some kind of annealing and some kind of quantum simulations. And then what are the simulations you can do? So that is the architecture. Now it is getting increasingly interesting because now quantum control techniques have become more and more powerful. So it is possible to manipulate Hamiltonians. It is possible to engineer the Hamiltonians. So we can do some kind of many types of quantum simulations with a large number of qubits. Now this is where another development has happened recently. It's called reservoir quantum computing. So it's a hybrid quantum computer. So where certain tasks are done in the quantum computer and there is a peripheral classical computing available. So it is like you have a machine learning circuit where machine learning has nodes and weights and connections and all those things, and it has some input and output. Now here the major part of these nodes and connections, they are replaced by quantum. Okay, so quantum kernel. So it's called kernel, and that is now we are. So there are the community is realizing this can be, the kernel can be replaced by a crystal. nuclear spin crystal. So where we can do solid state NMR and involve a large number of qubits, so of the order of hundreds of qubits, and still do something very interesting, which is the work that is going on. One early example is this. So this is 2021 work by a Japanese group. They have shown that we can do regression with solid state NMR with single crystal method that I showed. So they have also shown that it can recognize patterns, it can do classifying things. It's a quantum classifier and so on. So this is interesting because now we have crossed that barrier of 30 qubits, 50 qubits and so on. Now we are working with 100 plus qubits. Okay, and in fact, people have shown that up to 1000 or even 5000 spins can be quantum correlated. So that is very interesting because now we can explore or exploit a large Hilbert space of thousands of qubits. And now the challenge. Okay, the challenge remains. The challenge is qubit purity. Okay, so as Umakant said, in atoms they get highly pure quantum states. But in the case of NMR, NMR has energy gap which is tiny. So that is of the order of micro electron volt, whereas in the case of atoms you have electron volt. So because the energy gap is very small, the quantum purity is also small because we work in the thermal room temperature, and room temperature energy is like milli electron volt, whereas energy gap here is micro electron volt. So obviously there is a high thermal noise. Now one can also go to electron spins. We can take help of electron spins. That slightly improves situation because electrons have a larger gyromagnetic ratio, so energy gap is much larger. But then still that is not enough. So still the purity is not enough. But what one can do is the following. It is called hyperpolarization. So what one can do is you take help of atomic transitions, so which lead to pure quantum states, and transfer that polarization to electron spins or nuclear spins. Okay, so that's the hyperpolarization. So you are exploiting the polarization which is already there in the large energy levels of atomic transitions and transfer the polarization. Okay. So that is a very exciting thing. Here also in IISc, Dr. Sheetal Jain is working on this things. So it's also called dynamical nuclear polarization, where you can transfer polarization from either atomic transitions or electronic transitions and then go to the nuclear spin manipulation. So that is one way to realize pure quantum states in the nucleus or in the electrons. Now that is exactly what is done in this system. It is called nitrogen vacancy centers in diamond. So what happens is here you have an atomic transition which is excited by a laser. So this is the green laser which excites the atomic transition. Now in the ground state, so that the levels in the ground state are split by the spin quantum number. Okay. Now if you take ground state alone, there is no good polarization because again the energy gap is too less. It is of the order of milli electron volt or less, and in fact it is of the order of hundreds of micro electron volt. So that is not enough. So you take help of this atomic transition, green light, green laser. If you shine green laser, then there is a preferential population of the ground state. Okay, so there is a excitation, but when they de-excite, it preferentially occupies the spin zero state. Okay, so that is the interesting part. Now, if you just shine green laser, so there is a spin polarization. Okay, so that is the strength of the nitrogen vacancy center. So just by shining green light, you get pure quantum states, and so you get optically induced spin polarization, and also an additional benefit is it also gives spin state dependent fluorescence. Okay, because ms equal to 0 state considerably fluoresces higher than ms equal to plus or minus 1 state. So just by looking at the fluorescence, you know whether it is in ms equal to 0 state or ms equal to plus or minus 1 state. So spin state can be detected via optical means. So So that's the nitrogen vacancy center, and now using that nitrogen vacancy center, now you have quantum pure quantum state. How far you can go? So this work is now 5 years old. It's about so they have shown 10 qubit solid state register in NV center. So one thing nice about this NV center is whole thing works in room temperature. In principle, you don't need any vacuum or cryogenics or anything. Even at high temperature, it can work. And it is portable. Now NV centers have been put on chip, and so it can be integrated with other fabrications and so on. Some of my students are in Europe now in different companies, and they say that they are working on 30 qubits NV centers. So I don't have any published work on that, but they are working on larger number of qubits now. So hopefully we will get 30, maybe 50 qubits by NV centers. And one of the issues with the NV center is engineering the defects, because we need nitrogen and vacancy side by side in the diamond crystal. And if you want to go more than 10 qubits, now you need another such set of 10 qubits. Okay, so these are the nitrogen vacancy center, green and purple, and orange ones are the surrounding nuclear spins. So you need another set now, which is close to that, and then you can couple those two by hyperfine interaction and dipole-dipole interaction and so on. So that engineering these defects very precisely inside the diamond is one challenge. So that industry is working on. Now, as Umakant said, it is not just the quantum computing, it's also quantum sensing. Sensors, metrology, magnetometry, all these things are very interesting. And so NV center Hamiltonian is sensitive to magnetic field as well as electric fields. So it can be used for very precisely sensing all these physical fields, and also stress and strain. The zero field splitting ZFS is also sensitive to stress. Okay, so it can detect all even temperature. So it can detect temperature also, and whole thing can be miniaturized, and it works at room temperature, and you don't need vacuum and so on. Okay, so that's the advantage. So the setup is very portable and it is on chip. And it can be integrated with the AFM. In this case, it is used for scanning the surface of a thin film, and that's the image. So that's from this reference. So you can scan the surface of a film. Now, okay, so now various groups are working on it, on these architectures. For example, in IIT Roper, there is a group by Rajesh Nair who is working on nano diamonds and spectroscopy, NV center spectroscopy and so on. Kavita Dorai has a very nice big group on nuclear magnetic resonance quantum computing. In PRL Ahmedabad, Professor R.P. Singh is there, and also one person, Tanmay Chakraborty, has joined, who is an expert in NV centers. They are going to work with ISRO for quantum communications. And IISER Bhopal has Parveen Kumar, who works on NV center based sensing. And IISER Kolkata, Chiranjeev Mitra works on coupling different NV centers via optical fibers. And there is Rangit Bhattacharya, who is working on nuclear magnetic resonance registers. IIT Mumbai has a very big group on NV centers led by Kasturi Saha. And so IISER Pune, we work on nuclear magnetic resonance, and we also have a NV center setup. And in IIT Madras, Praveen Bhallamudi has group on working on NV center quantum qubits as well as NV center based other technologies like masers and so on. So these are some examples. So I might have excluded many other groups. So this is just it is not an exhaustive list. So there are many other groups. Now, just to summarize. So as I said, there are issues. So one is the state purity, and there are quantum superposition and non-local gates, and now what is the quantum resource. So classical registers, we all use classical computers even today, so they are having very good state purity, right? So 0 is 0 and 1 is 1 all the time, and quantum superposition is missing, of course, and non-local gates are being applied all the time. Whereas in NMR register, state purity is the issue, so it's very low purity. Quantum superposition is there, and non-local gates are very precise. Now question is, what is the quantum resource? So quantum resource is the discard, quantum discard. And in NV center, on the other hand, because of the hyperpolarization, we polarize using lasers, we get very good state purity, and it allows quantum superposition and non-local gates, and so the resource can be entanglement. Now, so here I want to point out one work. So this was actually guided by Professor Apoorva Patel, and so what we wanted to know, ask was the same question: what is the resource in NMR quantum register? What is the quantum resource? So that was the question in this paper, and Professor Apoorva Patel, I met in a conference, and I asked him to explain me what is quantum discard, and he explained me very nicely. I still remember his words. He said that it is the distance between a given quantum state and the nearest separable state. So that's the in simplest terms. Of course, there are technical details. So and from then onwards, so we collaborated on this, and we tried to see the evolution of quantum discard on NMR systems. And so that was very nice, and it was very educative for me. So that's about some summary I wanted to say, and I wanted to say a few things about Professor Apoorva Patel, given this is a special occasion. So I joined IISc in 1997, and in 1998 or 1999, I believe Professor Apoorva Patel started the first course on quantum computing. Can you correct me? 1999? 1998, yes. So 1998. So that was the first course on quantum information processing, and at that time, Nielsen and Chuang book has not arrived yet, right? So you taught from Preskill's lecture notes and other sources, and it was fantastic. So we were auditing because I had already finished coursework, and so but we were as much as a student as any other crediting student. I think as someone pointed out, the classes were in the afternoon, so we were very regularly attending all the classes. One thing I can say that the classes were so thorough. When he writes something on the board, he never used to erase it, because it was so thorough. When he writes an equation, it is done with all the care and all the attention, and so that was the okay. So that summarizes how thorough he was in his classes, in his teaching. He was very dedicated, as many of the speakers pointed out. The other thing was, it was also very exciting that he used to, that was the time when there was a boom of quantum information, because there were suddenly there were big books started coming up, and there were big popular discoveries were being made. So Shor's algorithm had just come, and Grover's algorithm came in 1997, so on. And that's the time Professor Apoorva Patel gave a very nice lecture. So that seminar, that was in SCRC, in the Superconducting Research Center. So that lecture was about quantum computing in our body, so in life. Okay, so that's the time when he first discussed about possibility of quantum computing happening at the level of DNAs. And so using Grover's algorithm, he proved that the optimal number of DNA base pairs is 4. So that's interesting. That's not the end of it. And then he took one more step and he showed that optimum number of proteins, or sorry, amino acids must be 20. That's even more interesting, right? So all these things followed from Grover's algorithm. And so that was amazing. So it was very exciting for us, and in fact that motivated a lot of us to get into this field and work on it. And thank you very much, sir. And I remember he was like Drona in Mahabharat, right? You may be working in any field, but you always worship and love Drona. Okay, thank you.
So, there is a quick question on if I forgot.
Yes. So Mahesh, I can solve for it. For the engineering of the vacancies in Jammu, what kind of preciseness that is required? Is it the separation
Yeah,
of the
yeah.
vacancies or?
Yeah. So one demonstration that German group, Ratstrup's group, they have shown is that NV dipole coupling for 10 angstrom distance is about manageable, about I think 50 megahertz or something. That was, and using that they showed entanglement between NV in the same crystal. Okay. And now, so the challenge is to put them in a very systematic lattice. So that is, there are works claiming that they have done, but there is no clear demonstration of quantum control in such things. So that is one thing, and also there is also question of orientation. NV axis should be oriented in a known manner, in a systematic manner. That is another thing. So these are the challenges. So I think there is one group in IIT Madras that Professor Ballamudi. So they are working on growing also. Yeah.
Yeah, Mahesh, regarding the NMR systems where you're now talking about people using large number of qubits. So if I understood right, you identify these qubits as different transitions in a given NMR molecule, right? So when you're talking about these hundreds or thousands of qubits, is it still the same or is it slightly different?
It is so it is different. So now what we do is the following, that you can you can analyze the magnetization in terms of different magnetic so multiple quantum coherences. Okay, coherence order. Okay, so coherence order is like what you use in sensing. If you apply phase phi, how much it rotates. Okay, if it is single quantum, it rotates by it gets e power I5. If it is two quantum, it gets e power 2 I5. Okay, so now you can see what is the coherence order. Okay, so now from that coherence order, you can estimate what is the size of the spins participating in that. So that's the paper that I showed. And from using that coherence order, they got about 20 coherence order, and they could do regression, machine learning tasks. Okay, so such kind of thing, and these can be done very nicely in the routine NMR spectrometer. It can be done.
So you just have some large Hilbert space.
Yes.
You look at some properties and say, okay, this looks effectively like a 20 qubit system.
Well, so you can't explain classically. First of all, so multiple quantum coherences are purely. It's not like a classical magnetization.
No, that's not what I meant. I'm saying that you have this large system.
And you have some control. You have some control. You can selectively get filter out desired quantum coherence. Suppose you want 20 quantum coherence, you can filter out. There are methods that you can filter out and analyze that separately. You can do in that sense. You can do tomography of the quantum coherence. Okay. So it's not a full state tomography. It is coherence number selective tomography. So it is like you are addressing certain parts of the density matrix. You can quantify.
In this quantum computing example using NV, you said at a distance of some angstrom,
10
angstrom the splitting was?
50 megahertz, if I remember. Yeah.
So your
Dipole.
So you get sidebands on your transition.
Correct.
So that you
Yeah.
can address.
Yeah.
I was just thinking how a C0 gate.
Yeah, sidebands you get and then address that. Yeah.
How do you measure quantum restore in NMR system?
So the method that we used was using state tomography. You first do state tomography, yes. Yeah. But now after that there were other methods. You can now use an ancilla and directly get the discard. So you have to do some post processing, but you can avoid tomography. Yeah.
But you still measure the distance.
You measure discard directly. You measure certain expectation values and then calculate the discard. Yeah. So it is not full state tomography, but it is more efficient than full state tomography. But you have to do multiple measurements for multiple expectation values. Yes.
In the interest of time, we'll any further questions we can take over lunch. Thank you, Professor Mahesh. So next up. So next we have Professor Vijayaraghavan from TIFR Mumbai. Vijay is a very well-known face of quantum computing with superconducting qubits in India. He needs no introduction to most of his audience, but I will as a formality introduce him. So Vijay received his bachelor's in physics from St. Stephen's College, Delhi University, and did a PhD in Yale University, where he developed a new measurement technique for superconducting quantum bits using bifurcation amplifiers. And then he went on to do a postdoctoral fellowship in the University of California.
I was streaming.
Where he worked on several path-breaking experiments using these resistant amplifiers operating at the quantum limit. And since after his postdoc, he moved to TIFR Mumbai, where he has been leading the group on quantum measurement and control, where they have designed new versions of superconducting qubits and have been pioneering the scalable quantum architectures in the Indian field. Over to you.
Thank you. Thanks a lot, Bala. Thank you for putting this together. It's really happy to be here. I have had the opportunity to interact a lot with Apoorva in the last 10, 11 years. I've been here back in India, and I'll say more about that a little bit later. I'm going to try and tell you sort of briefly about what this field of superconducting qubit quantum computing is very quickly, and then say about what are the current sort of the state of affairs in India in terms of the different labs, what are the capabilities. And then I'll end by just showing a snapshot of what we are thinking under the National Quantum Mission. And then we can discuss about some of the challenges and other things, which anyway I think I'll probably defer to the panel discussion after lunch. So let me move on. So very simply, a quantum processor is just a network of physical qubits. You can arrange them in different ways. It can be linear array. It could be something like this. You need the ability to control each of these qubits locally. I mean, there are other models as well, as you heard in the previous talk. You also need to be able to create entanglement between at least pairs of qubits. Nearest neighbor is sufficient, but extended connectivity is useful, which means that if you can entangle qubits which are far away in the network. This is, for example, a layout of a 127 processor from IBM, which is a careful choice they have made, balancing various kinds of errors and performance. And then you need to be able to make local measurements so that you can measure the state of each of the qubit. The two main challenges for building something like this is, of course, the fact that these qubits are not stable, so they decohere. And then in order to do anything really useful and practical with quantum computers, you need to build a system with sufficiently large number of qubits. A 5-qubit quantum computer is, a real 5-qubit quantum computer is worse than running it on a laptop. Okay, so don't buy a 5-qubit quantum computer if you're actually trying to use it for something. If you're trying to learn stuff, yes. And it's basically the idea that the size of the Hilbert space needs to become big enough that it cannot be efficiently represented in any classical computer. And once you cross that limit, then you sort of enter the regime of things where you can't even verify things so easily, but people are working on that. Okay, so the superconducting qubit is actually a very simple device. You can think of this as a nonlinear oscillator. It consists of a Josephson tunnel junction, which behaves like an inductor shunted with a capacitor, but because it's a Josephson junction, it's nonlinear, and you have a cosine potential instead of a harmonic oscillator potential, which means the levels are unequally spaced, and you can isolate the two lowest levels to make a qubit. These are typically in the gigahertz range with sort of an effective temperature of 250 millikelvin. So you have to operate at 10 millikelvin in order for thermal energy to thermal noise to not affect your state. If you Mahesh had mentioned this as a problem for purity in NMR. So here we try to do this by going to very low temperatures. The low temperatures are also required because these are superconducting materials. And here the sort of a simple answer is that the superconductivity allows you to have dissipation-free electronic components. And decoherence here can simply be understood as, if you set an oscillator in motion, it stops after some point of time, right? Due to friction, due to dissipation, we don't want it. We would like to live as long as possible. So you try to minimize all the sources of losses. After having single qubits, you also need to be able to create interactions. These are electrical systems. You can just connect them with a capacitor, and that gives you sort of a coupled pendulum-like model if you want to think about it like that. And this is how you create entanglement between pairs of qubits. You can do this by putting them next to each other, or you can also do this by connecting them with a microwave resonator. So this middle thing here called the bus cavity allows you to keep the qubits sort of far apart from each other, so that it's more practical when you try to create a network of qubits. So imagine just connecting everything with capacitors, which are basically done by keeping things close to each other. You can have a fixed coupling structure like this, or you can have something more complicated, which also uses Josephson junctions and magnetic fields to control the coupling so that you can turn it on and off. And these are two popular choices people make for building these processors. So once you have this, you can start putting them together. So here's sort of some evolution from way back, a 9-qubit linear array from the UCSB group, which eventually became Google. Here is a 16-qubit processor from IBM. Here is the 54-qubit Google's Sycamore chip. And now you can see multi-layer chips from IBM's 421-qubit processor. To summarize this, the basic block, the qubit is reasonably well understood. It's not perfect yet, but improvements are being made steadily over the last decade or so. In order to scale to build these large systems, you need a lot of resources. You need fabrication, you need electronics, you need engineering, you need time. And these are the problems you have to essentially tackle to put this thing together. I'm mentioning this because these big companies around the world have been doing this for quite some time. We are just about to start doing this. We have not yet started working at scale to be able to start attacking these problems the way they have to be attacked. Okay, so quickly to summarize the state of the art, this is the largest superconducting processor till date. It was recently announced, more than 1,000 qubits. It uses the fixed coupler technology. One of the big breakthroughs was that they developed this very high density cryogenic wiring. So they claim that there's over 1 mile of wiring inside a dilution refrigerator. They also released a smaller version, but this one has much lower error and uses the tunable coupler technology, and the performance they claim is about 5 times better than their previous generation. There are, of course, other companies. You have heard about Google's Sycamore chip. Rigetti also has announced an 84-qubit processor, and very recently I saw an announcement from China with a 504-qubit processor just a few months back. And the nice things is that these are real systems. There are many of them around the world, and many of these systems are actually available on the cloud also for free. Recently, I found out that IBM got rid of all their low qubit count processors, and the minimum one is 100 qubits. And I was at an event where the vice president of IBM was giving a talk here in Bangalore just recently. And in his words, if you're not above 100 qubits, you're not doing anything quantum. So apparently that was the reason why they took down all the smaller processes and wanted people to focus on getting things working at the large qubit number, which has its own challenges. Okay, so what does it take to design a good superconducting processor? One very simple idea here is that you actually only have three building blocks for this qubit. You have the Josephson tunnel junction, you have a capacitor, you have an inductor. So it's an electronic circuit, and depending on what circuit you make out of these three objects, you can get a different Hamiltonian, a different level structure. And that you can design to tailor your system to your requirements. So it could mean decoupling from certain source of noises. It could mean making the measurement faster or easier. So it's really quite nice in that sense, even though natural systems like atoms and ions are sort of perfect and given by nature. Here you can actually play and do something. So it's both a pro and a con. Because you're making them, it's difficult to make them identical, but you have the flexibility to change things around. So you have to work about the qubit design. The most common qubit is the transmon qubit, which is the anharmonic oscillator. There are several other designs which have evolved in many, many years. It sort of depends on different circuits here. And this new qubit called the fluxonium is also emerging quite rapidly as potentially an alternative to this transmon qubits, though large-scale processes with fluxonium don't exist as of now. So then you have to worry about how to lay these out in a chip. You have to worry about crosstalk. You have to worry about spurious modes. You have to think about the material choices. Here is some images from looking at the surface of niobium versus tantalum, and it turns out that the oxide of tantalum has less loss compared to the oxide of niobium, and this results in a huge improvement in the coherence because these losses absorb microwaves and bring your oscillator back to its ground state. So compatible with making a large-scale processor out of that. You also have to worry about filtering and shielding these systems, and these are extremely sensitive to stray radiation because that radiation can destroy superconductivity and create quasi-particles, which also can kill your coherence. And then finally, you have to really think about all the classical control electronics, because at the end of the day, the operation of a quantum computer using superconducting qubits is similar to a radar system or even a cell phone. A lot of microwave pulses going in and out, and you have to be able to create them, analyze them, and then do feedback. So, and then doing this at the level of thousands or hundred thousands of qubits requires a cheap and scalable way to make control and measurement electronics as well. So, sort of this is a simplistic picture of what it takes, but these are sort of the key ideas here. So now I will move on to what's going on in India. I'll start with Vibhor Singh at IISc Bangalore. They have been sort of focusing on both the quantum hardware and the classical hardware. And recently they have been working on a new type of qubit, which is sort of gaining traction around the world, called the dual rail qubit. And they have invented a new type of gate, which is sort of inspired from this stirrup techniques, and also doing multiplexed readout of multiple qubits, along with developing these classical hardware for controlling, and also using machine learning techniques to improve measurements. So I'll quickly go over some of these things. So this is actually two transmon-like qubits placed very close to each other. So they actually hybridize, and they create an effective Hilbert space, which looks like this. So here you have, this is the Hilbert space of these two qubits. You have the conventional 0, 0, 0, 1, 1, 0, and then all these higher levels. The idea of this dual rail qubit is to use this 0, 1, and 1, 0 as your basis states. It seems very strange, but you can also see that it's very difficult for this state to go to that state. So this is sort of a very simple idea that the decoherence here in that between those two levels is essentially non-existent, or can be very, very large. The coherence time can be very large because there's no direct path to it. But these states can decay to the ground state. But this is now treated as a different, it's called an erasure error, because your qubit has left your computational subspace, and it turns out that there are techniques to detect that and correct it, and it allows this formation of dark space. And they're using this some stirrup-based inspired gates, which has allowed them to create gates with very high fidelity, which are also very insensitive to the deviations in the controls. So this is finite resolution and finite noise, and you need your system to be robust to some deviations, and they have shown some results on that, and this is some work in progress. They've also been working on creating these RF SoC based control electronics in collaboration with Chetan Singh Thakur, also from IISc. So they have actually used this control electronics and also used the onboard FPGA to do some very interesting neural network based processing, which allows them to discriminate 5 qubits in a single line using this idea of frequency domain multiplexing in a very, very short amount of time. I think they're claiming something of the order of 50 nanoseconds, which probably is some kind of a record. I need to understand more about this. I've just only heard it very recently. So these kind of techniques are also going to be very important as we scale up. Vibhor is also working on improving the coherence of qubits. I'll show some data from our lab later on, which some of it was done together with Vibhor as well. Moving on to Bala Suri, who is also at IISc Bangalore. He's been working on developing a 2-qubit device with a coupler and a tunable qubit. And this has a fixed qubit coupled to a tunable qubit. So one of them is fixed frequency, the other one can be tuned. It has direct capacitive coupling using these lambda by 4 inductively coupled resonators. They have used this IBM's package called Qiskit Metal, which now allows you to design these things so that you can test all these things before you go to the fabrication. And they have done some preliminary experiments to look at this cross-resonance interaction, which is actually what gives you the ability to do entangled gates. Basically, these qubits are kept off resonance, and then you drive one qubit at the frequency of the other, and that creates an effective interaction which can be used. And that can be seen here from varying oscillation frequency, depending on whether one qubit is in the ground or the excited state. They've also been working on these amplifier systems called the Josephson parametric converter, which has 4 Josephson junctions in a loop. And using this, they have demonstrated gain shown here around 4.3 gigahertz. And the signal and idler mode, which is created in these parametric processes, actually are highly entangled. And they've also analyzed the entanglement of these by looking at the correlation of the output from the signal and idler modes. And they're working on using this kind of entangled light for other applications apart from these being used in superconducting qubit systems as the first stage pre-amplification for measurement. Okay. Now I'll move on to our group's work here. We have been doing a whole bunch of things. One of the things we did some years back was using this flexibility that we can put these junctions and capacitors together in different ways. We made an interesting 3-qubit circuit. So it's a single device, but it manifests itself as 3 qubits, sort of similar to an NMR system, so you can actually think of this as an experiment on a single NMR molecule as opposed to an ensemble system. But the couplings are very strong, so you can access all these sidebands and can do these native 3-qubit gates. And we demonstrated that certain algorithms can be executed in a much smaller number of steps with low error if you use these kind of ideas. We've also been working on improving the performance of these amplifiers. So we came up with a very simple microwave engineering technique, which allowed us to sort of boost the bandwidth of the same device by a factor of 3 up to 10. And we also demonstrated multiplex readout of multiple qubits using this large bandwidth. There are ongoing projects of improving these things further also in our lab. This is some recent work which we're still about wrapping up, where again we have changed the design of the qubit to give it some special properties. So for example, it is because of the orthogonal nature and how it couples to the environment, it's actually naturally protected from dissipation into the environment. It also allows us a way to improve the measurement, and we're trying to push it in such a way that we don't need the pre-amplifier stage, and we can get sufficient measurement signal from the qubit itself. And then finally, this ring resonator based coupler is a technique to connect non-nearest neighbor qubits by placing them along a circular transmission line. And in this 12 qubit sort of idea or system, we sort of showed that each qubit can be coupled to 9 other qubits. And essentially this happens due to constructive and destructive interferences along this circular transmission line. So each qubit actually interacts with another qubit by sending signals either clockwise or anti-clockwise, and they can interfere constructively or destructively. So if you choose the frequency and the spacings correctly, you get a network map like this. So using this ring architecture, we are actually building a full system. This is a project in collaboration with DRDO and TCS, we are trying to build a full quantum computer with about 6 or 7 qubits. So which means that working on all these aspects, so the quantum processor, the cryogenic setup, the electronics, the calibration software, and also the cloud access. So that's where TCS has been involved. They have developed the cloud-based interface. So once the system is ready, you'll actually be able to use it just like you're able to use any other quantum system. This work is still in progress. It's kind of delayed, but we hope to wrap this up fairly soon. So this is a zoom in of these things. So here you can see the ring resonator. All of these little cantilevers here are the measurement resonators. The qubit chips are placed right in the middle. So there are 6 of them, in alternate locations. So a zoom in of how the chip looks like. And in this architecture, you get a connectivity where every qubit is connected to 3 other qubits. So this is quite a unique connectivity, which is not so straightforward to get using conventional techniques. Okay. Then in addition to this, we've also been developing these high coherence qubits using the tantalum process. As I mentioned, this work is also happening in IISc with Vibor, and we have exchanged samples and films. So in these 3D transmon qubits, where the capacitor pads are now made out of tantalum, but the Josephson junction is still made out of aluminum, we have seen coherence times close to 100 microseconds. Similar numbers have been obtained at IISc as well. We also use the same tantalum process to make this fluxonium qubit, which is a slightly different kind of a qubit and in general has higher coherence. And here we have been able to get coherence times of the order of 400 microseconds in this fluxonium qubit. And we have been doing some studies on the measurement of fluxonium and what happens when you try to measure it in terms of other inefficiencies and instabilities. And we will be putting that on the archive in a couple of months' time, just doing some data analysis. So that's sort of the end of the kind of experiments that are going on in this field. I'll move on to the National Quantum Mission proposal. We have proposed to build superconducting quantum computers with a team consisting of TIFR Bombay, IISc Bangalore, IIT Bombay, TIFR Hyderabad, and IIT Madras, forming the core team. And we are proposing that we will develop a 25-qubit quantum computer in 3 years with the existing fabrication facilities and 100-qubit quantum computer in 5 years, which will need a new fabrication facility. These are the core team members, 8 of us. We have 4 superconducting qubit experts. That's me, Vibhor, Bala, and also Vishal Rajan from TIFR Hyderabad, who's he's joined a couple of years back. We also have a multi-layer 3D IC integration expert, which is needed to make the more complicated chips. That's Viresh Deshpande from IIT Bombay. We have a control electronic experts. That's Chetan Singh Thakur from IISc Bangalore. I already mentioned that. And we have 2 theory experts, Prabha Mandayam for quantum error correction and Sai Venjanampati from IIT Madras and IIT Bombay respectively, who's a quantum optimal control expert. And then we have identified several other partners for flexible high density wiring, test and verification centers, material growth and characterization, more theory, and other areas. So this is just to give you a sense that the entire effort of building a quantum computer will really require a large team addressing various problems. And this is going to be very, very challenging to coordinate in a distributed fashion, whereas companies like Google and IBM have all of these people under one roof. So this is going to be challenging, but that's the boundary condition we have as right now. And we're also looking at collaboration with industry, both within India and abroad, for developing many of the components which go indigenously, and also to get some access to some test facilities, and also sort of future roadmaps by collaborating with other countries. A key thing would be a central nanofabrication facility which has all the right tools. And this is sort of really the distinction we have made. To really develop high quality processor chips, you have to do all of this in a very robust, carefully controlled fashion, where you need process engineers who are doing this day in and day out. This cannot be done by PhD students running around from one lab to the other lab. We need to train them, we need to put them under one roof, and you need to have all the quality resources. So this is something we have pushed for. We'll see how these things go on. So this is sort of just a summary of the various things that have to be done. You have to develop your qubits, look at the materials, improve the coherence time. You need to develop these high density wiring solutions, all these filters and other things to protect your device. You also have to develop these amplifiers for your first stage amplification to get low noise in your measurements. You have to develop this cryogenic packaging and multi-layer chip designs. You need to do multiplex readouts so that you're not putting too many output lines, which also adds to the cost and complexity. So for that also you need the control electronics, which has to be scalable and low cost. And then, you know, some processor architecture and then implementation of error correction and quantum algorithms and quantum control. So that's sort of roughly the summary of what a superconducting qubit quantum computer proposal should be, and this is sort of what we have proposed. So I'll now just end my presentation by saying that, you know, this is basically what's needed to build a quantum computer. In Indian efforts, you know, we have 3 well-established labs, one at TIFR and 2 at IISc, and 2 new labs are coming up, one at TIFR Hyderabad and another one actually at TCG Crest Kolkata. Their lab is actually ready, and they've already tested single qubit devices which we have sent them. So I'm actually advising them and helping them set up their program. We've also identified several experts in allied areas for materials fabrication, 3D ICs, control electronics, error correction, and optimal control. Small scale systems, as we show, are already demonstrated or under development, but bigger processes will be developed under the National Quantum Mission. And there are enormous challenges, but also enormous opportunities. And you know, this really, one thing I already mentioned about the central fab, it's going to be critical, but we have to see. And I think I'll defer many of these things to the panel discussion. But as we were going through this process of preparing the proposals and also talking to other guys, you suddenly realize that even though the scope of the project sounds big, we actually don't, it's not 4,000 crores is actually not enough. And we also have the number of people who are working in this is small. So I think it's going to be critical under the national mission to decide. I mean, there are 2 approaches one can take. One can say, look, this is really a first stage of this development in a serious way. So we push all the fields and bring them up to a certain level and then sort of pick and choose. Or we say, no, we are already too late. We have to identify. So I think some tough decisions will have to be taken, because if you are subcritical in all the areas, nothing is going to happen. But to really push it to the kind of level, we also have to see if the fields are ready to be pushed to that level. Even if somebody is willing to make the investment, do you have the team, do you have the time, do you have the expertise to do that? And here I would end by saying that Apoorva has actually played a significant role, and others have also mentioned this. I remember when I joined in the, TIFR in December of 2012, within a month or maybe even the same month, there was a conference in IISc on quantum, and quantum computing was one of the topics. And there was a virtual center at IISc, which was I think sort of towards the end of its already 5-year program, and I think Apoorva was involved in that greatly. And later on, we talked a lot on weak measurements, which Parveen also presented. In fact, Parveen spent some time in our lab doing weak measurements in superconducting qubits. I didn't have time to talk about that, but it's a very nice platform to implement weak measurements of certain type. And you know, he had some results in his thesis also related to the data we took in our lab. And since I think 2017 or so, when the DST's Quest program started, and Apoorva has been playing an important role, both as a participant of the program, but also to push various things at various levels. One of the things a lot of us were worried about, that we really were missing a senior person in this field, because everybody, this is relatively new in India, and everybody who's working in it has started recently, and we didn't have somebody senior. So Apoorva, I think, sort of took up this role. There were talks about him not saying much, but I have seen him say a lot of stuff in various meetings. In fact, at some point, I had even dubbed you as the angry young / old man of quantum computing. But I think what it helped many of us was that when Apoorva spoke freely at those meetings and pointed out, you know, all the BS, it actually gave a lot of the youngsters confidence to also at least emulate that to some extent. Often, many of us are afraid to say things, and I think that was really useful, that we found that, okay, Apoorva is going to back us if we are saying something correct. And so that was, I think, very useful. So thank you, Apoorva, for pushing this field. I know it's been a great struggle. We know the kind of challenges. We will all learn from our mistakes, and so will the organizers and the funding agencies to sort of fine-tune these things to be more efficient for the next round. Thank you.
Right. So it's very nice. Question on the 25 qubit. How much of it is you planning to do research on what's the right architecture, and how much of it will be essentially take the run-of-the-mill existing transformers and put them together and make it?
Yeah. So given the time frame, this will have to be done in parallel, but the R&D part will feed into the next stage. Whereas the 25 qubit processor will mostly be run of the mill. We won't spend too much time on the design, but there is an aspect of actually designing these chips to be reliable in terms of spurious modes, crosstalks and things like that. And I think Vibor's group has made some significant progress in understanding those challenges. We are still struggling with some of these ideas back in our lab. So it will be a simple system. And this is actually part of the challenge, is that given the kind of time frame, and if one decides that, okay, should a fab facility come up, should we use foundries to send our design, it really affects on what we'll be able to do in the next stage. Because getting your qubit coherences, your material processes down to the T requires a lot of R&D time. It's stuff which other groups have done, but these are not easily translatable from a paper to a new location. And that's really the challenge, is to balance these things out so that we can do this. And this is something we will have to negotiate with the funding agencies on what ultimately is going to be the focus, because there is pressure to build that first system and show that it works. And there are various ways of doing it. We could buy the QPU, right? Because you can say, if you're doing a run-of-the-mill, then why bother? But if you want to do it yourself, even that using existing fab facilities is going to be challenging.
So are you saying that the first 25 run-of-the-mill, then when you go to 100 or more, it will probably take some R&D result and then...
Yeah, so that R&D result will happen in parallel while we are building the run-of-the-mill 25 qubit system, and that will feed in to the next stage, most likely. I mean, some depending on how things progress, some of those ideas could go in to the existing, but we will be testing those ideas at a smaller level, maybe at a few qubits or a 5 qubits, so that then that can plug into the bigger system. I mean, at least that's the way we are thinking. Yeah.
So you said IBM already has 1,000 plus qubits, right?
Yeah.
So I'm curious why they are not launching error-corrected 100 qubits, right? So that will be fault tolerant, which can establish the quantum frequency.
Yeah, so that's a great question. I actually asked this question to Jay Gambetta about a week or so ago. I asked him, when are you going to get to a processor which is based out of logical qubits? So he had a very interesting answer. So let me first say that error correction experiments are running on these big systems. They are not available as toolkits for you right now. And what Jay was trying to say when I asked him this question is that you should not think of logical qubits necessarily as a separate entity. He said, just think of the whole thing as a more complicated quantum circuit, and then see where you can use these error corrections. So error correction is ultimately an algorithm, right? It's a quantum circuit which is running with some more complicated feedback and things like that. And they are pushing a lot on these error mitigation techniques, which is based on understanding the noise in your system and somehow cancelling it out or back calculating the answer. So they are saying that we want to think of not this thing as a current era of non-error corrected qubits versus a future era where only error corrected qubits will be there and you'll do gates between them, where everything is so perfect. He said it's going to be a continuous thing. You're going to have a large quantum circuit where some error correction protocols will run, but other things also will run. But you optimize that based on what the problem you're trying to solve and what is the state of the hardware you have currently and which combination works best for the final result. So I think it will come. Error correction requires a lot of challenges depending on the kind of architecture you're using, whether it's surface code or you're trying to use some of the native things, requires connectivity. And it ultimately is a question of, does the error correction add more overhead to your process that you actually make it worse? Yeah. So I think the superconducting qubit processor errors are just not there yet to do logical qubits so easily. There's been a lot of demonstrations. whereas in neutral atoms and all, it's, the errors are much smaller. But there are still challenges on both sides. So, I mean, this was actually an interesting, I'd never heard this. I also, in my head, it was also like, okay, non-error corrected, and then one day we will all shift to a logical processor. But they're saying it's going to be a more continuous evolution. Well, I think actually for the end user, it doesn't matter. If there is a box and there are 4 men sitting inside doing the calculation and giving the answer, I think it doesn't matter. I think that's the point, like real end user. For the person developing the application, it matters. And
what I mean is, for the end user, whether you say that you can trust the result or not. So that matters.
Yes and no, but already, I mean, we are taking a leap of faith by saying that error corrected quantum computers will work. You still have to demonstrate that the error correction is working properly. So even for these other approaches, in some of the recent results, they actually try to show this, that can you trust the result? And that was a big part of the presentation, which Jay said it's also there in that paper, on the recent paper in Nature some months back, the work led by Abhinav Kandala. So there they're trying to push that how do you figure out that you can trust your results? So you do some checks, they compared it with the best classical algorithms, they compared it with some other things. And it's a hand waving and sophisticated argument, both in the same time. And it really depends. And I think there are different schools of thought on this. But remember that error correction works, demonstrating that is also not so trivial, apart from some very basic checks on coherence.
No, I had actually a related question.
Yeah.
Which is, I was going to ask you how many logical qubits would be equivalent to 1100 quantum?
It could be 0. It could be 10.
It looks like
yeah.
Can't say.
No. So see, again, that depends on the architecture. So the surface code, which is usually been pitched as the most practical way because it relies on a 2-dimensional fabric, it has a threshold. But after that, it actually doesn't matter. It's like if you have very good qubits, you will need less number of physical qubits. And if we have somewhat bad qubits, you will need more number of physical qubits. It's sort of expandable in that sense. So it really would depend on what they're implementing. And to be able to implement one particular error correction protocol versus another, the qubit architecture also matters. How the qubits are connected and how they are laid out. The surface code is most amenable to nearest neighbor coupling, which is basically the standard you can do in planar circuits, for example. So I don't think they are offering logical qubits yet, but I believe he said it's going to come soon.
He said he didn't believe we lived in this era at all.
Yeah.
Because he believes it's a continuous evolution to logical qubits, and their focus is also a lot on error mitigation right now, if not error correction.
Yeah.
Okay. In the interest of time, I also want to remind everyone that there is a very interactive panel discussion that's going to happen post-lunch. So please do take part, and a lot of the questions will get answered there. And thanks a lot, Vijay, for the talk.
Thank you.
So, to continue the program, we are a bit delayed for lunch, but we will continue with a couple of talks that we have left. So we have next up an online talk by Professor Prasanta Panigrahe. He's a professor at the Physical Sciences Department in the IISER Kolkata, and he completed his doctoral studies from University of Rochester, USA, followed by his postdoctoral research in University of Illinois at Chicago, USA, and University of Montreal, Canada. He served at University of Hyderabad and Physical Research Laboratories at Ahmedabad as a full-time faculty. And he's also a fellow of the Gujarat Academy of Science Academy and the Indian National Academy of Sciences. Over to Professor Panigrahe. So Professor Prasanta, you can hear us?
So can you hear us?
Yeah, I can hear you.
So you can start.
Yeah, you can begin your presentation.
Okay. So can you
Not yet.
No, you have to share the screen.
We have to share the screen. Just 1 second. I'll wait. Just 1 second. I have sent you my talk. Is it possible for you to load it?
Okay, just give me a minute. I'll load your presentation. Just a minute.
Okay. So before then let me start with my talk before I get into technical things, because once this goes by, I know Apoorva for quite some time. In fact, there is a very strong overlap with his work. During my PhD thesis, I started working on samples, masses of chromosomes and sigma and this scattering cross section. So at that time, Apoorva also was working on exactly that. So I had been doing his work for quite a years. And during that period, in the 80s, that exclusivity started very seriously. This book in Colombia, we are simulating these masses of variance and valence, and then I got to know that Apoorva knows. So each one of statistics theory has been well known, and particularly in the context of utility and soft facts. And then, for example, I physically met him during the time when there was a brainstorming session in IISc, all by Academy of Science, where computer science people live, and some of the like us were invited from outside. Initiative, Prof. Gupta and others started brainstorming. So I could see the deep side and had a good discussion with him about many aspects, and particularly one of all of us were there. Subsequently, we met in many conferences, particularly once in Allahabad and many other places. And the voice mentioned about quantum discord. So honestly, I also learned about quantum discord through one of his talks. Similarly, weak measurement also, very deep insight about weak measurement. You can see its parts of weak measurement and quantum fluctuations, which I talked about, this beautiful piece of work where this still technique is made, this quantum fluctuation and this nonlinear influence. So we describes it. So you can see he sort of had a fundamental contribution and always tries to very fundamental understanding of physics. Now later on I find, so when I look at his publications, I regularly check his books were found. His works on this quantum coherence in biology, quantum coherence in biology, very fascinating. Similarly, it's understanding of mathematical physics and many of the aspects when he uses it related to quantum discord and with measurement and other aspects, I find very fascinating. So when I follow his works, that will promote him and push it also quite important. So as you can see, these contributions are intertwined, that is the theory. You see many of the ideas what is working on plate, quantum has connection with that. So then, so now I think I now go to this area third and then see I could participate in seeing him, long running. If you are after 26, right? I put myself in 65 last year and currently in Kolkata. So now I start with my talk. Is it loaded? Okay. So I will be very brief. So essentially, my talk is about seeing entanglement, right? So what is the yeah? Yeah, sure. Am I audible?
Yes, sir. One more. Okay. We can start and let us know that.
Yeah, okay. So, my title of my talk is Seeing Entanglement Through Light. What we're talking about is, dipolar, two-level dipolar systems. There are three of them. So, that's a very fascinating system which can relate to gauge state, local state, and this is emitting light. So, looking at the past behavior, can you really infer about nature of quantum correlations? What kind of quantum correlations? Quantum entanglement, quantum discord, and of course, tangent like system. So those things can be inferred by looking at hard light which is emitted from three coupled systems. So, and you will see this very simple system show a very fascinating behavior and the clear difference between different kind of systems as a function of temperature and also light frequency what we are using to probe the system. Next one, please. Next one. So now, so it will be two-level systems. There are three of them. So I will be looking at intensity behavior, the heart rate. And then I show you, apart from proving different kind of correlations, you can actually use it for some kind of technology, like frequency concentration, where you will see tangent plays a key role. Next one, please. Okay. So the Hamiltonian of the system is general and particle system. You can see can be written in terms of all these three matrices. The first one is diagonal, and this is like exactly like a magnetic field. So that is a dipolar system. So it behaves the same way like a magnetic dipole. So dipole have to crash. Now the second term is the coupling term. So and the S process minus and the gauging are load operators. So this is quite familiar, same kind of behavior, and you can see I will be combining myself only three particles. Next one, please. So you can see when I want to see the behavior of light, now I put my detector on the domain. So the configuration which I have chosen here is so-called line configuration. The three atoms are put on the x-axis. There is another one where we put the loop configurations where 1, 3 is placed in such a way it joins with 1. You see very different kind of behavior because of these two different configurations. So in the these are the coordinate systems, and this x and z axis is the one. And your dipole moment is pointing along the xz plane. So don't worry about it too much of geometry because these things are on how this work and take out x these things. Okay. So part the domain, the positive frequency part, that's the one I will emitted. And see in the equation 2, the loading operator is minus. The x-axis is taken with load, and hence this positive frequency also light emitted. I'm in the part wave domain, so that's the this behavior the exponent here by r, and r is the distance from the origin, and that the distance r. So this n is the unit vector of this vector direction r by r, and the dipole is this transition dipole between excitation and static unit vector field, and so you can see this geometry can be further simplified by assuming stable directions for that moment, which and also taking direction of observation. Next one, please. So if you do that, things will simplify. So that's what I have done here. Things will simplify, and you can finally perceive that in equation 4, it is this spin-spin type of correlation which plays a key role in determining the behavior of light and the R domain. That's what I want to emphasize. That electric field average which you are seeing is actually controlled by this S plus S minus average, which you know really gives track of fluctuations, entanglement, all those things. So it can be the reason why you will see light intensity will vary. And the phase also that I minus ij will also depend on the marking of correlation integration. So correlation is decided coming in equation 4 because it's binarious, which we have seen here also. In case of spin systems. Next one, please. So now I do a thermal operate and try to see how it behaves. Very simple. Basic matrix is this exponential minus e by kt factor, and then if dimension is 3 for the system, so I put one weight and it normalized by the numerator. So ratio of mu. What is the thing what one finds in mathematics is? So we assume suitable things. For example, that nothing all the frequencies are same, which may not be realistic, but there are systems that we can assume same. Suitably to choose the public so that one could put same or the one is zero. This is just for illustration. In which case it gets simplified. And you can see question 7. It looks like kind of things we encounter in optics, diffraction experiments. Okay, so now what is the first interesting result? That there are two cases. And this kind of baseline song was seen in early 70s in Michael Hill's work. And this was actually theoretically determined around 50s. So you see that the uniform plates and then the phase where coherence is going on, and then a distinct baseline. So this is the so-called decay state. Decay in 50s realized that going on multiple parties, this nature of the multiple state will affect the mediator. We don't interpret in terms of entanglement. Often we are understanding that this happens precisely because of entanglement. So there is a uniform phase and there is a non-uniform phase. They actually characterize as a phase transition. Here it arises because of the nature of quantum conditions that has to be addressed. So this transition was seen earlier in 70s experimentally. So now what I'm showing you that the function of temperature and improving frequency omega versus the gap sigma parameters is very next one page. So now you can see that the intensity is quantum correlation. How does quantum correlation behave? We know that something very intriguing what we found here is in which Mahesh concerned about this act that is called the distance between separable state and intact state. Using it for experimenting. So what you find is that this like shortened date quantum correlations conference they vanish suddenly. In monogamy also are the same behavior. But as we have seen earlier, this could survive for only our period. This was seen experimentally in many experiments. You do see here, it is the group power which survives at a constant temperature, whereas this conference suddenly was equally another something. That's what you see here. But what happens is that after the temperature, when you change omega, you see that in B, you got B, at one point, suddenly all these things vanish. Entanglement, discord, and all of them there is quantum gate. This part I still don't understand. And these are happens omega, not temperature. So this is something which is quite looks like more of a quantum differential, which we have not understood. But this is surprising aspect of it, and this behavior of phase transition. Now let me show that what tangle the role of tangle. We know that monogamy is characterized by tangle. So only three-body nature of the system. So it will actually compute tangle. And when you do that, you can see that behavior of the tangle is actually somehow captures the intensity correlations what we saw. We saw there are pages which are uniform pages, and there are pages which are coherence in present. So those things can be actually characterized through monogamy. I'm not getting details, I'll give you a reference here. But very interesting that three-body correlation plays a very significant role, and I'll point out the same three-body correlation will play a role in the generation of the frequency form. Okay, now if to understand more about the nature of entanglement and the phase transition, I will refer to parts of individuals, overall, and its collaborators. Also, that how, for example, for GAZ and of the state, the nature of phase transition is different, and particularly trying to understand very deeply the one of decay in terms of entanglement. See, there are also few ideas of late. So, decay state is a very well known state that we use for quantum processing. Only of late we are appreciating this work of decay, that the nature of the superradiance, many behavior like people have seen experimentally, superradiance. That this work was in terms of superradiance, that intensity will be like proportional n and the number of atoms to n squared. And is now being placed to entanglement. Because of entanglement, n squared will comes. Now, there are ways of making it more than n squared, for example, by putting external sources and external feedback kind of thing. But n squared was the result of making in opposite atomic systems, intensity would be proportional to n squared, and that was verified empirically. And that happens in one case, and there is a case where this doesn't happen. The case where it happens is where quantum fluidus crystallization is coherent, which behaves in terms of coherence. And when the quantum fluidus is not present, you have uniform phase. And in that case, for example, this kind of n squared doesn't happen. It's coherent addition of intensity between n and addition. So here is the one where you can actually use entanglement control the amount of proton that you get in the heartbeat. So the other one is that there are various experiments demonstrating this kind of thing. Early on, 70s, the experiments only showed the extension. Now, nature of coherence, quantum discord, and quantum monogamy, and others, they are coming up now. And not still of So now, this optical frequency term is the other one I'm just going for launch. So this is actually here we found that intensity calculated two dipoles. One reason of consistency is because there are atomic dipoles now. Both atoms where pure atomic dipoles are being manipulated, and people have seen super solid and many other places there. That was one reason why we did. It's a bit complicated, but thanks to mathematical matter, do it. So still kind of good system, except that the coupling has the additional terms that are needed. Now, one of the things what we observed here, I just summarize for you what we observed, is that there was the fascinating thing was that there are two different configurations, which was so-called loop configurations, where three atoms are put in a triangle. Other was the line configuration, and they were very different. Now, and what we found is that some of those pictures I show you, that also and you can see that it was this second one, the type B, which was actually loop configuration. So very nice coherence property and the frequency compensation, whereas the other one was not so. So this, basically geometry is a very key role, and this is about here. Now, the other thing what we observed is that what is the effect of temperature, or what is the effect of this parameter probing omega, and you do see that the effect is very significant in both the phases, and it's again very different. You can see that first one is basically linear configuration, line configuration. Here you do see that this effect intensity showing similar behavior for a longer duration of OL. OL is a parameter which is issue between frequency of the incident light and the ratio of omega. And whereas the other case is not present. So this thing we don't quite understand because it is the X different system. But you do see that you can control system and have a control generation, and it is the angle which plays a big role there. Let me show you how of that. For that, for example, you can conference and all that. So and you do see that the explicit dependence on monogamy, which is a vertical equation, which is understandable because you want to generate the some kind of correlation, 3-body or 4-body correlation is required. Because otherwise, how do you generate the system which can be verified? So that is much more understanding the problem. But basically, we thought to see this not the conference, but monogamy which is and as a function of temperature and improving frequency, we will satisfy. So I will, and then you go to intensity in this impedance. That is the radar work of these people. Again, you see very significant difference between this fully shows the quantum nature. And when entanglement is present, we expect it to be quantum. So now you see it's present when OAL is small. And when, so basically you can control the quantum behavior and control the super radiance, which is intensity. Also control the photon is how quantum is. So that we say some simple 3-body system actually can retrieve of desired intensity, desired potency. Okay, so I conclude that if there are simple 3-level systems, like for example, which atomic to encounter in lambda system, in B system, so which already had shown fascinating behavior Pascal level. Same system where the entanglement is length and truly show very interesting behavior, particularly the unique complex and the homogeneous complex density 1 kg dependent on the square, where the quantum collision is today, and pH like N, when it is not today, the distinct pH transfer will be maintained. Then bottom one you find the pH transfer is different, ion temperature and fluid temperature. The possibility that one could be a quantum pH transfer, one could be Pascal. Bottom one you find that there are qubits from the system where unity of the system will manifest in the group of the system and computation. And here, monogamy, theory for the system is a very right. And then you do see that for intensity, but quantumness, correlation can be controlled. Both are a function of temperature and as a function of frequency. It is more dependent on improving frequency than temperature. I think I stop here. And the reference I was mentioning to you, and there are some recent experiments. Short. I will stop here. I will just give some of the pros and not much. Thanks a lot. Again, I wish you all a great time. Those retirement is my personal like that. And I know just contribute significantly to our quantum community. This new sim is doing very well, and we will provide you other contributions coming. Thank you so much.
Thank you. In the interest of time, we'll move on to the next talk.
Sure.
Final talk of the morning session will be by Dr. Aavishkar Patel, who is a Flatiron Research Fellow at CCQ Flatiron Institute. Aavishkar received his PhD from Harvard University, and he was previously a Miller Research Fellow at the University of California, Berkeley. Who is Aavishkar?
Sound good? Yeah, okay, good. Yeah, so thanks for the invitation, and I'm very happy to be speaking in this event. So I'll be talking about work that I've done on the strange metal problem, which is a very quantum many-body problem, and my recent efforts on solving it computationally using a method called hybrid Monte Carlo. So the physics is quantum, but there's no quantum computation here. The computation is all classical. So yeah, before getting into this strange metal problem, which is a highly entangled quantum many-body state, I'd like to mention some work without any quantum entanglement that I did with Apoorva. And this was probably, this was my first research project in physics, actually. So this work was constructing a classical coupled oscillator model for which reproduces the dynamics of Grover's algorithm, and that's because Grover's algorithm doesn't have any entanglement. So you can actually implement it with classical wave dynamics using coupled oscillators. And these are the steps in Grover's algorithm. So what this did was that it mapped the amplitude of the quantum states in near to velocities of classical oscillators like mass spring systems, And then the various operations like flipping the amplitude became flipping the velocity, and then there's another operation which was just implemented naturally using the time evolution of the system, and you could like increase the amplitude of a target state. So that video is like literally a mass spring system that I constructed for that project. So that's some quantum mechanics without entanglement that worked on with Apoorva. But I then moved on to quantum mechanics with a lot of entanglement. I worked in the field of strongly correlated systems. So it's a quantum many-body problem where your Hamiltonian is not quadratic. It has strong interactions between electrons. And this problem is the core of modern condensed matter physics. You have things like Hubbard models and high-temperature superconductors that are all strongly correlated systems and are what people work on a lot. So the high-temperature superconductors are materials which I'm interested in, and they are superconductors, but the transition temperature for superconductivity is much larger than liquid helium for conventional metals. It's liquid nitrogen temperature range. And the microscopic mechanism for why one can have superconductivity at these high temperatures under ambient conditions in these materials is not well understood. But they already have interesting applications, like one can make lossless transmission cables and electrical equipment, and also more recently they've been used to construct magnets which can carry very high currents and compact geometries that are being applied to building fusion reactors. This is a thing that has an idea that's been around for a while, but it's caught on again in recent years. So in order to understand how high temperature superconductors work, one has to understand what the normal state is, so what they are above their transition temperature. And that's what's called a strange metal. So the strange metal is a metallic phase of matter, finite density of carriers, it's compressible, but it has unusual electrical properties. And the hallmark of its unusual electrical properties is it has an electrical resistance that's linear in temperature over a wide range of temperatures, all the way down to the superconducting temperature, or even below it if you suppress superconductivity. And that's in stark contrast to ordinary metals like copper, where at low temperatures the resistivity scales quadratically in temperature. So, like conventional metals are just mostly non-interacting electrons, and in a regular crystal lattice, you fill up electrons in a band up to a Fermi energy. And when you apply a voltage to it to measure the resistance, the electrons drift, and then these electrons collide with impurities or with the crystal lattice, but only occasionally, moving around freely to a very large mean-free path. And what one gets at low temperatures from collisions with the lattice or Coulomb-Clap processes, you get this T-square dependence of electrical resistivity. And at higher temperatures, you do get linear in T from phonons. And there's also a zero temperature finite residual resistivity from impurities. Strange metals are different. Electrons interact very strongly with each other. There are just so many collisions between electrons that they quantum mechanically no longer well-defined individual classical quasi-particles. They become a highly entangled quantum soup. But they still conduct electricity. And in addition to these strongly interacting electrons, the crystal lattices that make up strange metals have much more disorder than elemental metals, because they are dope materials with several different kinds of atoms. And their transport properties are different. The electrical resistivity is linear in temperature down to almost zero temperature. So you take something that's like a qubit high temperature superconductor, and you apply magnetic field to kill the superconductivity, you get linear temperature resistivity plus a residual down to less than 10 Kelvin. There are other materials which have even lower energy scales, like the heavy fermions, where your linear resistivity goes down to order 10 millikelvin. And that's well below the scale at which phonons can produce any linear resistivity. So it's not due to phonons. Now, in order to get any kind of electrical resistivity, whatever, in a metal, you need to solve the momentum bottleneck. So if you normally have an electron fluid current that's flowing, and that flowing current carries momentum. So in order to have resistance, where you have to restrict that current, you need to relax momentum. So you can't, like a translation invariant system with no momentum relaxation will have more resistance. And now, if you say you have your electron fluid is subject to impurities or other kinds of disorder, or the crystal lattice and phonons, then you can have momentum relaxation. But I mean the low temperature limit where phonons don't work and Umklapp's very weak, you have to only have only thing that can work that is generic across several different systems with disorder. So that leads to a conclusion that strange metal behavior is probably occurring due to, at low temperatures, due to disorder in these materials. But that there are also many other results which tell you that electron scattering in strange metals is inelastic, which I won't get into here. But the usual way in which disorder is treated in solid state physics textbook is the elastic impurity scattering, which is not the right kind of scattering for strange metal behavior. So we need to find a way for disorder to mediate inelastic electron scattering in order to get various properties of strange metals. And this rather simple model for that was proposed in my paper, on this paper here, where what was done is to note that in a strongly correlated system, in any kind of effective description of a strongly correlated system, one that doesn't have impurity potential disorder, but the interactions between electrons can also be disordered. That's why we have spatially random interactions. For those over here who are specialists in condensed matter physics, the model in field theoretic notation consists of Fermi surface of electrons coupled to a bosonic sector, and this boson is almost gapless, it's near critical. But the important point is that the boson couples to the electrons via Yukawa coupling that has a spatially random component. So your Yukawa coupling is this uniform component G, but also has G prime of R that depends on the spatial coordinate. It's a fluctuation about the mean. And the G prime of R is just a Gaussian random variable. So this model, if it cannot be solved exactly, it can only solve it in certain kinds of artificial large N limits, where you assume that you have a large number of electrons and a large number of bosons for lattice site, and derive some mean field equations. And then, but still, those equations, they actually do end up reproducing some of the signature of strange metals, including linear temperature resistivity. But in a real system, one doesn't have large N number of electrons per lattice site, and can't apply mean field theory. So one has to go beyond large N and mean field to make this more realistic and think about what's going on in a real material. And for that, there's no choice but to resort to computation, not to analytic calculations. So what I've been working with is quantum Monte Carlo, and specifically we write down a model which contains, again, your fermions at finite density of the Fermi surface interacting with bosonic modes via this spatially random interaction. And these bosons out here are taken to be spin density way about antiferromagnetic excitations. So in pictures, you have this model with two flavors of fermions that are usually coupled to each other via this boson with a coupling. You have a coupling that's a random function of space. And this two-band structure was first introduced in this paper. The advantage of this particular two-band structure is that when you integrate out the fermions, you get an effective action of the boson that's parameterized with this determinant, the fermion determinant that you get after integrating out. And the determinant comes from a matrix A that's Hermitian positive definite. So it's always positive, so that then this becomes a probability measure, and then you can just sample over your phi field using Monte Carlo. So in other words, there's no sign problem in this model, which makes it feasible to solve it. So, of course, computing that determinant is not easy. You have 2 dimensions, so you have L square sites, and you are also discretize imaginary times, so you have NE points in time. If you want to compute a determinant directly, it costs the order of the cube of the number of degrees freedom, and that's very bad. So usually what is done in quantum Monte Carlo determinants is you compute it once, and then when you update your phi field, you do it in such a way that you only have low rank updates for the determinant. So that reduces the cost a bit, but still add to the 6. So you can't go to large spatial sizes. And furthermore, if you this low rank update method requires you to compute, store, and apply A inverse and keep updating it. So A may be a sparse matrix, but A inverse is large and is dense. It's an extensively sized dense matrix, and by storing and applying it, it's very expensive in terms of memory and bandwidth. So solving this problem at scale with ordinary determinant in Monte Carlo is not feasible, especially with a disordered system where you do need very large spatial sizes to average over disorder. So there's another method called hybrid Monte Carlo, which is much better. And this method came from the lattice QCD community. It's actually something that Apoorva used in his old research back when he was a PhD student and a postdoc. And he used HMC with other people like Rajan Gupta also spoke initially. So this use of HMC is also part of the quantum legacy of Apoorva. So in HMC, you don't compute this determinant directly. You rewrite the determinant using a Gaussian integral over a new set of complex scalars, this var phi. So now you have a joint probability distribution of phi and var phi, and you sample over both of them and then marginalize out var phi to get the path integral over phi. So so you don't actually evaluate the determinant ever, but when you're given a var phi, you will compute A inverse, the action of A inverse on that, so that involves solving a linear system with A. But that can be done with an iterative linear solver. It can become expensive, but there are various techniques like preconditioner to reduce the cost of that. But ultimately, this thing uses far less memory and bandwidth than the determinantal method. The cost is only order L square on L to the 6, and it's a little bit worse than linear in NT. And also this linear solver, which uses iterative method, where moves only matrix vector products, is very GPU friendly, and you can implement it on GPUs and get a lot of speed, and you can scale this to large sizes because the complexity is not that bad. So implementing on GPUs, we do these matrix-free matrix vector operations where the different rows of the matrix are all applied at once to the vector in parallel using the architecture of the GPU. And one can code this up very efficiently so that it minimizes memory traffic and make the best use of whatever memory bandwidth you have and get a lot of speed. It's 10 times faster than it's using sparse matrix formats. It uses much less memory and bandwidth than DQMC and is therefore greatly accelerated on the GPUs. So we did this, and then we also implemented a preconditioner, rather sophisticated multi-grid method, which involves doing an approximate solution, then using that solution to get the actual solution. The approximate solution is done on a coarse grid. And there are various subtle points involved in coarsening the coarse grid and then transforming back up again, which I will not get into in the interest of time. But it does, you get further 3 to 5 times performance boost from doing this. And then finally, we can compute A inverse action on phi, but then one needs to also update on bar phi, and then one also needs to update phi, and that's done via this fictitious Hamiltonian dynamics. That is one of the key features of HMC, and one can adjust. There are various ways in adjusting hyperparameters to make sampling very efficient. So we did all this, and we get this non-perturbative phase diagram of this model with a strange metal. This is a mass tuning parameter. Go from a gap boson phase to a short-range ordered boson phase with a small mass gap, and in between the two, there's this intervening region between lambda S and lambda G where you get a strange metal with T-linear resistivity. And to the right of it, you just get a conventional boring Fermi liquid. On the left, you get something that's different. So the key to the physics of this strange metal is that the bosonic eigenmodes, the low energy bosonic eigenmodes, are not extended plane waves anymore. They're extended at high energies. This is the localization length. And then low energy, they become localized at small localization length. So you have these various localized bosonic modes that electrons can scatter off and give you unconventional transport behavior. So we can measure the transport behavior by applying the Kuba formula on the imaginary axis, and then reparameterize the conductivity that we get in this ruled form, and then we can look at like what the scattering rate is after we extrapolate it to zero frequency to get the DC value and see if it's sensible. So if we carry out that procedure, then in this strange metal region, lambda S and lambda G, we find T-linear resistivity, and the slope of the T-linear resistivity is maximum at lambda S, although it's linear in this whole range. And then for very massive bosons beyond lambda G, you get a larger power of T, or 1, it's more like a Fermi liquid. But at this special point, lambda S, where you get the T-linear resistivity and maximum slope, the scattering rate is of the order of kBt over h bar, so that's what's called a Planckian scattering rate. And also the residual resistivity ratio is large, so if you extrapolate this back, the residual resistivity is small, and as you increase temperature, you can get a resistivity that's much larger than the residual. So that means the fermions are relatively clean in spite of the bosonic sector being highly disordered. So further interesting thing is that we can change the amount of interaction disorder in the system. So this random coupling G prime, we can change the value. But if we always get to this special point lambda S in the phase diagram where you get the best T-linear resistivity, the transport scattering rate stays the same. So the transport scattering rate is linear in T with the same slope at this point in the phase diagram, lambda S, even at different values of the random coupling. So there's a universality to this Planckian transport scattering rate. That actually comes out of a property of the bosonic density of states that it scales inversely in the random coupling. And if one then it's actually that scaling the bosonic density states is compatible with universality of the transport scattering rate, just from looking at the one loop self-evidently. But we don't really have a deep understanding of why one gets the scaling in the bosonic density of states so far. But this universality of the transport scattering rate is actually very interesting, and it actually correlates well with what is seen in experiments. So the experiments done on several different strange metals. These are like various cuprate compounds, and they have different chemistries. They have different amounts of intrinsic disorder because of the different chemistries. So if one thinks that our model applies to them, they would have different amounts of random coupling strengths. But they all have transport scattering rate as order kBt over h bar with pretty much the same three factors. So they have the same slope of T-linear resistivity. And that universality is something we can reproduce, and it's very clearly a non-perturbative phenomenon. It doesn't come out of any naive perturbation theory physics. So that's a big win for our computational work. There aren't any other ways of understanding why one gets this universal T-linear slope from other calculations so far. So to conclude, high temperature superconductivity in strange metals are non-perturbative quantum many-body problems, and high performance computational methods are going to be necessary to gain insight into them. And we have a sign problem-free model and a powerful algorithm that allows for scalable non-perturbative solution of strange metals. And we can probably learn a lot more from it besides just linear resistivity. So it's an active area of work with a lot of things to do. And furthermore, one has these models. They tell you that one expects strong disorder in the bosonic sector of strange metals, but not the fermionic sector. So that leads to these localized bosonic modes, which would be interesting to detect experimentally directly. That's something that experimentalists can take away from the things we've been doing. And yeah, we also have we're able to reproduce this universal Planckian T-linear transport scattering rate in strange metals independent of the order strength. And ultimately, we would want to have connections between these models to microscopic ab initio models of high temperature superconductors, where the ab initio calculations are done in such a way that they actually explicitly take into account the effect of disorder in the dopants and other things. So with that, I conclude.
Questions? Yes, Arina. So it looks like that all the universality is strongly sensitive to which point of phase space are you at. So essentially, if you are at lambda s,
yeah,
you go a little bit this way or that way, it's going away.
Right.
So is there a reason to believe a normal system which is completely natural will always end up in that point?
Well, when the experimental measurements also universal at the point where they get the largest slope of T-linear resistivity. Yeah, they're at the optimal doping, right? So they've also tuned their parameter to a particular value and in each different material, and then they compare the slope. Yeah.
Experimentally, there's always a range. It's
Yeah.
not just you have a tool. We talk about the high. So, but linearity of the resistivity is more or less there over the entire area of the tool.
Yeah.
So it's but lambda s is a specific point in time.
Right.
So how do you sort of see them to be relevant? Because nonetheless, it's not that the moment you go away from the calculation,
Yeah.
the moment you go away from numbers, your scattering rate, the slope is changing. So
Yeah.
you're away from the plateau.
Yeah. Yeah, so the coefficient does change. So this behavior is specific to
Scattering
lambda.
rate's a range, right? So, and there, the coefficient is more or less the same. I'm not sure, but I might be wrong.
I think the slope does change as you change like the doping. It's not always Planckian. There's like once you go to optimal doping, it's Planckian. That's so they also tune their system in different materials.
So you were saying that we always end up at lambda s the moment you try to tune the system to the highest superconducting condition.
Yeah, to the highest TC, yes. And that's
But that's hunting. Is there a way to justify this from the other side?
well, no, not yet, but we hope to understand it better in the future.
Any other questions? Not, let's thank Aavishkar. Token of appreciation, we have a memento. So now we have lunch, and we apologize for the delay, but I hope the morning session was quite engaging with a round of extensive set of topics covered in the talks. And in the interest of time, we will resume around 2:45, so that we can. We'll have a panel discussion in the afternoon, which promises to be quite interactive. So I request all the students to come back. Thank you.
So welcome back to the second session of the Quantum Week. So we'll be starting with a panel discussion soon enough. But before that, we have a couple of video messages from former students of Professor Apoorva Patel who really wanted to be here but couldn't. So first, we have a video by Vijayaraghavan.
Hi, this is DDJ. First of all, I'd like to Hi, this is DDJ. First of all, I'd like to the second time I said for not being able to do Congratulations,
Try it, no? HDR.
Problem is with the here it says the recorded video itself output is very low. Okay.
But
Still low.
Yeah, it works.
My association with Professor Apoorva Patel. Hi, this is DDK. First of all, I would like to thank the Institute for members and other audience. My association with Professor Apoorva Patel was a dream and it is not even completed because it has immensely impacted the way the second time I feel grateful for not being able to do so. I wish I stayed. In 2011, this conversation, I started to work and the same thing at IISER. After those works, I started working in one of the open scholars. Idea was think of once we had an insight that of course I realized it's really come from I was in Venezuela and I was working, I was not impact and organic processes. I just have to focus on biomechanics and moving after appreciate. And of course, that was not a problem, and I still have time for that. I have a few fond memories with Professor Patel. Once in a seminar about computing, he expressly advised that sort of speaker to qualify the statement lab for something entanglement and recover herself. In fact, functional entanglement is not discussed. But it's too easy to spin to quantum entanglement. And once he said 80% of what theoretical physicists predict is wrong. This sentence only looks profound when we normalize this in other fields, where almost all the time what people say is wrong. He was a theoretical physicist at heart. He had a very clear sense of distinction between mathematics and science. And he was always a chemist, meaningless trend of symbol manipulation. So he didn't publish many papers, but wherever he did, he provided a fresh and original perspective. To him, physics was a way of thinking, and everything was an element. He lived this. I heard about this before. I read a quotation similar to this one, but having spent some time with him, made me realize there's some meaning behind that. He approached problem in various aspects. I came to realize that biology was a proper science instead of bookkeeping. After having a few discussions with him, he asked fundamental questions like, why are there 4 nucleotide bases in DNA, why about 20 amino acids, why 2 eyes and 2 ears, or only 1 nerve? And even with the evolutionary classified life mechanism, he provided impossible arguments for instance. People working with computers as well, not just in theory, but at hands-on, he set up the email server and debugged them. Once I saw him using an esoteric Linux command very easy. And that gave me confidence to tinker with the computer system myself. I have mentioned intermittent but regular communication with him ever since. I've been pestering him with questions of cell division, thermodynamics, and recently about ChatGPT as well earlier this year. It is always a delight to talk to him. I wish I would have the strength to stay away from cell phone and hypes in technology and also in science in general. I wish him all the very best. May he has a very happy and prosperous life ahead, a very meaningful life ahead. I wish, if it is possible, at some point in time, to spend a few months or years with him in a Gurukul-like setup and explore the mysteries of nature in a completely unconstrained way. Thank you.
So the next video is by the student Pranav.
Congratulations, Apoorva sir, for your superannuation. I really enjoyed having you as my academic mentor at IISc and all our interactions after that. I wish you all the best for your future endeavors.
And the final message is by Utkarsh.
Hello, Professor Apoorva. I know it's a special day for you and I want to thank you for everything. My journey in quantum world would not be possible either without you or learned you. For that reason, I always cherish my best summers of my life. I got to learn so much. I had so much fun, and I still remember you solving those big density matrix equations on board and then asking us to code up to verify them. We would take more than half a day to do that, and we would have solved it just like that. So yeah, all the progress I make in sciences and the nation makes it quantum, I think both of us owe it to you. And I hope you use the retirement as just another opportunity to keep on inspiring people like me. Thank you. Take care. Bye.
So with that, we are going to start the panel discussion. So let me introduce the moderator for today's panel discussions, Professor Arindam Ghosh. Professor Arindam Ghosh is a very well-known personality in the quantum materials domain of research. He received his MS and PhD in IISc from IISc, and then went on to do a postdoctoral research associate at University of Cambridge, UK. And his areas of interest are in 2D materials, where he worked with graphene and other 2D materials. And for this work, he won the Infosys Prize in 2020 for the development of atomically thin two-dimensional semiconductors to build a new generation of functional electronic, thermoelectric, and optoelectronic devices. So let me welcome Professor Arindam Ghosh onto the dais.
Go there, or you can come. You want to 1 minute.
Sure.
Okay, you can hear me, right? Good. So, thank you, Bala, and I think I was supposed to give a small introduction to IQTI, but no. Okay, so I'm going to go short on that because I think let's give a more stress on the panel discussion, which is quite interesting. So IQTI, probably all of you already know here, tries to use the core strength of IISc, which is a large multidisciplinary institution, and we have now more than 11 departments participating in it, and about 50 to 60 faculty members from these departments. We look at various theoretical and experimental and hardware aspects of quantum technologies. And you can see the way quantum technology is shaping up is quantum computing, sensing, and communications. They all require a very strong interdisciplinary effort. The fundamental science must meet the engineers, and that's what we are trying to do in overall IQTI activities. But IQTI needed a leader, and I don't think there's anybody here in this room who will agree that without Apoorva this wouldn't have happened. And I think I would just add one more sentence or two on this. Apoorva has led the quantum efforts in IISc as nationally as well, but he actually could shape the quantum efforts in IISc from the beginning in a hands-on manner, because he could teach the students here as well as give the realistic viewpoint to the faculty members. It's very easy in quantum world today to get essentially blown away with all the hypes and all the talks of money, for example. Apoorva always made sure that we keep ourselves grounded, and he managed 3 consecutive projects. First the Quest project, then came the Center of Excellence, COE from MIT, and now with the NQM coming up, we are continuously, anytime in doubt, it's Apoorva who is heading and guiding us through every detail and every intricate scientific step that we should take. I think with that introduction, I would like to invite our panelists because National Quantum Mission is going to be the story, I would first like to invite Apoorva on the dais, please. Apoorva. Next, Mahesh, T.S. Mahesh from IISER Pune, whom you have heard today morning. I will not go through the introduction of Mahesh or anybody as such, because you already know they have already spoken or they will speak, so it'll save some time. Vijayaraghavan. Professor Chandni, you. Chandni probably is not speaking, right? So she is a faculty member at the Instrumentation and Applied Physics Department in IISc, and also one of the young faculty members who is engaging with the quantum material and verticals and devices. Professor last, Umakant Rapol. Umakant, please. Professor of Physics at IISER Pune. Okay, so probably I can take my seat over there now. I think I can speak from here, and those two mics can go to individual. Okay. So the theme of this panel discussion is the quantum technologies in India with the NQM and the way forward. NQM, the National Quantum Mission, has started, and now there is a lot of activities that's going on to attain certain technology goals for the nation, and those which should be at par or on par with the global standards, what the world is trying to achieve. Of course, there are, I'm sure you got some impression when some of them gave the talk to the morning, that India is at far behind in certain aspects of technology. But the reason we are meeting here today is because the quantum technology is not in a state where it's completely decided who is going to be the winner. And still that happens. It's always certain aspects of infrastructure building, the knowledge creation, so that we can create the basic know-hows and jump into the technology that we believe will eventually make the best. So in that context, what I did last night, I sent a message that each panelist here could touch upon three aspects in their respective domains of expertise. First is, what do you think are the unique challenges and opportunities in your area of expertise? Then, whether do you think the National Quantum Mission mandates are sufficiently realistic? We can achieve that. And the third is, do you think India as a country, given the resources and the funding that's going in, can lead at least in one focused area? This is a very important thing, because at the end of the day, we would like to be independent. So in their mind, is there any area, however focused it is, that we can make a mark and lead that subject in a global manner? So with these three, I would request my panelists, maybe we'll start again with Apoorva, to have a brief comment on these directions and what you think along these lines. If you can, let's have it in about 4 or 5 minutes, and then we can each, that is. I know you have lots to say, Apoorva, but we will come back to you.
Yeah, I will repeat some of the things which I have said many times.
Yeah, it's on.
And let me begin with saying that the questions of security will always come in at some stage or the other, and if you want to develop it, you have to learn how to stand on your own feet. There is no escape from developing the expertise indigenously. You cannot rely on anybody else. Now, given this particular fact, we can look at known examples from history. And the high-level technology has succeeded in the examples which I have quoted many times, when the control was in the hand of the scientists. not the bureaucracy or the politicians. They cannot do the job. They have to follow the guidance given to them by the people who have the technical depth of knowledge. And the most well-known example of this is not from our country. It is from the US, how they built the atomic bomb. You may not have read the history, but you may have seen the movie Oppenheimer. The government had all the resources. They had the factories to deliver all the kind of weapons, but they did not give the job to any of these weapons manufacturing factories. They gave the job to Oppenheimer. Why? Because he could deliver. That was the criterion. And the government, of course, they watched it from the sidelines, but their role was to provide the support. And it has happened in our countries also, where the technology at very high level has succeeded, whether it was Homi Bhabha leading the nuclear technology, or Vikram Sarabhai, who was leading the space research, or Satish Dhawan, who followed him for developments of various kind of rocket engineering. They were the ones who were setting the agenda. And the government gave them the necessary support, and now we can say that in this field at least we have reached somewhere. Of course, there can be a time lag. Means Chandrayaan repeated what Apollo or the Soyuz and Luna missions did 50 years ago. But still, it is a worthwhile achievement, even with the time lag, because we did it indigenously. And that is the fact which must be kept in mind. I have been telling that to the government all the time. I don't keep my mouth shut about it at all. That you are not the right people making the decisions. It's not the finance department will decide what can be funded and what cannot be funded. They have to find areas where we can choose. We don't have to do everything, but we have to be prepared. And that requires all kinds of intermediate steps. You don't repeat the mistakes of somebody else who did. You can even reverse engineer many intermediate steps because it has been demonstrated somewhere else. But beyond that, you develop a basic skill and preparedness, so whenever the opportunity comes in a specific area, you can jump on it. And that preparedness is a fundamental requirement which must be the focus of the future agenda in this particular national quantum mission.
Good. Thank you very much, Apoorva. Mahesh?
I think your first question was 3 challenges in our areas, right?
And opportunities.
Opportunities. The challenges are already well laid out by De Vincenzo, so 25 years ago. So he named 5 criteria. So like scalable qubits, initialization, high fidelity gates, coherence time, and qubit specific measurements, and so on. So some of these challenges are fairly overcome in some techniques. As far as NMR is concerned, initialization is still yet to be overcome. That's one challenge. Qubit specific measurement will be problem when we go for larger qubits. So that's another. And quantum control, of course, that is ever increasing problem for all the architectures. Okay. So these are, and of course, prospects.
Yeah.
So prospects are, as I mentioned in my talk, there are prospects in terms of hybrid quantum computing, where you have a quantum kernel and which is interacting with some very specific task, which is doing, it is not doing universal quantum computing, it is doing very specific task and it is supporting the rest of the classical hardware. So that's where I see that there is a prospect for NMR. And for NV Center, of course, there are a large number of prospects because so it provides very pure qubits, and it is optically detectable, very sensitive. Qubit specific measurements are very efficient. And it has multiple platforms. It can be integrated into from communication, sensing, and quantum computing, and so on.
So that way, Mahesh, actually Apoorva did touch upon that aspect, preparedness, and jumping into a possibility in which we probably can contribute and make an impact. So in these areas that you just mentioned, do you think we have the two related questions? Is that, okay, these are opportunities, but do you think, or can you see any aspect of these areas where we hold an edge in terms of human resource, infrastructure, or, so that we can come to the international level?
Yeah, I think generally speaking, I think we have largest number of groups in sensing. So second comes communication, and so almost zero quantum computing using NV Center, because we have only couple of qubits. So sensing we can latch onto, and so of course there should be academic industry collaboration, and we should have very niche target and somehow realize that into products. So that should be part of the mission, and I think already there are proposals in this in the NQM.
Okay, good. Vijay?
Yeah, so I'll touch upon one side point which both Apoorva and Mahesh mentioned. This is about which problem to attack to make an impact. There are, of course, one tries to, because we are behind in terms of when we started doing these kind of research activities, especially experimental activities in India, many of the earlier steps have been done elsewhere, right? So unless you come up with a completely new way or a breakthrough there, it becomes difficult to make an impact on the academic side of things, like publishing a nice paper. But having said that, unless you do those steps, you will never be able to develop the technology yourself, which now comes back to the question of being able to do this indigenously. So one can always ask the question, do we ever want to build a quantum computer which is indigenous within quotes? Because even what is indigenous, it's also it's an entire, I think, debate for a panel discussion. Or are we saying that, okay, we are going to be happy buying the machines, and then let's focus on the applications, because maybe we have a bigger strength there. So this is, I think, a careful balance one has to see. And if one decides that, yes, we have to build, Apoorva gave the example of how our rocket technology has finally gotten to a level, but it's 50 years after it was first done. It also means that it has to be done in a different way. It cannot be done in PhD student labs. It has to be done in a very different way. So the corresponding support and the patience has to be there also to let that through. And I think, again, ISRO and the space program is a very good example of that success. And along the sides, there will be many innovations which you will do automatically. But if you don't even start doing that, then there is nothing to actually do there. So that's by balance of making an impact. It can be by cleverly identifying a gap in the world progress and trying to push something there and get a nice paper and international recognition. But I think a long-term impact would be to get all the necessary skill set and the infrastructure to eventually get there and where it matters, right? So if I come to quantum computing, as I was saying earlier in my talk, a 5-qubit quantum computer is useless from the application point of view. But unless I go and try and build a 5-qubit one, there's no hope of building anything beyond that. So within superconducting qubit domain, if I come back to the question now, I think from the in terms of getting to demonstrate a better processor or something, I think it'll take time. So there, the chances of an immediate international impact is harder unless we innovate at the level of even the single qubit. So, and the real question is there room for such research under the NQM mandate? Now, of course, the labs so far have been working, and we've all, had some innovations, but they have not reached the level where they say, okay, here is a new qubit design which actually is better on all these aspects and can serve as a potential replacement. But I think there is scope for that. We all know that transmon qubits have their limitations. As I had mentioned, the fluxonium qubit as something which is emerging. Maybe there is room for a completely new kind of a qubit, where we now know, because 1,000 qubit systems have been built, we sort of now have a better understanding of what the basic building block needs to really make it work much better. So I think there is a scope there, but the question is there patience and investment and time for doing those kind of things? But this could be an academic project which can happen, but it may also require the kind of resources which will come from the investment for pursuing the engineering part of the problems.
So, I mean, I'm sure Chandni will have something to say on that, but before it goes to her, are you saying that, okay, is your answers in the context of the superconducting qubits? Or you are taking into account even the, say for example, NV centers?
No, I was specifically talking about superconducting qubits because, I mean, we cannot reinvent the calcium ion or the ytterbium ion, right? It's already there. Right. Unless somebody identifies a new ion and new set of levels for a breakthrough there, I don't think there is much scope in terms of which is your qubit. There, the innovations are in a different level. And again, unless you build up those systems, we will not have an opportunity to do those innovations. Right. So I was mostly focusing only on where we can do in superconducting qubits. New defect center as well. And this also requires a lot of theory effort.
Right.
We are not seeing that kind of work happening where physicists are thinking about how to invent a new qubit. Often this comes from a group of theorists. But it's also an ecosystem question. If the experimentalists are not messing around with things and feeding it back to the theorists, that they can say, okay, let me think about it and come up with a new idea. So that I think needs to be pushed. Okay. On the other front, I think innovations in miniaturization and cost effectiveness of control electronics and even cryogenic wiring, I think that's in the engineering classical domain, and we have people who work on these kind of things but not in quantum computing. So there may be an opportunity to make an impact on the commercial side or the engineering side as well. I think there are still many open things. Right. In fact, I know that some of the big companies are looking for new solutions, because these 1,000 qubit quantum computers are enormously expensive. And during our proposal writing, Vibhor and I, we all sat down and just started counting. Forget that we don't know how to build a 1,000 qubit quantum computer, but we know what parts go into it, right? So if we start counting what the cost of just buying those parts, it's enormous. It can be a significant fraction of the National Quantum Mission. So then the question is, how do you build that?
Right.
So there may be opportunities there to innovate at that level, and then we can become a provider of that technology for everybody else who's building it at a more advanced level.
Wonderful.
So that's one other thing.
Wonderful. Thanks very much, Vijay. Chandni?
Yeah, so I will be talking about quantum materials. So before we even get to the questions, like whenever we hear this word quantum, I see a lot of students. So it's very confusing, this whole terminology. It's as though because there's a quantum thing going on, you just have to add the word quantum to materials and believe that this is a new thing. So anybody who has attended any solid state physics class might wonder what happened to all the quantum that went into those materials. So it's a very confusing terminology, and I think it's partly fueled by the ongoing developments in other fields. So I tried couple of months back, I was supposed to give a talk at my department, and I was searching about where this word came about. So it was about a decade back in some Physics Today article where this was mentioned. For anything that is not normally spoken about in your solid state physics textbook, any emergent phase is now a quantum material. So if you bring in that perspective, then what is the relevance of all these materials to the technology that the other three speakers just spoke to you about, right? It's very confusing. So I think the same confusion is there in the NQM mandate as well. So the first question was like what are the
opportunities and challenges?
So I think we need to have some clarity on what are the, of course, all these materials are important. You're talking about superconducting qubits. As condensed matter physicists, we can contribute to improving the superconductivity or the transition temperatures, coherence, everything. But we have to be clear, and I don't think most people are clear about this aspect. The same goes with the mandates that are there as well. So it's very vaguely written in my view, which needs some bit of polishing. But having said that, I think there are lots of fields where the quantum materials community, the so-called quantum materials community can contribute. In terms of new materials development, we have lots of groups who are into synthesis or even characterization. And now this gives you a channel to sort of focus your energy to creating a material that is of actual use. So we might have to come out of our comfort zones of working with a particular set of materials or measurements to channelize that and bring it to the different other verticals. Like how would we feed into the other verticals? That is something that we have to think about, while at the same time thinking about topology or other new semiconductor qubit platforms and so on. So all that included, I think that's the way we should approach this.
Do you think on that, because the questions are there as well, but do you think that a national quantum technology mission, because this is a technology deliverables, should materials come in direct closest to the technology, or it should be as a material development which may or eventually may not give to technology? What sort of balance you think we should have in this mission as such?
I mean, I would say it's like 50-50 because we can't really foresee which material might or which platform for even would be the best suited, right? So I think, like I said, it has to feed into the technology. Otherwise, today somebody was just telling me that quantum is the new nano. This is with, what they mean, that last many years earlier, like all the funding was in nanotechnology, so everybody was a nanoscientist. Now everybody is suddenly a quantum scientist because all the money is here. So I think it has to be a balance between what is the pure materials aspect or condensed matter physics aspects to that, and what can actually feed into the other technologies. I think both are relevant, but it has to strike a balance.
Good. Thank you very much, Adi. Umakant, maybe we can.
Yeah, so I'll speak from the perspective of atomic physics and quantum optics community. First, the first question about challenges and opportunities. I will first talk about opportunities in this particular domain. I think we have people with a large experience in working with these atomic systems, photonic systems, and ions also included. I think over many decades there has been a good foundation that has been built in the country, but as you all know, everybody was working in silos, and there has been an accumulation of a lot of knowledge in handling these systems and so on. But now the issue is that although we have capabilities and some of the community members also have direct experience in handling these systems, not only for quantum computing, but this particular technology spans across at least 3 verticals: computing, sensing, metrology, and communications, for example. All these verticals, this particular community, these platforms, they actually span across the various applications. The problem is that we don't have enough capacity in this area. Unlike other communities in the country, like condensed matter community, which feeds into the quantum materials or materials for quantum technologies, I think this particular community lacks the capacity. And in terms of the number of researchers that are existing within the country, and also the amount of human resource pool that is being generated. Now, one of the biggest problems that we face is retention of skilled students and postdocs, for instance, because the postdocs are the people who actually drive many of the research that goes on in the country, right? Now, that is one of the biggest challenge for us. The other challenge is that since we are talking about a technology mission, quantum technology mission, most of the deliverables that are there from the mission are towards developing technologies to the point where they can be utilized for practical applications. I mean, leave aside quantum computing, which is still, even across the globe, there has been a tremendous progress that has been made. For us, it might take a while to catch up, but there are other domains where we can actually catch up. But the problem, again, there is a disconnect between the aspirations of academicians and the demands of the mission in terms of like what kind of work one needs to prioritize as an academician. Because when for example, if I am an assistant professor at this point and I am an expert in developing some of these sensors, it requires sensors or computers, it requires full-time effort from my side and my team's side to actually deliver. But while doing that, there is very little chance that I would be actually doing great innovation in terms of getting the kind of publications that the academic ecosystem demands from me for any evaluation purposes. So there is a mismatch between these two. So I don't know, that is a problem that one needs to think of. Of course, it doesn't matter for people who have become senior enough. They can dedicate themselves to technology development and focus on giving solutions. But for youngsters who have the most energy and enthusiasm and new ideas, it becomes a big challenging task. So there has to be some kind of a balance that needs to be struck, at least from the perspective of researchers, to dedicate certain fraction of time on technology development and certain fraction of time on actually contributing to the community of scientists working in this particular area to gain new knowledge in the area. So there has to be some balance, and I think while we are developing technology, we should also focus a little bit on feeding into next generation technology through fundamental research in some of these aspects. So that is one of the challenges. The other...
in your area, what do you think we can...
Yeah, so on the opportunity side, again, in this particular area, there is a wide gamut of technologies that are utilized: ultra high vacuum technologies, photonics technologies, control systems, laser systems. All these technologies come together. Now, if you look at, I think Vijay or somebody said that if you calculate the amount of money you need to spend in order to set up any of these facilities, I think 95% of the components, out of the 1,000 components that are needed, 95% components we need to import at the moment. We don't make simple mirrors, optical quality mirrors, which are used for these experiments. So there is a huge opportunity for Indian startups and industry to actually develop many of these technologies locally, but for global markets. There is no point in just developing it for Indian market, because unless they are globally competitive, it cannot lead them anywhere. So one has to target global markets, and there is a huge opportunity there as a community, and not academicians, but as an entire community. There is a huge opportunity there to develop these sub-technologies, which the classical technologies that go into any of these quantum technology things. Because at the end of the day, you rip apart any of this quantum tech-based device, the 5% of it, maybe 5 to 10% of it is going to be the quantum core, where academicians actually have their expertise. But remaining 90%, 90 to 90%, 95% is where all your classical technologies come in. Control systems, algorithm development, all this signal processing, whatnot. All these, I think there also we have scattered knowledge spread across the country, which need to be brought together for developing any of these. I think that's
wonderful. Thanks, Umakant. I think all of you have touched upon some points that we would like to discuss. I would start a few questions that's more of a discussion, but at this point of time, I think we will welcome comments and suggestions as well as questions from the audience as well. Please raise your hands. But I would like to start with this point, and maybe to a certain extent, I would ask a particular panelist to start, and then other panelists can pitch in. Say, what Umakant just said, there needs to be a culture shift in the way that we have done research so far. For example, India has many academic institutions, and in the past, for many, many years, we have done reasonably good quality research at a individual level in silos in our own laboratories. Quantum mission actually requires something which is different. It needs a synergy between very disparate areas of research, from core hardware development to packaging, for example. Now, do you think, and how do you think we can effectively get this cultural shift? How do we incentivize and how do we train students for being open to very different type of research, even though the PhD or a background has been in one particular focused area? So your comments on this will be very... Vijay, will you start?
It's $1 million question. A lot of us have been debating this. I think the description of the question itself, I think, is not so straightforward because there are many facets to this. I kept hearing this in many forums that Indian scientists don't like to collaborate. Indian scientists don't like to collaborate. And initially, I didn't think much about it. And then I started, I think maybe about a year back, I started thinking, okay, why? I mean, I started looking at myself, have I really collaborated a lot or not? And I realized that actually, no. I mean, I have done some collaboration within the institute, but outside of the institute, apart from casual conversations, there has not been an active project. Like, Vibhor and I have exchanged samples and ideas, but we don't have a project together where we are thinking about something together. Same for, I guess, Bala. And I was wondering why this is. And I mean, this might be a very simplistic answer, but one thing I realize is that the logistics of doing research is already so complicated for most people that going beyond your institute, you introduce lots of new variables, potentially new regulations and other things that I think it just seems like a Herculean task. So in a very broad sense, unless the ease of doing science in terms of the logistics aspect and the administrative aspect is not simplified, I think these kind of collaborations are going to be harder to nucleate naturally because you're not even thinking that, hey, I should maybe do this. Now in quantum, of course, the community has been small, right? And it's only growing now. That the opportunity itself probably didn't exist so much. But I mean, I've been quite impressed by Vibhor and Chetan's collaboration, and now also Bala included in the team on the kind of things they have been able to do now with this neural network techniques and other things. So, but again, it's within the same institute, so it's easier. To do this across institutes, I think will require that when the overall burden of just managing things goes down, it will improve. I don't think fundamentally, I mean, I've heard, I think we have had this conversation that maybe there's this fear about, whose idea gets stolen and all of that stuff. I don't know, like when I was asking this question, this didn't even cross my mind, but maybe just me. But for the mission to succeed, we will have to put these things aside, because if we start protecting some things while we start these discussions, it's going to be extremely complicated to make progress. And I'm hoping that this somewhat forced opportunity will lead to some good examples of how this can be done.
So the one question is force, and the other question is incentive. So I would like to listen to maybe Mahesh. If you want to have this collaboration, whether it's a multi-institutional, interdisciplinary, is there a way you think you should incentivize such collaboration so that people can come spontaneously rather than worrying about, okay, whose idea goes where?
Yeah, one incentive is already there in NQM, I think, the thrust to translation, right? I think it will force people to collaborate, because when it comes to translation, you can't leave halfway. So you can't say that I have published one paper and that's my job and that's done. So you have to do the rest of the things, and on which you may not have expertise on all the things that you need to bring out a product. So I think that is a very good incentive. So you thrust translation end to end. So
you're again saying thrusting. So thrusting is not incentive.
You are incentivizing by funding the right. Where is the correct? Yes. So I think that's one way, and maybe others may have others.
Apoorva, would you like to add to that point? How do you incentivize other than thrust?
I mean, in the NQM mandate, the fact that you can only submit a proposal if you come together is well, you can see it as forced, or you can also say that, well, this incentive is that if you want money, if you want funding, this is the way to do it. And the thing is, at least in this particular example, there is no other way. There is no single group or even a single institution to have core competence, sufficient core competence to deliver completely in any one area. That's just the situation, right? So we have to do this. It's hard, but we have to do this.
Point taken. Apoorva, do you have any comment on that?
I will go back to the point which I mentioned earlier, which is sort of the same thing. How do you make the preparedness level of the future generation in this particular area? And here we have seen what was put in place in both nuclear technology and space technology. It is not a question of making an advertisement and asking everybody to apply and then making a selection. Because most of the time, the people who are the best suited for this kind of work don't even bother to apply. So what was put in place was collecting a mechanism to extract people who have real passion for this field. That is the criteria. Whoever wants to jump in must have real passion for the field. And what was the mechanism which was put in place? That many of them were handpicked. Nobody went and advertised here, there, etc. who want to do this. They were handpicked. What were they promised? They were not promised some great salary here, there, etc. And even now, those who want to make a lot of money, let them go to finance, let them go to IT industry, whatever it is. It's not the motivation for this kind of field at all. The people who have real passion for this field, they need two things. One is the freedom to pursue their passion. And the second thing which was removed from their daily burden is giving them a promise that if you want to select this particular field as your career, you can do it. Nobody is going to just discard you after 6 months or a year or whatever it is. You want to spend your lifetime doing it, the opportunity is there. And that guarantee makes a whole lot of difference in our society. That yes, you have the freedom to pursue your passion and you have the opportunity to devote your lifetime if you are up to it.
Good.
If you give it, you will find people. Maybe it will start with small number, but you will find people and they will actually produce something which is relevant.
Okay, so I think we can take a quick audience comment there. One and then two.
So how do you think of if industry is going to give you anything, they are going to ask for a lot more and take a lot more. So all of you are academicians, but industry I think is required in this NQM. So
Of
how
course.
do you think industry is going to help?
Umakant, do you want to take this?
See, I think there we are a bit challenged in India in terms of industry participation. There has not been a tradition of active industry participation in joint development of many technologies in the past. You may know that most of the technologies we import for many of the things. But now this is a good opportunity to get industry involved in it. As I said, 90 to 95% of the modules in a particular quantum technology device is going to be classical stuff in the sense, I mean, there is nothing quantum about it. It's standard engineering, electronics, mechanical, and whatnot engineering, right? I mean, there is an opportunity to actually start interacting with industry. And already in this quantum mission, there have been quite a few such industries who are willing to be part of it. In some way or the other, they are showing interest in joining hands at some level for in development of these technologies now. I think there is a shift that is taking place slowly. It's not going to happen today or tomorrow or by some some big mandate or thrust, but it will happen slowly. Yeah, it will take us to become Atmanirbhar in this quantum technologies maybe 20 years, 25 years, but we have to start somewhere slowly.
Yeah, so my question is, when someone writes a proposal, so maybe he or she gets the proposal, then maybe in the meantime, someone loses the interest to deliver the promise that was written in the proposal. So as a student, when we generally deviate from our target, there are our mentors, our professors who correct us. But when a professor is not hitting the target and maybe he or she is deviating from the field he was promised to deliver, so who are there to keep the track of it, and what is the body like, who is there to
monitor.
And who takes
maybe
that accountability?
I think most scientific proposals or projects that are funded, there is some monitoring committee, which does periodic reviews of the progress of the project, and accordingly the project is either kept alive or the funding agency just chokes the funds, in the sense they can shut it down anytime. But you're also right that we as scientists or professor, whoever is submitting any proposals and gets funding for executing or giving those deliverables, we have to be honest with ourselves to put in honest efforts to take the project to the logical conclusion. Of course, there can be some setbacks during the execution of the project, because there can be many things which can be unforeseen while executing the project. Because finally, these are R&D projects. I'm not talking about the NQM, but in general, R&D projects. NQM, there are clear-cut deliverables, and for many of them, the technology is already well known. So the risks in terms of the science involved is very less in many aspects. So, yeah.
And if you don't hit the target, there's a very high chance maybe Vijay can say what.
Yeah, I mean, I was trying to understand the motivation behind this question. It's like हमको तो professor से डांट पड़ती है, professor को कौन डांट लगाता है? I've been only in the system for about 10 years, but so there are monitoring bodies, but I would also add that it probably needs to be much more stricter and clearly defined to do this a lot more properly, which basically means that there has to be a reward for performers and there has to be some kind of prize for non-performers.
Absolutely.
When that doesn't happen, the motivation to perform slowly goes away. So I think this definitely needs to be strengthened. I think many of us in various documents and all have mentioned this aspect as well. I'll go back to the previous question very briefly about the industry aspect. See, when it comes to developing new technologies which have to be commercialized, as Umakant was saying, there has to be a market, and it has to be a reasonably big market for that company to to succeed. One can also create special purpose vehicles or something which are only providing that technologies, let's say for the mission's use, but then it will be shut down. And here I think a model which allows the scientists and the end users who know about those products to certify them. I think a big problem you often hear is that even when there are alternatives to an imported product, often we hear that the Indian version is not up to the mark. And there's a huge risk aversion. I mean, see, the thing is, when I'm setting up my lab and somehow I have convinced somebody to give me 5 crores, I don't want to risk buying a 2 crore worth of equipment from somebody I've never heard about. Because if it doesn't work, my career is over. The institute is not going to be generous and say, oh, okay, koi baat nahi, right? So I think a mechanism where new startups which create a product are tested and certified by the experts in the country, I think will help in a long way. And where the expert also doesn't have to risk their career or project, that they will be given this product for free or paid for by the mission. They can test it. Tomorrow somebody develops a dilution refrigerator. I would be happy to take that dilution refrigerator, install a qubit in it, test it, and say that yes, this works as well as any other system in the world.
Absolutely.
And then, if someone in the community certifies it, then people will be a lot more, acceptable to go and buy it for their own. So that needs to happen. I don't know. There's a mechanism. In fact, I think we probably also mentioned this in some of the documents earlier. But this needs to be done because there will be people who will try to develop products, and that certification and trust building has to be done. And it has to be also developed at a level that it is internationally competitive.
If you're looking at that long-term vision, then it needs to be a internationally competitive product. Akshay?
Yeah, can you hear me? Okay, so maybe it's a more complicated question. So what is the role of foreign academics in the NQM specifically? Because so recently I was in the UK, talking to some academics there. Now sample exchange to China is one way. What that means is you cannot send samples to China, you can receive samples from them, right? I'm pretty sure in a few years, India will be in the same sort of position. So until then, do we leverage the excellent relationships that Indians have with all these countries, get the know-how or like collaborate with them to make this mission actually work, or do we get all the expertise, everything developed in-house, like in India?
Okay. In the Chandni, I think it comes close to you.
But I think he's asking for a more specific NQM related answer.
No,
maybe Umakant?
I think this question I would say is more general, especially when you are talking about developing some high-end technologies of the future. It need not be NQM related also. It is valid
beyond
for
NQM as such.
It's beyond NQM. So I would go with a simple rule. I mean, as long as there is academic collaboration, exchange of ideas, as long as you remain within the boundaries of intellectual property sharing, and basically it all boils down to intellectual property, right? I mean, what you are bringing to the table, what others are bringing to the table. If you are clear about what IP each one is bringing together, I think there won't be any conflicts, commercial conflicts in that. But at an academic level, I think people are free to collaborate, I suppose. I mean, as long it all depends upon personal relationships.
Okay. One more question or two more, Max.
There's just a side point. Maybe this is not directly connected, but it was made fairly clear to us that if a foreign researcher is looking to get money from the NQM for some research, that's not going to be possible, to the best of my knowledge. Any such collaboration, if it is under the NQM umbrella, it has to be a bilateral thing where they get their money from their own agency and only the Indian partner is going to get money from the NQM. This may or may not be ideal, but in some way it may be also fair. We have limited resources. But we will also start seeing that many countries will slowly not be so open in collaborating in all aspects. That's going to happen. It's already happening. So wherever the things are still open, or with countries which are at a similar scale at which we are working, so that we can work together to make progress to catch up, is I think is definitely possible.
I mean, not only between academics, but even companies which are selling things for us to develop some of the things. I get a feeling that there are unnecessary and unjustified reasons for delays, in that sense of extremely long lead times.
Let's keep it within the National Quantum Mission.
Hello. Hello. Am I audible?
Yeah.
Okay. So thanks for all the nice talks today. So I have a question more on a technical level. So My question is the proposed quantum computer that has been proposed so far. So what is the basic qubit architecture? So is it just superconducting qubit, or what is the prospect of a, say, hybrid quantum system for building the quantum computer? And why not other qubit platforms like based on photonic cavities or semiconducting qubits? So what is the
Maybe Vijay Chandni can take this.
Yeah, so I think maybe you've misunderstood. I talked about only the superconducting proposal because I was talking about my work. There are many proposals. I mean, there are proposals on ion traps, there are proposals on photonic qubits, there are proposals on semiconductor-based qubits. I was only talking about some details about what the superconducting community has proposed. So there are many proposals, and then the selection committee will decide which projects to take forward.
Chandni, do you want to add anything to this? Achha, fine. Yeah.
So thank you everyone. I have a question to Professor Apoorva, but anyone else please feel to join in. So this is again about the geopolitics of technology in general. Like you mentioned that there were some watershed moments where technology was in the hands of the scientists, like the Manhattan Project or Homi Bhabha leading the nuclear efforts here in India, or Satish Dhawan. So those were very specific moments where the world was in a very different place. It was a highly bipolar world. There was war, and these technologies came out of it. What do you think could be an enabler, not an unfortunate one like that one, but what kind of situation would be an enabler in today's context, in India specifically, that can allow this transfer of control to the scientists?
Apoorva?
Somebody else can answer. I have answered my own way. So.
Can you just repeat the question? What's the thing in
I think it's I think he's asking that there were specific geopolitical conditions around that time which enabled these kind of programs. So he's saying that not that kind of what can we do?
In today's context, when we talk about when Apoorva said that.
It's on, but I don't know. But it was working fine when it was here.
Yeah, I think the battery might have gone off.
Maybe can we exchange?
Yeah. No, I think that we got the gist of the question, right? I mean, I think Vijay said it correctly. Actually, before we go into that direction, I have one myself. I wanted, because we don't have too much of time, but I wanted to have one. This is an important question. And I would like, the panelists who wish to comment on it, maybe. See, at the end of the day, the quantum mission is supposed to be run in a little different way. Apoorva at the beginning actually said that the quantum mission, it has to be run by the academics, because look at what Satish Dhawan did, look what Bhabha did, look, the ISRO thing came up. So, quantum mission is not supposed to be like that. It's supposed to be what DST wants is a Section 8 company. It's supposed to have an independent structure. Now, what I would like to know from the panelists here is that, do you think this is how a mission which is going to give a technology, like what ISRO does, like what BRC does, should be run? Or do you think it should be run by a standard DST project, which, I mean, we are asking institutes, academics to take the lead, but we are getting Section 8 companies. Do you think this is the right way to run it? Is this ISRO? It's not ISRO model, right? Or it's not a BRC model. So your opinion or your comment is to a certain extent connected to the question also.
I think that's a well articulated.
Yeah. So what do you think? I'll come to you after this, Tabla. Apoorva.
Well, two things which I kind of extracted. One is that there are various geopolitical considerations. They are always going to remain there, okay? Just they disappear for a few years, don't be fooled by it, they will come back. So we have to learn to live with them and find our solution, that we are not overly dependent on something which is not in our own control. The second thing is, well, how should this National Quantum Mission be run with a Section 8 companies and that kind of architecture? I don't believe that making Section 8 companies is going to do the job in a proper manner. because they cannot deliver high technology. That is essentially the point. Whatever is well established, yes, Section 8 companies will be able to organize it and deliver it, but whatever is open-ended, that is not the job of Section 8 companies. And that is where the structure which is there in, say, BRC or ISRO, it's different. It is not a Section 8 company. The Section 8 companies would not have been able to do that kind of a job. And so if you want to say that, yes, National Quantum Mission is oriented in this direction, fine. But then don't ask it to deliver on uncharted research topics.
Okay, good. Any other?
So I see what Professor Apoorva Patel is saying, but I think government is looking, I don't know, maybe some people in the government are looking at two aspects. One is like HAL has delivered LCH, right? So it's an organization, it has delivered. It was slow, it is, I think, decade slow, but finally it is there. Okay. Secondly, how to find Oppenheimer? So
I'll just add one point to this discussion, that I think something that Apoorva mentioned in the beginning is about handpicking the right people. So to me, for any mission to succeed, whether the structure is Section 8 company or an ISRO model, it's the people that's most important. So how do you handpick? I mean, there is some person sitting over there and handpicking. Now that person can handpick only the people that he or she knows. So this sort of a model where you're initially giving some money to a lot of people would enable the NQM, the current NQM model may enable us to come with a structure that can work, or maybe find the right people who may be then able to lead the mission. So in my view, this 5 years, whatever is being said about, that's just the beginning, and then what happens after that is possibly what will define whether we can follow up the success that we have had with BARC and other national organizations.
Umakant? Yeah, so the model, which what I understand on which this NQM is going to be executed is something which is going to be in between the ISRO model and the Section 8 company model. I think at the end of the day, most of the technology development and all is going to happen in the individual's lab. It is not some physical building where all the researchers are coming together and then there is one Oppenheimer on top or whoever it is, and then everybody is working towards one single goal together. It's going to be different. It's going to be something in between this ISRO and Section 8 company model. I mean, Section 8 company model, as long as if it gets money from private sources, then things might be different. Yeah.
Dhavala, coming.
So I just want to add quickly. Yeah, I think at the end of the day, I think the model doesn't matter so much. And the Section 8 here is, at least the way it is being seen right now, is really an administrative logistics kind of body. There was in an earlier round of discussion which looked like everything will come from choosing the hubs. Now that could be compatible with handpicking. For example, if the hubs were handpicked and then they were given the mandate to go and figure out which are the how to form the teams. But I think it's not so practical and realistic in the current sort of spread of talent and expertise in the country. I think the ISRO or BARC model is really out of the question, even though at some early stage of the DPR development, an Indian Institute of Quantum Technology was being formulated. But if you just ask everybody who submitted a proposal, would you all leave your current job and go to a new place to do this? The answer is very clearly no. I don't know what kind of motivation could have been given ideal thing. But then again, remember that, this is probably simplifying ISRO's mission, but ISRO's mission was to make a rocket and send it to different levels of space and then ultimately to the moon. The quantum mission is much broader. There are many, many different targets. So would you create an institute for every such thing, or you create some? So there are examples. The IQC in Waterloo was an attempt to bring all quantum under one. But the mandate and the requirement or the deliverable time scale is much longer. Same goes for ISRO or BRC, right? Yeah, exactly. It's just an open-ended thing with some milestones. Here, things are a lot more tight. And the Section 8 company model specifically, I mean, at least to how it has been explained to us, it's actually to make things simpler, where the government actually takes a step back. So the model is that the DST will give the money to the Section 8 and then leave the Section 8 to manage. And the Section 8 will have a governing board, which should have a lot of scientists. So in that sense, some things are under the control of the scientists, and they can probably also take decisions based on the progress. But I don't think it's completely disconnected. For example, suddenly if one institute becomes the hub, they cannot start saying that, okay, your project is done, I will take all the money. It's not possible. It has to be done in consultation with the DST and also the mission governing board. So it is really a model to manage such a big thing in a way where there are fairly diverse topics. But as Umakant was saying, Section 8 company could just be a virtual entity. An institute will have to set it up. In fact, this was emphasized that if tomorrow IISc becomes a hub and creates a Section 8 company, the Section 8 company is not IISc. It's an independent entity which IISc has facilitated to set up. IISc's own interests and desires cannot and should not influence the working of the Section 8 company. Now, in the reality is always going to be different, but that's the model, that the Section 8 company then has the independence to take those calls and some amount of flexibility in reappropriating funds, because everything doesn't have to go back to DST. I mean, this is my understanding. In practice, this is harder. There are, I think, good examples where Section 8 companies have done work efficiently, others have struggled. It's also because I think many institutes who have not set these things up, they don't know. There are also seems like conflicts of company rules versus institute rules versus DST rules. So these things have to be ironed out. I think the ICPS mission has given some experience. So this will go a little bit more smoothly. Okay. But remember that now becoming the hub is an enormous responsibility and a lot of work, and doesn't necessarily give you unilateral power to do whatever you want. So, be careful before wanting to become the hub.
Thank you, Vijay. I think Bala is going to, 2 more minutes. Okay.
I will add one more point. It's
we'll get to her.
Face this thing towards you.
Yeah, the organization of all this NQM hierarchy, etc., is not very clear to me, so I don't want to say too much about it. But there is one point which I want to make, and which is very important in the context of our own country, that many type of dedicated structures have been set up in our country to get the deliverables, so to speak. And examples are CSIR labs or DRDO labs, etc. And they were given specific targets and they delivered on those kind of things. But that had only a limited goal. If you want to continue future developments in this area, that is not sufficient. And the obvious signature of what happened in those dedicated institutes is they disconnected completely from teaching. There was no way to pass on their knowledge to the next generation which will take up the job. And this is an essential point which will be required for any technology which has to continuously develop. Unless you know how to teach the subject, you have not understood it properly yourself. That's a very simple test, and it holds. And that is where the input for the future of this particular area will be, and somehow we have to make sure that that connection exists.
Thanks, Apoorva. Dhavala.
Mike. The batteries.
Better.
Why don't you pass this? By the way, the YouTube comments are terrible. about the audio?
Okay.
Yeah, so I had two questions. One was continuing on what Umakant was commenting earlier, was that do you see in the Indian academia or scientific area, do you see a cultural shift coming up in a few years in terms of students, where in the West we don't see PhD students freaking out about becoming a faculty, right? So do you see that coming out as one of the spin-offs of NQM, where you'll have enough grad students, you know, translating into industries and jobs like this, where they're still in the scientific area, but you know, it's as of now, it's like people who come to do PhD and then postdoc and then faculty. That's the only larger.
Actually, there is slow.
Yeah.
Not working.
No, this works. This works.
Is it working fine? Can you hear?
Can hear? Yeah.
Okay. So I mean, I can say that there is a slow shift in in the mentality of students these days. I've already seen a couple of, well, at least 5-6 students across the country who are thinking of going into setting up startups. So that is one direction where the students are thinking about going into. My own 4 of my students have set up a startup, and there are other institutes where students are actually seriously thinking of taking the startup route instead of taking the standard route of going for a postdoc, then looking for an academic job or something like that. So that shift I am seeing.
Yeah, I can speak from my personal experience. So after my PhD, academia was a second preference for me. I wanted an industry job, and I tried really hard to find something in India, and I sort of failed. Right, and then I went for a postdoc. So, but I think now the situation is much better. So the problem that I had was all I could find was computational jobs, not really a hardcore experimental job. But now the situation is much better. We have lots of opportunities now for students which are experimental. May not be in the hardcore area that they've done their PhDs, but they still do find jobs where they use their hands.
The one more thing was that all of us, or all of you all, before the NQM, there are certain research goals and research dreams that you all pursue. What about those? In the race of NQM and mission and trying to do 1,000 qubits or whatever it is.
You're saying kya se kya ho gaya?
Right. I mean, aren't we hitting the Indian scientific academia or the backbone in some?
So, okay, actually, I mean, I probably have a good answer for this, because I did have a side of me which was not to be just a pure academic. I always had a thing for developing technology, even though my own experience is not, in terms of training has not been the case. So when I came to India, I was pleasantly surprised that there was even opportunity to get $1 million to set up an academic lab and facilities which would allow me to do the kind of research which I was interested in doing. And the goal was simple, work on innovative problems which are not going to lead to building a 1,000 qubit quantum computer, but maybe try for breakthroughs in the building blocks and do some associated interesting quantum physics experiment using these systems. And it just happened that by the time I had my first set of results, that the Quest program started and the whole quantum craze. So it was very nicely timed. And going forward, I would like to keep a balance on these two aspects, but it would require 2 different types of teams. A smaller academic team, which is working on cutting edge new ideas, crazy ideas, blue sky research, and a technical team which doesn't care about publications, which can move the thing forward. And if managed properly, they will feed into each other. And because engineering innovations can lead to new breakthroughs in science as well, because you can do things. So that would be the ideal goal. But I don't think the NQM is forcing anybody to leave academic pursuits. And but I can see why you're saying that, because the community is small and somehow everybody is feeling the pressure that we have to contribute, right? So.
Yeah, so it's related to the last question. As Umakant was saying that the research goals will be most likely will be attained in a lab rather than some building in which all the researchers are coming together. My question is, the lab goals are, how overlapping are the lab goals versus the NQM goals? And also, the know-how has to be transferred, whether forced or incentivized, as you were saying. There has to be a transfer of knowledge freely between few groups. How is that going to take place, and who is moderating the know-how? Because that can be conflicting with the individual lab goals as well. So
I can tell you about my own journey and experience. So can you make a short answer? Yeah. See, I have been working in this field for the past 25 years or so. Only now quantum technology mission and many other programs have been recognized. So it actually doesn't make much difference for my kind of research, because it is just a continuation of what we have been doing. So, and of course, one has to dedicate certain portion of your research for doing fundamental physics and training students and getting PhDs out. So that is up to an individual researcher's management skills on how they are going to manage these different aspects.
Your question is about what if multiple people are doing the same thing. I think the way NQM, as I understand, is that if there are multiple people who are doing the same thing, they'll be brought together, right? That's at least the idea that, yeah.
All right. I think I'll just quickly want to conclude this session. Just one point of importance is that, to me at least personally, NQM is an opportunity, and it's an opportunity beyond developing certain technologies. Maybe tomorrow we will have a quantum computer, maybe we will have a fantastic quantum sensor, or communicate through quantum internet across IISc or everywhere else. But I think what NQM in a global manner would like to achieve at the end of the mission, or somewhere down along the mission, is filling a lot of technology gaps that we have. Gaps in manufacturing, gaps in expertise and knowledge, know-hows, and gaps in every other scientific research that we do. Today, equipment, what Vijay had said, making a dilution refrigerator, or even buying a voltmeter or a lock-in amplifier, we have to do it from outside. Maybe, just maybe, in 5 years or 3 years or 5 years down the line, some of these should be possible to have right here. Not all, but some. Today, if you are making a filter, simply RF or gigahertz filter, you have to pay $375 per piece, and to get it from either Germany or whatever it is. Maybe tomorrow we will get it off the shelf somewhere in Mumbai. So I think at the end of it, the goal of NQM is beyond certain specific technology mandates which the NQM has, and we can have larger opportunity for students to get into scientific jobs after their PhDs. So that naturally becomes a very lucrative source of, career choice in the longer run. So with that, I would like to thank all our panelists. They did a wonderful job. Thank you very much for your insights, and I wish all you the best. Oh, am I supposed to give it to them? Sure. All right, welcome. Thank you very much.
A lamp of a different kind, okay? I'm sorry. They like my idea and they stole it.
You want to take a picture or something?
They're doing it.
Are you taking the picture?
Yeah. But it's a different model, okay?
Apoorva, sorry you. No. It's okay. I'll take it later. No, it's okay. There.
Yeah.
Thank you very much. So this is this is for you.
We have it. You can just have an exchange.
This. So with that, that's a very engaging panel discussion, and I hope all of you learnt a little more about the structure and operational modalities of the National Quantum Mission, and of course the challenges and opportunities therein. And the next event we have is perhaps the most important of the evening. So I request Professor Apoorva Patel to deliver his keynote address to conclude the symposium and share his experiences, thoughts and vision for all aspects related to quantum technologies, education as well as research. Apoorva, you can use the collar mic. That's this is yours. You want to come? HDMI is there. There is an HDMI port. Yeah. Okay.
There's HDMI on this side. Okay, that's it.
It should detect, or do we have to turn the projector on? We have to turn the projector on. Is it too far? Yeah, let's start that. You can wear this, and that can
This
be
also?
a bit below. That's for the web streaming, I think. No, this you can wear above.
Okay, so now how do I get this mirror thing? Is it come?
Yeah, it's coming.
Okay. Hmm? So how did I get here? That is what I'm going to talk about. Not any more lectures and policies or whatever it is, but what brought me to the stage where I am, and probably it will give some idea about what the future holds. So this is the title page of my thesis, submitted in May 1984. And this was what I put in as dedication. It's a well-known slok from what is called the Guru Stotra. Ajnanatimiraandasya jnananjana shalakaya chakshurunmilitam yena tasmai sri gurave namah. And for those who don't understand Sanskrit, there is a translation. Salutations to the noble teacher who with the collyrium stick of knowledge has opened the eyes of one blinded by darkness of ignorance. Forgive me for becoming a little emotional, but this has been the underpinning of what I believed in and what I would like to pursue. And this, when I put it up in my thesis, the person who was most curious about it, he was my thesis examiner, one of the thesis examiners. And when I started my thesis defense, the first thing he asked, how did you get this shloka, particularly the Devanagari script, in the thesis printout? And it was nothing complicated, it was just a Xerox machine trick. But in those days, I had to write home, tell them to send me the correct clipping by post, and when it arrived at Caltech, stick it on a piece of paper and then do a Xerox copy. And then the second question Feynman wanted to know is, who is this guru? And I had to explain to him that it is a generic label, doesn't refer to any particular person. Those who can teach you something useful at any stage in life become your gurus. The guru doesn't have to be perfect. But what is important, provides the correct inspiration at the right time and the right place. That's it. That becomes part of your life. So, well, that is where things will happen. There have been many turns and changes in my life, inspired by some people in some ways, and I will recount some of those things which left a permanent impression. So first, my parents. They didn't have food to eat. They didn't have proper clothes to wear. Paying fees to educate was out of question. But by generosity of somebody, they donated and gave them fees to study. In a sense, they kind of rebelled in their environment, that they wanted to study. Family background was not there. But to credit of my grandparents, they let them be. That yes, they have some drive, they have some motivation, go ahead, we will not demand anything from you. And that's how they ended up getting educated, and my situation was much better. I didn't have to undergo any of those kind of struggles. But my parents' experiences left an impression on their lifestyle, and indirectly on my lifestyle as well. So, well, I didn't have to struggle, but the first unusual thing which I remember is my parents discovering that something was wrong with my eyes. That is because I have a squint, not very visible, but it is there. And when I was about 2.5 years old, they noticed that I was not keeping my head straight. I used to look at everything with a little head tilted. And they tried figuring out the reason for it, and understood that something is wrong with my eyes. So, well, it has to be investigated, and they decided to take me to a ophthalmologist. Nothing available in my neighborhood where I grew up. So we went to Mumbai to an ophthalmologist and asked them to investigate what is wrong. And ophthalmologist said, well, they did some tests, whatever it is, observation, put some eye drops inside, etc., checked, etc. But then they said, no, we have to actually check the vision individually, eye by eye. And then there was a board, standard thing with all letters written from big sizes to the small sizes. And they asked me, can he read? Now the fact is that my mother tongue is Gujarati. I had learned how to read, but the board was in English. Can he recognize the letters? And I surprised both the ophthalmologists and my parents, saying that yes, I can read. Now, how did that happen? The background is that we used to get a English newspaper, Times of India, at my home. And I used to look at the pictures and cartoons, etc., and some letters as well, and used to ask my mother, what is this, etc. And she used to say that, yeah, this is a picture of this, and this is a picture of that, and this is letter this, it is called E, and this is called F, etc., whatever it is. And somehow that has registered. Some people now call it photographic memory. You don't understand the language, but you know exactly what you are looking at. And so I read the board. One eye, right eye, everything from top to bottom, all the letters I could identify. With the other left eye, only the first letter I could see, nothing beyond that. So then the doctors, now confident that something is there, they checked whatever was the cause, and they discovered that it was a congenital defect. That the image of a visual object is supposed to fall at one particular spot in the eye, so-called the yellow spot, and it was not falling there, it was falling a little bit on the side, and where it could not generate the correct input signals to the brain. And that was labeled eccentric fixation. That's the medical terminology. And I accepted that. So if anybody calls me eccentric, doesn't matter. I am eccentric. And then the question came, what is the treatment? So the doctor decided that this eye has not learned how to see properly. Maybe you shut it down for some time, and after taking some rest, it will wake up in the correct state. Okay, so that had to be done. All kind of stuff. That's why I started wearing these glasses since 2.5 years old. The first step was to put a transparent glass in the eye which I can see with, and an opaque one in the other one. And that didn't work very well, because opaque one will block this region of the specs, but what about the sides? The light was still going in. So it tried, didn't work. They said, no, it has to be something better. So next step was to take a handkerchief, fold it, and put it on one of the eyes so it remains permanently closed, and go about while doing my whatever course, I can't call it course, whatever I did it as some 3-year-old, 4-year-old, etc. Doesn't matter. It had some effect or not, I don't really know. But that is fine, so I carried it around with one eye closed with a handkerchief. Then after a few months worth of experiment like that, the doctor decided that now it has to be woken up, but it cannot be woken up fully, so it had to be given light, but only in a restricted amount. So then the one glass remained whatever it is, but the other glass was replaced by a red camera filter. And again, well, I lived like that for some time, and it kind of became routine. But imagine this kind of a situation when I am playing with other kids my own age. I developed lot of names. Everybody made fun in their own different terminology. And somehow I grew immune to it. On top of that, my whatever school friends or kids, not yet school, even before that, kindergarten, they discovered that my parents had an intercaste marriage. It was registered in a court, but no ceremony. So some more labels came with that. And well, some of them I couldn't understand. So I used to go home and ask that other kids are calling me by these names, that name, so what does it mean? And somehow my parents also felt embarrassed to answer me. And sometimes my mother would just hug me and tell me it's not important. And that became actually a gift. That I can shut off my mind completely while being right in the middle of a group to anything which is not important. And it's a gift which actually I am very happy with. Many people may have seen that I'm sitting in the middle of the group, but where my mind is, no idea. I switched off. And that is how the disadvantage turned into an advantage. Yet another story. It was time for me to get admitted to school. I was 5.5 years old. My parents decided that I was going to join the primary school in the neighborhood, government public school, and I was going to study with all the kids which are in the neighborhood, whatever it is. But they decided that they are not going to come to admit me to the school. So they wrote a note, a little chit to the principal saying that he is now 5.5 years old and he can get admitted to the school. Please do so. And told me, well, take this to the principal. I was not very happy with it. So they put some dry fruits in my pocket, little bit of a bribe, some cashews and raisins and things like that, and told me, you go, you will be happy. That didn't help. So then my younger sister. She was 4 years old. She told me, "Chal bhai, apne beh jaiye." And she grabbed me by the hand and took me to the school. I gave the chit to the principal, and the principal then decided to check what I knew in terms of my background. So he asked me to read something, I did that. He asked me to write something, I did that. He asked me some addition, multiplication, the mathematical tables, etc. I did that. And so the principal said, "You already know all those things. You are not going to go into the first standard. I am admitting you to the second standard." And so I got admitted 1 year ahead, and the principal, whatever he saw him, he had the authority to do that, and that was fine. So we came back home, and my sister gradually announced that now he is in second standard. And that's how my primary school started. The classmates I had, they were all the local neighborhood people. Most of them were from the working class. And by the time I finished primary school, their parents saw that now they learned how to read and write. Their school job is over. So they were immediately taken out from the school and put in the business. Some of them were just helping their parents run something in shop, little errands here and there. Some of them with these push carts selling things on the street. And well, I went to higher school. They were taking up this kind of job, but I used to meet them walking on and off on the way to the school. And yeah, now I have reached a different level. Those people have also progressed. Now instead of having some little push cart, they have their own little shop on the road, better off in terms of their living standards as well. But when I go home, I meet them. They're still my friends. And they are also happy to see me. So that is well, another kind of connection to the background that I have. And well, there are many things which happened afterwards. I did all kind of activities covering all kind of topics which I came across in school. I don't know, I had the energy to do everything, whether it was relevant or not, didn't matter. Of course, I was good in studies, so there were topics like debating and essay writing, etc., there was all fine. But then there was music, classical music. The only place which taught it was all-girls school. And I wanted to learn how to sing classical music. Fine, went to all-girls school to learn how to sing classical music. There was an evening class for typing. I was not going to become a secretary, but I wanted to learn typing. So I learned how to do the touch typing with 40 words a minute speed. And it became useful when the computers came along later bit. But that's another adventure. I joined NCC, left, right march at 6 o'clock in the morning. And we were in school, so we were not given the big rifles. But I learned at least how to shoot the 202 bore rifle. 303 is the standard bore which is used by the military, but I learned how to shoot a rifle in the practice ranges, whatever it is. And well, all other kind of things I ended up doing. But fine, that was a kind of different, what you call, source of energy, and I had the time and the capability to cover all that. Because in the school, I didn't have to study much. I read it once and it was over. No need to repeat it. And so, at some stage, my mother got worried that he's not getting enough competition. There's so much capabilities, but he's in this environment over here and it's not the right thing. He should be put in a better environment. The better environment in those days means going to a boarding school, somewhere where you get special training, etc., etc. And there were some arguments between my parents, and of course I was present. And my mother suggested that he should learn something better and go to a more advanced school to develop his talents. And my father just made a flat statement કે હીરો હશે તો અંધારામાં પણ ચળકશે ને કોલસો હશે તો ગમે તેટલો ઘસે પણ ઉજળો નહીં થાય. So to translate it, if he's a diamond, he will sparkle in the dark. But if he's a qubit, it is not going to become bright. That was the end of the story. I studied where I was, in that Gujarati medium school, doing whatever skills I had picked up, and I was not unhappy with that. And then come the next stage, finish school. In between, lot of other things happened, but that is not connected in the same way as my change in directions. I did a lot of what you call unrelated activities with whatever my parents were involved in at that particular stage. But in the college, I was going to become a doctor. I was a top rank holder, so I was free to do whatever I want. And that was a popular choice that good students, well, they will go to the medical school. And never got any other thought until the whole thing got over. I got admitted to medical college. Studied there also for a couple of months, whatever it is, the initial part. But at that stage, I got a lot of suggestions from my teachers in the college that you are a bright person, why do you just want to become another doctor? And what I enjoyed and what my teachers also noticed was I kind of liked solving puzzles, all kind of mathematical challenges, etc. I would sit down and solve the problems to the extent that if I go after a problem, everything else is forgotten until I found the solution. And my parents had noticed that also, and they never used to bug me that he's solving a problem while everybody else had their dinner and finished, etc. He still wants to solve the problem, give him a glass of milk and he will finish the problem and then come and have his dinner. Nothing wrong with that. So my mother took me to the physical research laboratory in Ahmedabad, that is where I was studying, and that was a reputable institute where scientists used to go and work, legacy of Vikram Sarabhai. And she asked whatever people she could get hold of because of the suggestion from my teachers as well. They were from Xavier's College in Ahmedabad. That they said the best person to talk to is the deputy director, Saurabh Pandya. And he went and talked to him and said, yes, he likes to study science, he is good at it, let him study science. And my mother said, yeah, we have no problem with that, he can study the science. But Saurabh Pandya insisted that the answer comes from me, not from my mother. So he told me point blank, look, this is a different field. You are not going to make a lot of money, but you are not going to starve either. And you are not going to get a social status like a famous doctor or a whatever businessman, etc., who is involved in all kind of things, and people, whatever, give them a prestige, etc. You will be more isolated. Is that okay with you? And my answer was, no problem. So I was 16 years old at that time, and that no problem is still fine, no regrets. And so what to do? So all the admissions were over, but at that time the IITs had an option that you can get a direct admission based on the rank in the university. That option doesn't exist anymore. But the courses are already started, but this option was still open. So I applied to IIT Bombay. Why Bombay? Well, closest to the home. And only one branch, physics. And nothing else. And it got accepted. I joined 1 month late over there. And that's how I ended up becoming a physicist. But there were some caveats along the way. First thing is, all my studying was in Gujarati. And IIT education started in English. So landed up first couple of weeks learning all kind of things. And I remember one example, some exercise in geometry, some property of an isosceles triangle. I didn't know what an isosceles adjective meant. So I got a dictionary. And dictionary I looked up that isosceles triangle is a triangle where two sides are equal. Fine, now I understood the problem and now I found a solution. And that's how I learned many of the technical words with a dictionary. And yes, picked up language English in a different manner, but that is fine. A lot of interesting things happened in IIT as well, and that's another story, but I ended up getting the gold medal. And this kind of not knowing technical words in English remained with me. Probably sometimes I still look up things in dictionary because I did not learn those words in the what called native manner. I learned them by translation, and some of them I don't know. But it also happened when I was admitted to Caltech. Went to apply for a visa. And the consular officer asked me, "Are you immigrating?" I said yes. And that was a wrong answer. So he was alarmed. So he took a piece of paper and wrote in big letters, IMMIGRATE. Do you know what is immigrate means? I said yes, to go from here to there, that is immigrate. So the rest of the things were in order. He did not reject my application, but he gave me a 2-year visa. Caltech was okay, it's a well-known institute, and assumed that yes, they have made the selection properly. He gave me a 2-year visa. So after 2 years got over in Caltech, I had to do some jugglery to extend the length of my visa, and that worked out. But these are the kind of things which also happened, and I learned some lessons from it about, well, what can a lack of technical knowledge about certain words can do to you. And yes, that brings me to the story which I just described at the outset about my thesis, and afterwards what happened. Well, Rajan Gupta said something in his opening remarks. I don't know whether it was clearly audible or not. Some part of it was and some part of it was not. But that is a part of life. And one thing which I kind of adopted from my experiences and also from whatever I learned is that what is the meaning of life? I had learnt Indian philosophy quite regularly from my childhood. I adopted it with various aspects which I came across in studying about biological systems and adventures. Well, that is another story, but the gist of it is all that matters. And that was that biological evolution has improved something. Improved in the sense that the new thing, whatever came, somehow helped the future generations in some way or the other. And there were other things which didn't work right and they have fallen by wayside. And we call them in computer science kind of analogy, one is software and another is hardware. The hardware is essentially all recycled and improved, and software is a subsidiary and it is forgotten after its need is over. And what are we left with at the end? That the accumulated knowledge has gone into our genetic information, in our education. What it does is tells the future decision making processes what is useful and what is not. What is not there? No names. There are no names of whoever the bacteria or the previous generations of living organism discovered and put it in our genes. What has remained is the knowledge. And so, names don't matter. What matters is that are you able to contribute something that is useful for the future generation? And in that spirit, I have never bothered about getting my name somewhere or asking some credit somewhere. It's not important. And yes, that is my meaning of life. I will stop there. Thank you.
Thank you, Apoorva. That was truly humbling, and I can, our generation fails to relate to the hardships that your generation must have faced. And hearing such accounts is what gives us perspective on and relate to what we have really, if we have experienced these comforts and have stood on a steady platform, it's because of what you guys have done. And a very big round of applause for what we just heard. And you will remain an inspiration and a guiding light for all of us. And I think we will come to you for various things in the coming future. So thank you for all that you have done. And to mark this moment, we have a brief felicitation ceremony planned. And so I request Professor Rahul Pandit and Professor Sudhir Vempati to come onto the stage, please. And yeah, so we have the most cherished memory of probably Apoorva's, which he has often talked about, which is his interactions with Feynman. So we have tried to crystallize it, literally. And we wanted to gift it, wanted Professor Rahul Pandit to gift it to Professor Apoorva. And we have another. Yeah. And we also have a very special gift from the students, alumni, well-wishers of Professor Patel. So, a group of students, and the idea originated from the, minds, interactions of Srividya here, Chaitali and a bunch of alumni, and Anjani, and they have done something really special. So we are instituting an Apoorva Patel, Professor Apoorva Patel Award of Excellence with a cash prize of 10,000 rupees for the next 10 years with, of course, future extensions. But at the very outset, it's going to be announced for the next 10 years. And the contributions have come from all these people. So we would like Professor Sudhir Vempati to hand over the plaque, which has this inscription, and I request all the audience to read it. And I think Professor Apoorva himself summarized paraphrased this in his own words in the last speech. So, Sudhir, you can. So the modalities of the award will be worked out over the next coming weeks. But we consider it a truly fitting honor to Professor Apoorva that in his name an award of excellence is being instituted for quantum technology students in IISc for the best performer of that batch. And I want to thank all the people who have, put their minds to this and come up with such a beautiful gesture. Anjani, Chaitali, Srividya, and all the alumni who have contributed, the first year batch of MTech students and the current batches of MTech students together. Yeah. And I would then request Professor Sudhir to speak a few words about his interactions with Apoorva, and if after that, Professor Rahul Pandit too. And then we have a cake cutting, and then that closes the ceremony fully. Thank you.
So hello everybody, and it's a great privilege and honor for me to talk about such a distinguished and a brilliant colleague. I am supposed to be representing the entire CHEB department, actually not just my own recollections essentially. And I think all the department would agree that it has been a privilege for all of us to be associated with in the same department as where Apoorva has served for such 35 years. Actually, from CHEP point of view, we have two stalwarts retiring this year, along with Apoorva Deeptiman, who is here, who will also be retiring. So it is a double blow for us, but still we are celebrating, okay? See, we are celebrating on 2 weeks from now, so we will be celebrating on July 19th, so all of you are welcome again to celebrate from the department point of view, essentially. Yeah. Today's conference covers most of his technical contributions in the recent years and his quantum computing side, lattice gauge theory side. I think Rajan Gupta has already talked about his contributions to lattice gauge theories. I know a few of his works. They were the first ones to calculate the chiral parameter, B parameter on lattice. And then, of course, he started work on quantum computing long before many people in this country started, actually, much long before anybody actually. And and as far as this knowledge goes, it doesn't restrict to these two fields, it covers most of the branches of science actually. And I don't think I have much to add there, except that he's a brilliant physicist, and we all used to go there to him whenever we have questions or anything. I personally interacted with him on especially QCD related questions or something. But one major thing one would not expect from someone who is such a brilliant and caliber is that one would not expect that he's so generous with his time. He's extremely generous with his time actually. As for the department's sake, he has been super generous for us. Actually, I'll just give you a couple of examples. We are a small department with very limited resources, and I give you a couple of examples. When I first joined CHEP, we didn't have any computers. We had students, but there were no computers. Okay, and the students are going to join. So I went to Apoorva complaining, Apoorva, we have no computers, we have students going to join. And he said, we have a FIST cluster, which is there for I don't know, for donkey's years. It was there. Okay, and said, let us hack it up into small computers and distribute it among the students. And he did it personally, and I was just assisting him. He did most of the work essentially. And we distributed the computers, so the students had their first computers. So he was such a simple man, so generous with his time. So, and it was very helpful actually. And secondly, when we were moving from the old building to the new building, the amount of time he put to pursuing all the people related to this building, how it's being constructed and everything, it's just amazing. He went almost every day here, visited how it is updated, how it is being, I am sure both our department and physics will thank him for that, because I think every nook and corner, he's the only one who knows about this building actually. Every nut and bolt and everything about this building, he knows it actually. And of course, he's also very careful with public money. He never wasted it. He was always careful. But he never trusts secretaries or anybody. He does everything on his own. Even today, I think he had some POs which he will fill it up completely and come for me with see. Okay, he does it everything on his own actually. But there is one secret which I have to tell you. He had black money. Okay, so this is the departmental black money. So we had some source of money which the institute didn't have. Okay, and he was maintaining it. It was all in cash. Okay. And it was, and because we could only trust Apoorva to take care of that kind of thing. So in cases when the department was going under, or we had some visitor which we had to pay, the department didn't have any money, or some student who didn't have any scholarship or something, we had to run to Apoorva. and ask him for money and everything essentially, and he'll dig out from his cash all this money and give it to us actually. So he was, it was excellent being with him almost. And I know that all our secretaries are jealous of him handing all this money because they wanted this pool. Actually, they want to control on this pool actually. On a personal level, he has been very kind, not only a great mentor on many things, computers, physics, but on a personal level too. He helped me when I was sick. He used to inquire me daily, and then he asked, Rashmi and everything, they helped me to get a second opinion. And they were really, really kind to me actually. And after several years, I think I finally, a couple of summers ago, he really pushed me, inspired me to study quantum computing courses, so which I did on the CERN website. Okay, and it was completely his inspiration essentially. And then I started attending some of his lectures on that one also essentially. So we will not miss him, but because he is going to be around actually. So I wish him all the best for all his future endeavors, and I wish him a lot of success, good health and everything on all his quantum computing pursuits actually. All the best, Apoorva. Oh, okay, I also have a moment too. Okay, thanks. Yeah, sure.
Well, I really don't have much to add. You have all heard, and we all know what a wonderful physicist Apoorva is. I don't remember exactly which year he joined, but his reputation came even before he was supposed to be brilliant. He was brilliant. He continues to be brilliant. You know, if he's one of those physicists where, I don't work in his area, but if I were to get stuck on some problem, I'm sure if I went to his office, he would answer any question I have. He has a really encyclopedic knowledge of physics, which of course shows up in his research. You've heard of all the important things he's done. But later I interacted with him in a sort of, semi-administrative setting. He was always took the lead, and we started first, with a Center for Quantum Information and Quantum Computing, which was held by Professor Anil Kumar, and he, of course, was a very important part of it. And then it grew from there, and when the DST came to us to sort of put together a vision for quantum computing, quantum information in the country, which today you see as the National Quantum Mission, it was really Apoorva who did everything. We just stood there and helped, and you can see the results of it. So what more can I say? He's just wonderful, and I thank you for all the good that you have done for the country and for the Institute, and we'd love to see you here. I'm sure you will continue working, and we wish you and your family all the best, good health, and I would love to continue learning from you. Thank you. Thank you.
So with that, we have come to, we are coming to the closing of this event, and to end we have a cake cutting by Professor Apoorva on the occasion of his superannuation, and after that we break for high tea. I request ma'am, Rashmi ma'am and Aavishkar to join on the stage, please. And I don't know if you can see from there, but the inscriptions on the cake are from his notes. So it's a very thoughtfully crafted cake, and the credit goes to Chaitali and Srividya here. And yeah, Apoorva. All of us are going to partake of it. Yes, yes, please. So, let me also take this opportunity to thank a lot of people. The list is quite long, but most importantly, I want to thank Rashmi ma'am, Anjani, Chaitali and Srividya, who through their discussion came up with this idea of holding an event, celebrating Apoorva's contributions. I jumped in at some stage and just gave blessings to a few things, but all the groundwork was done by those two people standing there. So they deserve a huge round of applause. And all the volunteers, all the MTech batches, the first batch, second batch, and third batch, and there are roughly 30 names. So I'm not going to reel out all the names. So please take this as a personal token of gratitude from me for making this a grand success. And I want to thank the physics department and CHEP department. I have had interactions with Sudhir during the course of planning this, and it's been very smooth. And I want to thank physics for giving us this space to hold the event. And then I want to thank all the speakers who have participated, both coming from far and wide. Vijay, Parveen, Umakant, Mahesh, everyone, for traveling from abroad, from various parts of the country to participate in this, and purely out of their affection and respect for Apoorva and for what he has done to the general quantum technology scene in the country. And I also want to thank all the alumni and old friends of Apoorva's who participated virtually, Dr. Rajan, Gupta, Love Grover, who could not be online but who sent a message, and Professor Anil Kumar, who we were not able to connect to him during the day, but he was very interested in being part of the event, and all the students who sent messages. And I also want to thank the photography videography team, and we apologize for any inconveniences that were caused due to glitches in the audio, and probably those who were reliant on the web stream would have faced more difficulties. But overall, it was a very memorable day, and I thank all the participants and students who kept the auditorium full throughout the day, and that shows the kind of popularity Professor Apoorva commands amongst the students. So with that, thanks a lot, and we will now break for high tea.
This is for Bala for guiding us throughout the process. Come on, join us. You.